All right, well, welcome back to the day two of the GenAI4Science workshop. We had great discussion yesterday, lots of interesting talks and discussion, and it's again good for us to remember that asking the right questions is the most important thing. We don't have the answers, we don't have to have the answers, but we are at that stage in this revolution that we know there's a lot of excitement, there's a lot of possibilities. But the road ahead is very long. To get to the kind of problem that we want to solve, we need to address a whole bunch of issues. And I think that's what you have to keep in mind. So as long as we keep asking the right questions, we have a hope of getting there. So we have a series of talks and panels today. There's in the morning session, we have 2 talks and 2 panels. In the afternoon, we have 1 talk and 3 panels and a conclusion. I'm very excited. I'm learning a lot from all the questions being asked. And sometimes we have answers, but that's okay. You know, the questions are the most important one. So with that, I'm going to hand it over to Professor Anand Grama, who is going to now introduce the 2 speakers and get started on the panel. Thank you.
Thank you, Dr. Kumar. It is my distinct pleasure to have 2 of my dear friends, one from my childhood and one from more recent. Wonderfully talented people. Our first talk is by Professor Ganesh Subbarayan. Ganesh is in the mechanical engineering department at Purdue, incredibly talented, smart person. Leads the Purdue Smart Institute for Digital Twins for It's a very large project funded by the federal government. Ganesh has done incredible work on both on data-driven digital twins and mechanistic digital twins. I've had the pleasure of seeing Ganesh talk in many, at least a couple of instances, and I said, we must have Ganesh over here. So I'm sure we'll enjoy Ganesh speak. Ganesh, thank you so much.
Thank you so much, Anand. That was a very, very generous introduction on the part of Anand. I don't know if I deserved it, but thank you so much for the honor of being here. I made a title because I wanted to focus on the importance of data generation automatically for what we want to do for AI. But I'm going to meander a little bit, if you will, to get to that point. So I'll talk a little bit about, so I'll start with some historical background and sort of like tell a story, if I may. So I'll start with my overall theme is modeling for design optimization. And more recently, ML modeling for design optimization. So I'll start with this example. This is from a long time ago. So we were trying to model how bones might respond to prostheses that are, a patient might have a new prosthesis, and you don't want the surgery to fail. You want to understand how bones would respond to the presence of the prosthesis. And the hypothesis is that bones adapt to loads that are applied on them, especially load-bearing bones like our femurs. So, and there's a mathematical way to describe the structure of the bones, and that in turn can help us identify how the bones might adapt when prosthesis is inserted. And it turned out there is a way to formulate this problem as a multi-criteria optimization problem, came up with a variational formulation that you're seeing there as a weighted trade-off between metabolic cost as measured by mass and stored energy, which provides a risk of failure. And that's all, very nicely, those kinds of formulations are all there for many, many bone behavior, animal behaviors, structure, and so on in that beautiful book that I've shown at the bottom there by McNeil Alexander. And what I found out was if this problem turns out to be a topological optimization problem, what you're trying to do is at every point in that structure, you're trying to change the density to find what is the optimal density driven by that criteria. And that is a large number of variables, optimization variables, and for each change in variables, you're going to have to do the analysis. And it turned out for one iteration of optimization, it took about 16 hours on the computer that we had at that time. So it was not going to be very efficient. However, if you could somehow spend the effort to figure out the analytical sensitivities and implement them, you could solve it in 3.5 minutes. So what that taught me was that all the problems, typical engineering problems, analysis problems, are more expensive on the analysis side than on the search side, and then on the optimization side. You might have thousands of variables. Finding the next search in a direct search method is far quicker than the step that requires analysis. The analysis, therefore, we need to do everything we can to speed up the analysis. So one thought, and this has been consistent thought in all of, at least in mechanical design optimization, is maybe replace the analysis with a surrogate model. And the surrogate model might be a machine learning model. And this is not a new idea. This idea originated in mid-90s, I'm going to say, mid-90s. So then we started to explore machine learning models in late 90s and took a set of example problems, some of them very simple, like the ones that you see on two-variable problems, algebraic problems, and some that look a little bit more complex, structural problems. And we went through and evaluated, using machine learning models, how the neural networks perform on these class of problems. And as with any algorithm, what you're trying to figure out is what is the trade-off between accuracy and efficiency. And what you find is what we found was that machine learning models were, at that time, with the resources that we invested in building those models, were not very good. We spent significant amount of time for training, and the red box here is the time it took to train and then to do the inference on the trained model, compared to what it would take for a classical optimization, which builds a series of local approximations and progresses downhill on the local approximations. So it takes far more effort to train, and even then you don't get very good accuracy. Your errors in function value percentage can be pretty large, is what you're finding here. 80% error in variable values, 20% error in function value, et cetera. So not doing very well. So the message to me from this learning experience was that you need to invest a lot of time in training the model. And if training is an important part of the overall solution process, you're not going to be efficient. So if training can be done offline somehow, then you can be more efficient. So then later, we worked on another example, and this example is on device color mapping. We were mapping color between, say, the monitor to the printer. This is a project that IBM was very interested in. IBM was, at that point in time, marketing room-size printers. IBM got out of the business. So I'm an ex-IBMer for Lior. So IBM got out of that business. So, but they were trying to figure out how to map color from the monitor to the printer, because their customers wanted to make sure that if they were buying a room-size printer, those printers produce colors as accurately as they could. So this is the gamut mapping problem. So color can be represented in a three-dimensional space in a device-independent manner, but the printers and the monitors don't represent colors the same way. Printers represent them subtractively, monitors represent them additively. So you have now in the color space, you need to go from this triangular shape, which is what the monitor produces, to range of colors that monitor produces, to the hexagonal shape, which is the range of colors that a printer produces. And the one that you see there, IBM Teak, is the one that IBM was manufacturing at that time. So we needed to figure out a way to map from the triangle to the hexagon. So we came up with, again, what we did was to print thousands and thousands of swatches of color and measured them painstakingly. This is what grad students do, right? Unfortunately, this poor grad student had to measure 7,000 patches of color. And then we were able to build a machine learning model, neural network model, that we were then able to use to correct on the fly the colors that the printer would produce for a given image on the screen. So we were able to patent this, and this is around 2000 or so. We were able to do this, and this told me that, again, this I learned from my previous experience, that here training time is not critical. I can do it offline. Now I can use the trained model to do the inference very quickly, and that was more important here. I was able to do that. So more recently, this is some work that I have ongoing with a colleague of mine, Dan Jiao. More recently, we're looking at modeling for advanced packaging design exploration. This is a topic that's very close to heart to Sachin here. So so one of the drivers for this is that the energy cost growth of AI computing is exponential. And it's expected by 2030 that, depending on who you believe, the number could be anywhere between 10 to 30% of total energy produced is going to be consumed by AI. So depending on who you believe. But the energy resources that are available to us are limited. So we need to figure out a way to reduce the energy. And this is where advanced packaging has been proposed as a way to, the ideal would be if you do everything in a single chip, but if you, at least for performance-wise and energy-wise, but the fact that cost drives us to not make single chips larger than about 858 millimeters squared, forces us to break the chip into smaller chiplets. And those chiplets you want to integrate as closely as possible to consume less of energy. Here's an instance of one of those examples of AI-oriented advanced package, and it has many elements in them. It has high bandwidth memory, a processor that needs to communicate with the high bandwidth memory, because now we are trying to push through trillions of parameters of our AI models between the processor and the memory. So this processor memory communication is the biggest source of energy cost, and that needs to be somehow minimized, which means you need to bring these things as close as possible to each other, ideally, if possible, to stack them on top of each other in three-dimensional stacking. So in this design process, you need to explore alternative configurations of these chiplet arrangements, and that in turn has, design would require criteria like, does the resulting package have the right electrical characteristics, right thermal characteristics, and right mechanical characteristics, because this package could warp, etc., could have high temperature. So what we did was to, again, explore for various configurations. We wanted to come up with a machine learning model that can handle it's trained with all the possible configurations, not just that, but all the possible flux boundary conditions that you might have, convective boundary conditions that you might have. So we didn't address generality of Dirichlet boundary conditions, but the Neumann boundary conditions were general. Any arbitrary Neumann boundary condition could be. So we trained the model. It required 3,200 training data points and 800 testing data points. And with that model, it was able to produce accuracy on an average of a 0.0053 kelvins and test times, which are much, much smaller than 1 second. Now, to build this sort of a model, this is a key point that I want to make. To build this sort of a model, one needs to automate the analysis procedure, because the biggest, by a Sandia study from 2005, the biggest bottleneck to finite element analysis is really the mesh generation. So it's about 50 to 75% of the time in the 2005 study was mesh generation. It's the human in the loop that you want to eliminate, which means you need to be able to automate your analysis, take all the possible different boundary conditions, power maps, configurations, and be able to automatically analyze them. That in turn, what it required us to do is to come up with a data structure to describe the geometry and automatically mesh it, assign power maps automatically, assign boundary conditions automatically, solve, and then interpolate, and then develop the network. So that's the part that I want to emphasize. So finally, I will leave with couple of thoughts. And this is all inspired by Anuja's presentation yesterday. So Anuj was generous enough to share his presentation last night. So I had some opportunity. So one thing that that I've learned over my career, I started off as a computational modeling person, but I've more and more, when I work with industry, I find that I don't get enough insight with computational models, and the insights are far better with analytical models. So I find that as we go from, say, computational models, numerical models to analytical models, my insight is better. And the insight is even less compared to computational models with data-driven models. So is there any way for us to provide that insight from a model that's constructed purely from, abstracted purely from data? Here's an example. So this is a project that I would give to my students who believe that anything they see on a screen produced by finite element code is accurate. So I'll give them an analytical problem and ask them to estimate the error for various meshes. So they will do a convergence study and find that their finite element model is often pretty far off. So is there something like this that we could come up with for machine learning models? Are there standardized tests? Finite elements have patch tests. Those qualify the elements. So do we have something equivalent to a patch test? Do we have validation procedures for machine learning models? Is there something we can come up with? So here's one thought. And the other is recently we've also been exploring physics-informed neural networks. These are linear PDEs. And what we find is what you're seeing in the screen is this data point is the finite element model analysis. The x-axis is mean percent error. The y-axis is computational time. And that's where the finite element sits. And all of these are different architectures of physics-informed neural networks. We find that no matter what the architecture is, even 100 by 100, it doesn't quite produce the speed and efficiency, the speed and accuracy of the finite element solution. So I think, in my opinion, physics-informed neural networks are not efficient or accurate yet, but they have the potential possibly. Here's one more thought. We know that overfitting is very common in machine learning models. Here's a simple analytical function. I generated data from that analytical function by adding noise. And I fit different curves to this data set. One is the blue dashed lines are polynomials. They're going to be highly oscillatory. This is something that's well known in CAD, in mechanical CAD, but nevertheless it illustrates a point. The blue is highly oscillatory, and that is my polynomial. And the red is the cubic Hermitian, and you can see the green line is the machine learning model. The reason why it's jiggling is because if I move 1 point, the whole machine learning model curve changes quite a bit. So it doesn't have what is called the local control. If I change at 1 point, all I want to have is a local region to change. These are some well understood properties in computational mechanics. There is this property called partition of unity. That property ensures, and compact support, that property ensures that if I move a node, the influence is local. And there is also this partition of unity property assures me that if I have convergence in a local region, I assure convergence in a global sense. Is there any assurance of convergence, or is there any tunable level of smoothness that ML can produce? These are all questions that came up to my mind based on my background. And the last question is, can we provide more insight? More insight. So for instance, if I have physical systems, I can construct governing equations numerically as k times u equals f. And then I can differentiate it, and I can semi-analytically calculate sensitivities. And that tells me something about the system. Now, is there a way for me to do the same thing with an ML model? Can I somehow estimate sensitivities? How do I systematically infer more about the behavior of ML models rather than treat it like a black box? So these are all some questions that came up to my mind. And the last, I will just spend a couple of slides on the new opportunity that we have. And Anant was very gracious in talking about the digital twins and the Smart USA Institute. It's a new opportunity for ML as well. So this is the Federal Institute that was stood up last November. It's a $285 million award by the NIST to SRC, Semiconductor Research Corporation. And those are the founding members there. When it comes to digital twins, it's not just the computational models, it's not just the machine learning models, but they need to have a bidirectional feedback with the equipment, with experimental equipment. So the models are corrected by data from experiments in a continuous loop in real time. So this is a new opportunity. The model needs to be fit for the purpose. You cannot have one model, one size model for all. Then it also, it's more than just simulation because there needs to be this continuous feedback. It's process being guided by models and models being refined with process data, manufacturing process data. And of course, you need to also verify, validate, and an UQ of these digital twins. So with that, I'll stop and thank you for your time.
A nice presentation. I got a good overview of the computational issues. The question I have is in the first thing you had done, I guess the stresses optimization. So in terms of the input data, because for neural networks, you need a lot of training data. So this training data, you kind of simulated them or you kind of got it from somewhere?
No, you basically, you have to train your machine learning model, neural network model. So for each function evaluation, you go do a finite element analysis, or in this case, matrix analysis.
So I wanted to understand better the matrix, the graph you put up showing that physics-informed neural networks are both higher error and more computation than standard PDE solutions. My understanding is that that is true if, in general, okay? However, the reason there is excitement about PINNs and generally the use of machine learning to solve PDEs is because many problems have a structure where a large part of the PDE solution is dumb and boring.
I'm sorry.
Is dumb. It's repetitive. It's, you have to go through the loops to do it, but it's not interesting. And those parts, you can basically jump over if you're doing it through neural networks. And so there might be some things that we can say about the structure of the problem that would change the conclusion that you have on that slide.
The way I'm looking at it, I'm a computational mechanician. Bhaskar here is a computational mechanician. I would love to hear his thoughts as well. The way I look at it is neural networks here is just another basis function for solving a boundary value problem. So in that sense, you should then ask the question, what is the efficiency of this basis function versus a standard Lagrangian function, for instance? So in that sense, I feel there needs to be more work. We need to still prove its convergence. Yes, neural networks are universal approximators, but are they any more efficient than, for instance, the Lagrangian functions we know very well? We know their convergence very well. So that's where I'm coming from. I said this is preliminary. This is, I know experiences will be different.
So if I can add to that, right? So from a, again, computational mechanics standpoint, from our experience, from a forward model perspective, if you have to solve a single equation one time, in this case AX equals B, I think we have 60 years of linear algebra, numerical linear algebra codes. I don't think any machine learning model can compete yet. But so in terms of a single forward simulation, I think conventional scientific computing beats pins other things right now, right? So purely because we are solving AX equals B problem versus we are solving half AX square minus BX optimization. But when it comes to like what your point about when you're looking at, if you can frame this as a problem of a family of PD solves, then I can amortize the cost of training the machine learning model on multiple instances, and then the cost of during inference instances from that family, then we are much better with solving using machine learning. That's where I really like your problem of framing this as an optimization problem where you have the same class, a family of PDEs, and then you can amortize the cost. So.
Yeah, fair enough. Thank you. Agreed.
Thank you, Ganesh. I really appreciate one thing that you mentioned about verification, validation, and UQ. There is a ASME committee on that, called ASME. VV10 committee, which is on computational mechanics, 20 is for nuclear and structural, I think. So I started almost 8-9 years ago, VVUQ for advanced manufacturing, especially using machine learning and AI and all that. So your point is very well taken. In fact, the committee has actually published 2-3 standards now. The foundational problem is, what do you mean by validation if it is completely data-driven? Okay, so you don't know the physics, you're trying to understand the physics and things. So that's one of the questions that people are trying to answer in terms of how do you go from simple regression model to causal relation, and we are not there yet. So I think you're raising the important point there. I strongly would like you to come to that VV50 committee and probably give a seminar there. I think we have many companies in that committee. So I'd really appreciate if you can come to that.
Thank you very much, Sudarshan. That was very kind of you. I just want to say that I just want to add a point. Sandia, for instance, has set a benchmark problems for fracture problems, for instance. Maybe this is a time to generate those sorts of benchmark problems.
I'm also a mechanics guy. I'm glad to see that you're attempting that. And sometimes, Mr. Naive question, your finite elements, so each element you have a basis function, then you're constructing your KU equal to F, right? So if you do the finite element, you got the K, and with the neural net or machine learning, can you come back to a basis function for the whole thing? I know reduced order model, different concepts are going on,
Yeah.
projection methods and all.
Yeah.
Did you venture into any of those kind of things?
Indirectly. So this problem, you can turn this into a multi-level hierarchical problem. Anant and I have discussed it recently. So it's a multi-level hierarchical problem. Then the only way you can do that, in my preliminary opinion at least, is that you need to have sensitivities. So you can poke the model, try to get sensitivities, and construct some information about the model. If it's a linear system, then it becomes relatively straightforward. The problem is most of our problems are not linear. So then how do we construct information about the system? So we need sensitivities to start with. Even for UQ, you need sensitivities to start with.
You remember we used to have a lot of work on floating point arithmetic and round-off error, floating error, truncation error, etc. So I have not seen anybody talking about that in neural networks or machine learning as if they think that they have infinite precision. How do you become computational mechanics and all that? One of the biggest problems they consider is if it is a truncation error. That is the whole idea of random number generator. You force it, and then a deterministic algorithm is trying to generate a random number. So you may get that in neural networks too. So I have not seen much of that work. Have you seen some of that?
No, I'm not very familiar with that aspect of that.
I can answer that a little bit, Sudarshan. So there is not so much from a stability perspective. There's a lot of work on speeding up neural networks in the energy perspective, where there are these empirical results that you find that the early layers of the neural networks you can quantize a lot. So you can get away with 8-bit arithmetic in the front layers. The back layers you tend to need more and more precision, and you can more or less maintain the backward accuracy of what you're trying to do an inference from. There are other ways of characterizing sensitivity as well. So for example, there is understanding of how the rank structure of the weights changes through the networks. In fact, there's some very interesting results where you can argue that the total information content through the network stays the same. In other words, more information flows through the middle layers, the rank actually goes down, but then the rank goes back up at the back end of the neural network. And there again, the motivation isn't so much sensitivity analysis, it's how little computation I can get away with. So for example, if you have a dense layer from layer 1 to layer 2, you don't have to train all n square weights. You can get away training k times n weight, treating it as a low rank matrix as opposed to an n by n matrix.
Yeah, I mean, those are many techniques like that. But going back to what Bhaskar said, at the end of the day, you have to solve Ax equal to b. Whether you're going to do sparse matrix or whether you're going to do canonical transformation, making into diagonal matrix, requires floating point arithmetic. So
let me use my moderator's prerogative here to add my perspective to Bhaskar's perspective and Jack's perspective as well. you're absolutely right. If it's kind of like saying that if I have multiple right-hand sides, let me use the LU factorization, and I can use the LU over and over again. So it's kind of like saying, let me train a neural network. If I have multiple right-hand sides, I can do this over and over. The only difference between what we do there and what we do here is there are no bounds on generalizability. So if you have a domain that's dynamic, you have discontinuities, you have inhomogeneities, you are pretty much at the mercy of the neural network. You have no idea what you're going to get the second and the third time you're going to do inference. That is the only part that scares me there. But that said, let me argue against myself, because I like arguing. In these cases, I think forward error is not as important. So did you get your simulation error? Did you get the simulation quantities right is not as important as saying whether you got the objective function, the design parameters right at the end of your objective loop. So you could be you make all kinds of mistakes in your simulation, but if you give me the right objective parameters, do we really care if you made all of those mistakes? That I have never understood. So smarter people than me probably need to.
Yeah, that's a question that needs to be resolved in my mind. That's very critical in my mind for a machine learning model to provide me insights. If I didn't pick the right variables, how do I know what is the right? So that insight is lost. I can do that with analytical models. That was my point.
We'll take one more and then maybe we can. Yeah, last question.
Thank you. So in this training of using surrogate model for optimization, one of the perennial problem we have is that the surrogate model deviates from the raw model, right? So sometimes people have this continual training, online training to keep it authentic. I wonder if you guys do that sort of thing.
So this work was done 25 years ago. We didn't do any continuous update of the surrogate model. So we basically built a surrogate model to try to get as low an error as possible. And given I don't remember all the details of when we stopped the training process. And then we basically used it compared it against a classical optimization approach where we are constructing local models. That's all we do.
Yeah, they veer off to different paths because when you search
it wasn't a dynamic problem. This was a static problem. So in that sense, it's it wasn't as much to see if the time evolution of the response changed, veered off. It was just to see how close we got to the final solution.
Thanks, Ganesh. Thanks. Let's thank the speaker again. I love it that we had such a lively discussion, and I'm sure we all have opinions. Our next speaker, it gives me an incredible pleasure. My friend from 45 years back, we grew up together, incredibly talented, brilliant individual, Dr. Surya Iyer. Surya is the CEO of Polar Semiconductors. He's going to tell us the challenges they face in the real world. I mean, we sit here in our ivory towers and think that we got things figured out, but the real world tends to be quite a bit different, I figure. So, Surya, we're looking forward to your insight.
And another neighbor friend of ours used to. I have some memories. We did, yes. But it was good old days. So thank you. While we're getting set up here, I just want to say, really a pleasure to be at this forum and honored to be invited to speak. I'm going to try and bring. By the way, can you, the people in the back, hear me reasonably well? Okay, good.
So which one's yours?
Mine's this one, last one here. Yeah. And so I want to bring a perspective from the industry point of view. I'm going to talk, as the slide deck is being set up here, I'm going to talk first, introduce the company that I work for. Some of you may have heard about it. We're kind of the claim to fame is that we were the first CHIPS awardee in the United States. So Polar Semiconductor was the first company to get CHIPS award under the Biden administration, CHIPS and Science Act. So I'll introduce Polar very quickly. and then talk about our evolution of collecting data, using data, and controlling the process in the manufacturing facility. And then go a little bit deeper and talk about things that I think would be useful in making Polar more competitive in the world as a manufacturing facility in the United States. Just to kind of bring the economics perspective, manufacturing of semiconductors is dominated by Taiwan mostly, and to some extent China is now catching up. But the whole point of the Chips and Science Act and other initiatives, both in the previous administration and this administration, is to try and bring that manufacturing capability and capacity back to the United States. How successful that's going to be depends on a lot of things. And one of the most important things is that how can we keep the technological edge while keeping costs down and efficiencies high. So that's kind of part of the discussion that I'm going to get into a little bit more today. And then introduction to Polar in one slide. Polar is a company that's been here for a long time, actually. We started as Control Data. So one of the original computer makers in the US was Control Data, and it has transitioned over different ownership. Most recently in September of 2024, just as we got the CHIPS Act money, we also got private equity, so we became not only a US located company, we became a US owned company. And that has implications in terms of national security and other things that will also be relevant to this discussion. We are a power semiconductor company. The previous presenter talked about a lot of power being used in AI computation, servers, and other things. Our specialty is power management chips. So we make power management chips that go mostly into automotive, but also to a lot of different applications in now growing into the AI ML space than ever before. Any of you interested in visiting Polar, I'd be more than happy to host you. If you're a student, if you're looking for positions and jobs, I'd be more than happy to talk to you. We are growing, we're expanding, and we need the smartest people that we can get. And that's another piece of that competitive edge to our competition across the world. So we're about a 600 people company. I don't want to spend too much time here. This is not an advertisement for Polar. Let's move to the next. This is kind of our evolution, where we have been and where we want to go. And almost every semiconductor factory, or fab as we call it, is a highly automated factory. Everything, as much as possible, is automated. That's because it needs to run 24/7, 365. We don't stop for Christmas. We don't stop for Thanksgiving, Ramadan, Diwali, or any of that stuff. It keeps going all the time. And so you need to have a lot of automation. You need to have a lot of efficiency. The amount of investment that you put into a semiconductor fab is incredible amount of numbers. For example, the expansion Polar is doing is $500 million. The kind of expansion that Analog Devices or Intel or TSMC or Samsung are doing are another 1 or 2 orders of magnitude bigger. 20 billion, 200 billion approximately from Micron. So these are large numbers. You have to make sure that the factory is running all the time, high utilization, so you get the economics to work for you. So some of the things we have implemented over the past maybe, let's say, 10 years or so are things like the FabGuard system, which is a fault detection system. It collects data from machines and tells us if something's going wrong ahead of time, so we can shut it down before we scrap thousands of wafers and destroy the product. We are using a lot more robotics. If you walk into the fab, you'll see R2-D2 and Rosie and all these robots walking around the fab. And that is huge in terms of efficiency and speed. In the past, we used to have operators move everything through carts. Literally, operators would be walking about 12 to 13 miles a day in a shift. Incredible amount of strain on knees and other things that are now avoided by the use of robotics. We've also introduced something called, about a few years ago, we introduced intelligent scheduling system. So you can imagine about 500 pieces of semiconductor equipment with about 60 to 80,000 wafers, 8-inch wafers in the line, have to be optimized so they can find their way from step number 1 to step number 450 or so with absolute efficiency, fastest way out of the fab. That is an incredibly complicated optimization problem. Again, ripe for things of the nature that you all are experts in, right? That's one of the key applications that would be very useful. By the way, the TSMCs and the Samsungs of the world have 400, 500 AI engineers, AI ML engineers working for them. And I'll tell you how many of them are working at Polar in just a second. The other things we're doing, are really starting to get into the AI ML world, right? And I think that is the differentiation that we need to be successful and to be able to compete. Because at the end of the day, if we can find and squeeze out those efficiencies in a factory that is transforming, has a much better chance of success than a factory in Taiwan, for example, that's already established and just runs. So you have that chance of catching up and beating them. Some of the AI ML efforts, again, I revealed the number of engineers that we have at AI, a total of 1. So 2 of them working 50% of their time. They're also, device engineers, right? So they do data analytics on the side. We started in 2019 with an engineer. We sent this engineer to Georgia Tech to get a certificate or a degree in AI ML. And this person came back and really has transformed the amount of activity in this field that we're doing now. We just hired, I think just about a few weeks ago, our second AI ML person, University of Minnesota master's graduate, undergraduate and master's student. So excited to have her in the team as well. So kind of the things that we're doing are automating tasks. We're doing some computer vision. I think that was original success, was just image type of analytics, just comparing images, finding defects. That was one of the initial successes with the effort. We're also now using natural language processing and other things. I have to, if you haven't judged already, even though I am technical, I'm an engineer by background, I really have no idea what all of you were talking about in the last session. So, but I did take a class at Wharton on AI for managers. So I know how we can use it, how we can make money out of it. So here's an example of what we do. This is something, we are a somewhat of a manual factory. We still have operators in the fab and a lot of equipment. Some of the equipment is older compared to the newer equipment that we bought in the last 5-7 years. And that means different kinds of processes run through it for the same step. And so matching becomes a very, very important piece of the whole, keeping the processes under control. To get high CPKs, you have to match everything as best as possible. So we're using these AI ML techniques to automate some of these tasks. So we have been using this now at least since 2022, if not even earlier, to use this AI ML techniques to match the systems. Huge amount of improvement. And these are not insignificant. We have been able to improve. We're an automotive factory, right? The chips that we make probably are in the car that you drive today. Most likely, in fact. I mean, we make sensors, power chips, and other things, motor drivers, those kind of devices that are most likely in your car. The automotive industry is a very demanding industry. Everything has to be, of course, safe, but in order to make it safe, you have to make it uniform, the same. No matter what it is, it has to be the same every time. So CPKs need to be driven higher to be competitive. We have used this to do that. In the interest of time, I'm going to keep going a little bit faster. This is another thing. We have, I said, about 500 pieces of machinery, about 300 or so different flows, probably 20, 30,000 charts, SPC charts at any point of time. At one point of time, we had a quality issue, and as a manager, I told everybody in the company to own 10 charts and look at them every day. But that was not going to work for too long. That was just a frustration thing that I took out. But anyways, now we're using these techniques, AI, ML techniques, and these things look at 15, 20,000 charts. This 15,000, this is from a while ago. So probably a lot more charts are being looked at every day and constantly being tracked. We're saving a lot of wafers that we would have thrown away by using these techniques. This is more of a kind of a visual slide. I don't know if you can read the words from the back. But again, we're using these natural language processing techniques. This is something that we started using in the last 2 years or so as things have become more mature in this part of the world. We're using it for simple questions that engineers can ask, new engineers can ask, people who are being, especially the technicians who are on the factory floor and don't have bachelor's and master's and PhD degrees. They need to get quick information. They are now able to use these kind of techniques to get some of that information. So they get process questions answered, device physics type of questions answered. You don't need to be a physicist. You can get some of these answers pretty quickly. So we're using a lot more of these kind of techniques. As I said, the defect classification, defect map classification was one of the initial successes. This was, again, resource intensive. So we have a lot of fancy machines that we buy from companies like Onto, KLA. I don't know if these names are familiar to you or not. These are fast imaging. So they will take a wafer and take hundreds of images. I mean, they can go through 400 wafers in an hour, right? And they'll take 100 images each. So that's a lot of images that these machines are creating. In the past, of course, generally speaking, a human would have to see a sample of those images, and if you get lucky, you find a problem and report it and fix it. Because remember, the minute you got the image, it's already gone through a lithography operation, a etching operation, probably a deposition operation before it shows up to this imaging. So we've already kind of no way to recover any of this stuff. So the damage is already done, right? So you want to be able to catch things as fast as possible before the damage over about 10 steps accumulates to, let's say, 2,000 wafers. If you can restrict it to 25 wafers, that's a good thing. So we've used this. The accuracy has been fantastic. Of course, you can see here that it's about 100 times faster than using a human. That's not a surprise to you, of course. Now let's move to things that I see as opportunities and how we can get better at what we do. So we have a lot of different kinds of engineers in the fab. We have, of course, facilities engineers, there's civil engineers, mechanical engineers, chemical engineers, and then we have equipment engineers and equipment technicians, 2-year and 4-year graduates that work in a variety of different areas, different processes, photolithography, etch, measurement, front end of line, back end of line, so metallization, diffusion, implant, epitaxy, and so on and so forth. And then we also have integration engineers who put the full flows together, and device engineers and device design enablement engineers who talk to our customers. By the way, I should start with this. We are a foundry. We're like TSMC, but tiny, right? So that's what we are. So we also have design enablement as part of the offerings that we give. And then we have, so that's just the technology piece of it, right? That's just the technology piece of it. And I tried my best to capture AI ML, and that's the picture I could come up with, is that human head with some circuits inside it. So that's what it is. So that's my way of representing AI ML. And so you can see here the message, what I'm saying here is that at almost every one of these engineers' jobs, there's an optimization, there's a improvement opportunity. And the examples that I have shown you at this point are things that we have done, like, let's say, metrology or defect, that we have done to some extent, right? We got some success there. One of the biggest issues, or the other success, is somewhat intelligence in scheduling the lots through the line. That's another little bit of success there. But the real issues still are process control. How do you get the equipment inputs, which is pressures, temperatures, flows, RF powers, and things like that, correlated to inline, which is thicknesses, uniformities, critical dimensions, and so on, correlated to the electrical sheet resistances, threshold voltages, breakdown voltages, and so on, to the product at the end, which is, you know, the functionality, the probe, the product information that you get out of probing each product. That control is not easy to do. There's a lot of data. The quantity of data is immense, and it is, and I'll come to the next slide, which is where the challenges are. But before I move to the next slide, I also want to talk a little bit about the speed. The top level there is what makes a company successful in the semiconductor world. If you don't have technology, nobody's going to talk to you. If you don't have technology that you can bring to the customer and to the market quickly, they're going to give up on you and go to somebody else. And at the end of the day, if you can't manufacture it for the cost they're looking for, and somebody in Taiwan and China or Korea or, you know, for that matter, Japan or even Europe can do it better, you're gone. They're not going to hang around with you for too long. So that drives the industry. In my opinion, the technology piece is the most important, because that's the getting inside the door piece. And that's where I think the biggest challenge and the opportunity for AI/ML is. I think we're doing a decent job in terms of speed, in terms of optimization. And that side is the operational technology, the IT people who work in the fab, the industrial engineers, automation engineers, supply chain people. You got to get all these things optimized. There's also a training piece of using AI/ML for training. We have done that. We've also looked at a lot of different ways of improving it. Huge opportunity for academic institutions to support companies like Polar. In the interest of time, I'll move to my second to last slide, challenges. This is the reason we are not where we would like to be, and where I think the kind of knowledge and information that's sitting in this room and the kind of knowledge and information we are using is at least 2 orders of magnitude different. We are using a very, very small part of what you all have here. And some of the reasons: data quality is poor. Cleanliness of data is messed up. There's all sorts of data sources. We have machines that are from the 1980s to 2020s, right? So they're all very different. Then we have vendors. All these small, I mean, I'm telling you, the number of people approaching me to sell their AI/ML products has surged in 2024. I did a survey yesterday before while I was getting myself ready for this talk. 1 to 2 in 2022, 2023. 50 almost in 2024 and 2025. So it's just all these companies are springing out. They all can solve all the problems that we have. But our problem is that, again, we are a small company. We cannot go and make a big investment in a small company that's going to fold, that's going to get bought out by somebody, and their whole agenda is going to change, their product line is going to change. So we need something different than these companies. And there's also not just the size of these suppliers. The other problem is the intellectual property. They are dealing with other people's data. Oftentimes, the companies that make the machines for us, the Applied Materials, the ASMLs, Lam Research, and KLA and others, they claim the data being generated in the fab as theirs. So there's also controversy there in terms of just the standards that need to be established across the ecosystem of the semiconductor business, that who really owns the data, who gets to manipulate it, who gets to use it, and so on and so forth. That's not an easy problem to solve. By the way, Applied Materials will sell the machine, but the software belongs to them. We're leasing the software. So there's some interesting dynamics there from an intellectual property point of view. And partners. We have tried to work with other companies in the ecosystem. Semiconductor industry, I don't know about other industries, but I feel like we are a little bit overly paranoid about data sharing. I think one of the famous books of the semiconductor industry is Only the Paranoid Survive. So that's maybe comes from there. Many of us do business with Department of Defense. So data sharing becomes another issue because the Department of Defense has ITAR trusted other kind of CMMC2 type of regulations. And then the other problem is, as I said before, the TSMCs can have 400 AI engineers. We have 2. There's just no way we can compete. And the gap is just going to get bigger unless we find a solution that closes that gap. And this is the way I think we can go ahead and really means what I'm trying to, the message I want to send here is that the only way companies that are small to medium, it doesn't have to, even companies that are medium sized, that are $2 billion companies revenue or less than $10 billion companies, they don't have the same kind of ability to put a gigantic team together. So they're all in the same boat. There's a huge opportunity for a consortium that could be set up at the University of Minnesota or Purdue or one of the universities represented here. And we work very closely already with U of M and Purdue and some of the other colleges represented here. But that combined with a way that we can share data that can be anonymized or to some extent normalized would be a way to get this done for companies like Polar. So with that, I'll stop, and if you have any questions, we're happy to answer.
So yeah, that was wonderful. Thank you so much. Please, Nikunj.
Yeah, thank you for that talk. Really nice there. Are there anything that you can share, like kind of unexpected insights that you got from your use of AI?
A good question. So the question is, did we have any unexpected insights out of AI? I think I have to say the unexpectedness was the amount of data that it could look at very quickly. The speed was unexpected. Personally, I knew that AI was going to speed up things. Analytics would be much faster. We don't have gigantic computers either, right? So we have, and I will be, I will expose my ignorance if I try to tell you what kind of computational capabilities we have at Polar. But I am sure we don't have the latest and greatest, big servers. So I was quite impressed that we were able to take all of this data and get something useful out of it in a very short time. The other thing that I was kind of happy about was a lot of this information in the public domain that our engineer could use to get to some of these solutions faster. Not everything had to be invented at Polar. So a couple of things that I think were useful.
Thanks for the fantastic talk. Mike, I'm curious, like, from you identifying an opportunity for optimization to getting data and then getting out a model and then kind of quality control it, how long, and then deploy it finally, how long is that process going to take, generally speaking?
So that is, again, a very good question, and a lot of it is, so one of the things I personally think that we should be doing is most return on investment is target things that will give us useful results quickly that can either drive technology or speed, sometimes cost. So if we find a problem that we determine, or somebody we collaborate with, for example, in academia, jointly determine would be a good problem to solve using AI/ML, I think we can then put the amount of resources that we need. Right? If I know that I can solve a problem that can generate, $1 million in savings or $2 million in savings in 1 year, we can throw 5 engineers at them. Right? We can hire engineers. We can even get outside people. So the timeline, personally, we have done all of the things that I showed, and this is just a very small subset, has all been done since 2019. So that's 6 years with one person most of the time, right? Half person most of the time. So I think a lot of these solutions can be implemented, or at least formulated, and a solution found in less than a year, and then implemented in about 18 months. I think that's the timeline that we look for.
Thanks for the wonderful talk, and I'm really impressed how much you did with one person in 6 years. Are they looking for PhD positions? Okay. My question was, you showed a hierarchy of opportunities, and you listed materials and effluents, and I'm a chemical engineer and a chemist, so I was curious to see what kind of opportunities were you thinking about there, and if you could elaborate on that.
I'm glad you asked that, because I think there's at least, I know there's one company here, right here at the University of Minnesota, that's working on using some of these techniques to develop new materials or understand existing materials. So part of the technology piece, right, the way we get differentiated from other companies in foreign countries is that we march on the path of new materials. And new materials is a significant opportunity for the semiconductor companies. For example, Polar is now one of the first companies that is going to make gallium nitride on silicon at an 8-inch platform. So we'll probably be the first. We're working with Renesas of Japan to get that done. So that's just one thing. Then there's going to be some kind of AlGaN or some kind of other GaN or some kind of other material that gets us to the, instead of going to 650 volts or 1200 volts, we need to go to 1700 volts. We need engineered substrates. All of these kind of opportunities are there. And I believe that some of these can be solved by the techniques that you are all working on. There's at least 2 companies I'm aware of, startups that I'm aware of, are already doing very interesting work in that world. The effluence and that piece goes to some of the environmental regulations that we have. For example, PFAS was one of a big concern that was raised. I think it's becoming a less of a, or at least it's being pushed out now, or we're getting more time now, whatever it is. But these are kind of things that I don't think the industry is super motivated to solve on its own. It's going to have to be pushed to solve these kind of problems, environmental problems. And if AI/ML has a solution that we can make this thing faster, I think it'll be very, very useful.
So I wanted to applaud your bringing up the issue of data set size and one approach to at least addressing some part of the problem. I wanted to also ask about market power, which often is what forces contracts to go one way or the other, and about data that is not suitable to make open. Do you worry about having your proprietary data used and made available to your AI service providers? They would be doing this potentially from your competitors too. They may, for today, not do anything bad, but 5 years from now, they may know more about multiple industries, or at least some specific aspects, and then choose to exploit that market power, for example?
I mean, you hit that nail right on the head, right? This is exactly the issue, is that every company like Polar, right, if you go to, just in the Twin Cities, we have 5 or 6 semiconductor-related companies, Honeywell, Polar, Collins Aerospace, which is part of Raytheon, Skywater Technology, and Seagate, to some extent, affiliated semiconductor. Just between these companies, it is very difficult for us to kind of get that data and give it to a entity that is going to use that and maybe even help us, because a lot of that can be used for others. We are very sensitive to that problem. And that is why the data cannot be given in as-is form. It has to be changed to a different form, normalized in some way, or I don't know what the solution is, but it has to be changed in some form so they cannot revert back and understand that what we are doing, right? So some of these things are, especially the intellectual property in this industry is super important. A lot of it is not necessarily in patent form. A lot of it is in kind of homegrown knowledge type of form that goes into a lot. I mean, our process flow has been developed over 50 years. The power technologies that we have, not everything is patented. But if you give the data, there's a huge risk that that company can give it to somebody else and they can recreate what we're doing, right? That is something that we cannot accept. And so there has to be a way. And that's another thing that is a challenge for your community here, is that how do you help us mitigate that problem?
So are you able to say something about how you're addressing that problem today?
Right now we're doing everything internal. So that's, which I don't think is sustainable. So we have to find a way of doing it with other people. And the minute you go to some other company, all of these can of worms open up. And there is no standard, there's no, there's cybersecurity standards and other things being developed by SEMI and Semiconductor Industry Association and things like that. There's no data sharing standard. There's no rules for it either. Another opportunity for a consortium to maybe develop. For example, the Smart Institute, right? The Smart Manufacturing Institute would be a place where some of these things can be developed.
And on that count, I did lie. We'll just take Ganesh take a quick question, and then maybe we'll.
It related to the SMART consortium was the question I was going to ask you. What plans do you see for digital twins at Polar? And the second part is, if Applied Materials controls your equipment and doesn't give you access to your data, how can you build digital twins and utilize them for your advantage?
Yeah, so I think, could you repeat the first part? I got the applied materials piece. What was the first part of the question?
Part is, what are your plans for digital twins?
Oh, yeah. So again, that's another, so we are looking at figuring out how to use digital twins. I think that has much higher potential than a lot of these things we're doing in terms of process control, because it's you can really understand what's going on a discrete level basis, like at one machine on one process, you can figure out what's going on. So that's something that we haven't done anything yet, but that's part of the roadmap. The data with Applied Materials and all of these other companies that are there is that the data is accessible to us. We pull that data because it's coming to our MES system, the manufacturing execution system. All of that data is accessible to us. We can do whatever we want with it internally. What goes back to the question is that if we're going to go use a third-party vendor to do some, get some help, or share it with a different company and combine data sets. Again, I have an etcher. Every semiconductor fab in the world has similar etcher. The recipes are also not that different. They all have BCL3 and CLF4 and the same chemistries, similar powers. So there's an opportunity for an etch machine data to be shared from company A and company B and company C, pooled together and kind of come up with a common solution. That's an opportunity there. But Applied Materials will probably not like that. And Applied Materials will not like that because one fab etcher machine might be a Lam etcher and we have an Applied Materials etcher. So that could be another problem too. So there's some serious kind of just logistics and legal problems that we have to solve. Thank you.
We're running a few minutes late, so we're going to cut questions at this point. Thank you so much. We have a panel next on manufacturing. I'm really looking forward to wonderful friends on the panel. Please, Ram, this is your panel. Absolutely, please.
And I think these morning two talks, we are late, so we are. But the good thing is that these talks created a lot of questions that are very relevant for the panel. So hopefully, if you can finish it maybe in 1 hour, then we'll shorten the lunch a little bit.
That depends on the panelists.
All right, okay.
I'll leave it to them. We are open. Let's try to use this thing. It's okay?
Yeah, that's perfect.
Does it come? Oh, pardon? Can you see if it's working, or I don't know.
It looks like it's working.
Do you see anything here? Okay. Okay, now let's start. So we have about an hour, I guess, as per the instructions of the organizers. Make up some time here. So anyway, my name is Ram Sriram. I am from the National Institute of Standards and Technology. Again, thank you for the organizers for giving us the opportunity to have this panel. I guess I'll talk a little bit about that later on, but we have several distinguished panelists here, both from the academics and the industry and the government. So all three parts are covered around here. So from the academics, we have Sachin Sapatnekar from University of Minnesota, and we also have Chai Wending from University of Minnesota. University of Minnesota is well represented here. So we have Sudarshan from the government, Department of Energy, and we have Devesh Bhatt from Honeywell Industries. So we have all the three places being represented here very well. Again, we were given this task by Anant. Now, don't blame us for the objectives and the questions. Blame Anant there if you have any questions on the thing. He set up the thing. So we just agreed to be part of this whole process, okay? So what I'm going to do is not to introduce these panelists in very much detail, and always tell people, nowadays go ask ChatGPT or one of those things more about the panelists. They'll tell you more than you'll ever want to know about it, okay? Provided they have a nice web page. It anyway gathers things from there. So the main objective of this panel is really to discuss the challenges and opportunities for GenAI in advanced manufacturing, and a lot of things are associated with it. So it's opportunities for GenAI in advanced manufacturing. And then, of course, there are lots of things in terms of workplace, the workforce of the future, and so on. So manufacturing plays a very important role in our economy. By the way, last I heard it's about almost $2.5 trillion part of our GDP versus healthcare, which is almost $5 trillion. And then you have, actually most of the GDP is services industry, if you look at it carefully. But these are some of the major things. And then this particular whole workshop kind of covers a lot of vertical domains, as you have observed, from ecologies to agriculture to manufacturing to healthcare and so on and so forth.
So I don't know how much it's covering services, but most of the economy is anyway covered in terms of generative AI. So the number of questions which we discussed before we did the panel here about last week, we all got together and said, okay, let's discuss what are these questions that Anant posed, and a couple of them we also added. But these things kind of can be categorized into the following. One is, if you're and what I'll do is give a brief overview of the manufacturing process, the whole entire life cycle thing around here in the next couple of slides. But the key thing is that you have the design part of it, you have the manufacturing part of it, and the supply chain. And we will discuss this, the panelists will discuss. Each one may not be addressing all the questions, but they will address their favorite questions. Like some of the people are in design, so they'll be talking about design. Don't worry too much of the manufacturing. I think we have 3 speakers here, mostly into the design and software. And then we have Sudarshan, who's mostly into the manufacturing aspects of it. And he has seen also design, but he has also seen several flavors of manufacturing, because he actually the program manager at DOE for several of this, what they call smart manufacturing institutes, which are in different forms. They call it different names, but the smart is in front of it. For those of you talking about smart, there in Japan, you have smart toilets also, by the way. You go to the bathroom and it'll tell you what is your digestive problem and all kinds of things as such. So next time when you go to Japan, ask for the smart toilet, okay? That's very important. Okay, so if you look at the manufacturing as such, I kind of look at it manufacturing from big M, which includes both design and manufacturing. So if you look at this big M part of it, all these are really networked kind of things. Network-centric manufacturing is what it's all about. So you have the design part of it, you have the shop floor kind of production kind of manufacturing systems, and then you have the supply chain. All these 3 things are important. And in Gen AI, actually is going to play a major role in all of them, not a single one. It's going to, as you've seen some of the examples, and in fact, both Ganesh and Surya kind of pointed out a lot of these things in the design part of it too, which becomes very important, I think, using of Gen AI in design. Similarly, you have Gen AI on the production floor, and you have Gen AI on the supply chain. So this is some kind of a vision which I came up with about almost a decade ago, and is still true, because in manufacturing, again, it's not just the technical aspects of it. There are several paths which goes to this future vision of your manufacturing. One path is the advances in manufacturing technology, and this is also a generic slide in a way. It could be electrical, it could be semiconductor, it could be discrete manufacturing, it could be chemical manufacturing. There are lots of things which are happening at the very technical level in terms of manufacturing technology, like innovative processes, either in semiconductor or in materials manufacturing. All kinds of things are happening. Then you have robotics, you have additive manufacturing, which is pretty big right now, 3D printing. Then you have things about sensors, and you have materials and so on and so forth. Similarly, you have advances in manufacturing practice that's happening. As we can see that you have the management, supply chain optimization, the workforce, predictive maintenance, and those kinds of things. And then what we are interested, actually what I kind of come from, is in terms of the computers and information technology. And lots of things are happening here, and we're going to focus on AI part of it, but then there's speed and storage, there's communications, and last but not the least, my favorite is mobile personal computing devices, because I don't really use it for calling my wife. Most of you maybe, the wife may be calling you, that's a different story, but or a spouse, whatever you call it. But most of the time, we actually use it for doing other kinds of things. In fact, ChatGPT and those kinds of things are the ones which are on your mobile phones, and you're always talking. And even on a manufacturing floor, what's going to happen is that all your people will be having this mobile phones, and if there's a problem, they'll just take a photograph of this thing and then ask ChatGPT or one of these chatbots, hey, what's the problem with it? Except that you got to be careful, because these things actually bullshit a lot. They call it hallucinations. That's a different story. I'll come to that in the afternoon when we have a government panel. Now what I'll do is that given my quick 5-minute introduction, I will let the panelists kind of come here and maybe take over the more podium from now and then. Maybe Sachin, you want to come now and talk about? So each of the panelists are going to talk about maybe 10 minutes or so, maybe or less, depending on how they feel. And then we have a short question answer session. Initially, this was supposed to be almost an hour and a half. Now we've been cut down to 1 hour, and it's called dynamic planning, by the way.
Well, we might also talk less depending on how you feel. If there are boos in the back, then I think that's a bit of a sign. Okay, so I'm going to talk about, we are all going to talk about our own fields. I work in an area known as electronic design automation, and it means exactly what it sounds like. You're building electronic systems. You can't build them by hand because the scale is so large, and so you look for automation tools for this. When I first started working in this area about 40 years ago, it used to be called CAD, computer-aided design. And then they said, no, 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 that's what the mechanical engineers do. And guess what? Now I work with people like Ganesh. So we're back full circle here. OK, so just in terms of kind of what powers the AI revolution, let's look at the picture on the top left. This is something that people have used ad infinitum. Basically, what it shows is that the demand for computing has been going up exponentially. The y-axis there is a log scale. And so you can see that until the gray area that was shown towards the right, it was exponential. But then with the advent of AI, that exponential went even steeper. And this means that the design of more complex systems became sort of even more important. Below that, on the bottom left, you'll see another graph, which is also plotted on a log scale. And it shows the stock price of a certain $4.4 trillion company, which shall be nameless. And you can see that, by and large, it also follows that. Sometimes there are some panics about things like Bitcoin mining, et cetera, which brings it down, and then it goes right back up. But to show you an example of a system, you can see at the bottom right, there's the NVIDIA Blackwell chip. And this is an example of an advanced GPU which sort of is at the leading edge of AI computing. I've never heard anyone in AI say, I have enough computing resources, right? So this is really something that has to become more and more important. You have to use kind of more and more complex systems, put them, have them work together, and churn out your computation. Because without this, there is no AI. The reason why there was such large progress since 2012, AlexNet, et cetera, is not just because of the algorithms, but because the hardware kept up. And somewhat coincidentally, there was this company that was building graphics processing units for graphics. And it turns out that matrix vector multiplications were actually really important. And it found a new niche after that. But if you look at one of these advanced chips, it dissipates anywhere between 700 watts to 1 kilowatt or so, which is huge. Your refrigerator dissipates about 500 watts. So think about that in the size of a postage stamp. It has over 200 billion transistors, and that's growing. It occupies an area of about 750 square millimeters. And just the sheer complexity of this gives you an idea of the types of systems that you're building. This is one chip. This is not a full system yet. And so if you try to think about how you build these 200 billion transistor systems, you really can't have a human being figure out where every single transistor goes. All of this has to be automated. And that's the role of electronic design automation. So you can see that all of this gets extracted or abstracted into computer science problems or electrical engineering problems, depending on who you ask, or mechanical engineering. And the idea there is that once you abstract these, you solve these, and you provide these as assistance to the designer so that they can build complex systems of this that actually work. Okay. Now, this, as you can imagine, is going to be an insatiable appetite, and you're going to have to build newer and newer systems. So as Ganesh pointed out really nicely in his keynote, we are going from single chips to advanced packaging systems where you have multiple such powerful chips that are connected in very close proximity so that the communication overheads are low, the cost of transporting data is manageable, and that allows you to perform your computation much more efficiently. The name of the game is not just being able to perform your computation, but to do it in an energy-efficient manner. Because if 20% or whatever number of your global energy supply is going to be for AI computing, well, you'd really like to get that to 10% or less, or something of that sort. So on the pictures that are shown here, that's a chip known as Grace Hopper, also from NVIDIA. I've used NVIDIA examples, but everybody else also sort of has their own versions of this. And one of them is a CPU, the other is a GPU, because each of them performs separate tasks, and they're all mounted on a single package. And this is an early version of an advanced packaging system. OK, so now that you have the context, these are the kinds of problems that we solve in electronic design automation. We handle problems both of scale, because you're trying to build trillion transistor systems in the very near future. So you have to solve really large problems. If you want to sort of perform some kind of an analysis, you have 1 trillion objects at the very least, but many of these are actually divided into sub-objects, etc. Of course, nobody solves them flat. You use hierarchies. You use all kinds of clever techniques to get around it, but they're still very, very computational problems. There are problems also which drive these multiple kind of subdivisions per component, which are problems of the sort of physics at the nanoscale. So now you have quantum effects that come into the design of individual transistors. You have thermal effects, and thermal effects at the nanoscale are very different from thermal effects at the microscale, for instance. And so all of these things come together, and it ends up becoming a multi-physics problem with electrical, thermal, mechanical effects at multiple scales, going from nanometers, which is about the thickness of an oxide in a metal oxide semiconductor transistors of the order of 10 angstroms, to, say, functional blocks, which may be, say, hundreds of microns, to chips, which may be millimeters, to racks, which may be of the order of meters, to data centers, which are possibly of the order of kilometers in the future. So specifically, if we look at just the chip design or the advanced packaging design, this is an incomplete list of problems that's listed here. You need early design planning. You need high-level synthesis for early design. You need automatic placement and routing of all the components, because that determines the communication latencies. It also determines the thermal profile and the power profile. You need things like circuit simulation, timing analysis, and these, if you've heard of the SPICE simulator, that's sort of the most basic simulator, but you can't run that on more than about 1,000 transistors. So you have to have clever ways of doing that. And then there's a whole bunch of other things that are listed over there too. Okay, so what this comes down to is that there is actually a virtuous cycle between AI, hardware, and electronic design automation, which is abbreviated as EDA here. If you have better hardware, then you can build more complex AI models and run them. And then if you build better AI models, then you can actually use better EDA algorithms. You can actually incorporate some of those into EDA. And as you build better chips, you get more data. And data is, of course, as they say, the new oil, except oil is a bad word these days. So if you have more data, then you can actually use that data to improve your EDA algorithms and then build better hardware in turn. And this gives you a sort of a flywheel effect that can accelerate the efficiency with which we build our chips. Okay, so this is by way of motivation. Now, very quickly, by way of what we can do. There were beautiful tutorials yesterday on what GenAI can do. So thanks for all that. And some of these have actually been explored to some extent within the EDA industry. The low-hanging fruit has been using stuff that's all easy to translate. So if you look at things like GenAI, ChatGPT, et cetera, it's really good at character strings, et cetera. So things like design assistants. If I have, say, a new engineer entering a company, should they be hassling the senior engineer who knows everything? Or should they be sort of learning on their own? Well, neither of them is really a good idea. But if you can create a chatbot that that the junior engineer can query, it'll sort of filter out the obvious issues and filter out only the important ones to the senior engineer. More importantly, the thing about this is that because technology progresses so fast, the questions and their answers also change. This means, for instance, the tools might change, so the way that you run a tool under a certain setting might actually change over time, and therefore, it's actually sometimes useful for the senior engineer too, not just for the junior engineer. Okay. The other sort of complication here is what Surya alluded to, which is that this industry has incredible layers of confidentiality. So if you're performing a design, and you work with a design kit from company X, could be Polar, could be Taiwan Semiconductor Manufacturing Company. Most of the time, there are strong NDA things. The only people who are happy about this are the lawyers, basically. And what that means is that, for instance, if I'm working on a design and say another person at another university is working on a design, And if we have NDAs with the parent company, we can't talk about it until we have a three-way NDA that includes the foundry, right? So all of that is really messy, and this makes data sharing very hard. So if, for instance, I want to build a better analyzer for, say, electromagnetic analysis or anything of that sort, what I need are the technology parameters of the underlying technology. I cannot share those. If I share those, I'm going to go to jail. So the best that I can do is to build some kind of a proxy. And that proxy can be built based on sort of public domain data. There's a surprising amount of information that's actually published by companies, which seems to escape the lawyers, which is in the public domain. So between that and between first principle physics, you can actually build sort of some kind of a public domain knowledge database that can translate into foundation models. The problem with that is that very few people are motivated to do that. Industry it doesn't want to do it because company A doesn't want to give an advantage to company B. Academia is happy to do it, but we've got like 2, 5, 10 graduate students. How much can we do, right? So there have been coalitions of people who've been getting together and trying to put this together. So for instance, next week I'll be at a workshop at Google where Google is trying to promote open source data sets for chip manufacturing or chip design. And the reason for this is because Google is a sort of a less interested partner over here. They're actually more interested in getting everyone on the same page than not exactly selling chips for the most part. Their main product is elsewhere. So just to conclude, the one-sentence summary over here is that if you have better hardware, you get better AI, and better AI is going to get you to even better hardware. And generative AI can actually solve a number of problems. I put together a position paper, which came in late, I'm sorry, which talks about the issues that have been successful so far. And the things that have been successful have been design assistance, things like verification algorithms. So if, for example, I'm trying to build, let's say I'm trying to build an adder, so A plus B equals C, what are the test vectors that I should provide? You can actually do that by looking at natural language descriptions, and you can generate those. And then you can become more complex if you build systems that are more complicated than adders. It's seen some sort of benefit in places like analog design, which have been very, very dependent on human intuition. These are small systems, but they are very dependent on human intuition, and this is where AI can help a lot. And so there's a recent interesting paper from Princeton where they built an antenna that looks nothing like an antenna any human being would build, but it seems to work pretty well. Right? So there are all these kinds of things that are on the horizon, and in the interest of time, I'll cede the floor to the next speaker.
Thank you. Thank you, Sachin. And actually, one of the things that occurred to me while you're speaking is that what will be the next chip look like, this AI-generated chip? Like you have NVIDIA, which they have done CPU, GPU, that you have put there one of their chip slides out there. And then you talked about this antenna, which really didn't know, people didn't really kind of know what, I've never seen something like this before. Maybe one can envision using the GenAI techniques, what will be the next chip look like, and what will be doing anyway, okay? Like NVIDIA kind of lucked out on the metrics manipulations kind of thing. There must be some new technology in AI which is going to come out. We have neural networks, you have neurosymbolic reasoning, all kinds of things are coming out. So it'll be interesting to see what will be the next chip which is going to come, okay, in terms of the electronic design automation. Now, we'll ask Devesh Bhatt from Honeywell Aerospace Advanced Technology. So he's going to focus on this verification and validation in a sense, because that's one of the questions that we raised in terms of the safety critical systems and how Gen AI is going to deal with this, plus and minuses.
Yeah, thank you, Sriram. So I'm from Honeywell Aerospace Advanced Technology Labs, and so we build basically aeroplanes, you know, what goes in the cockpit, what flies the plane, and I'll show you some examples of the kind of complexities there are in these systems. So we'll go to the next slide. Okay, yeah. Okay, so on the left you see this is kind of our domain. I mean, we have, you can see we have cockpits, we have functions like flight controls there, engine control, flight management, which is basically conglomeration of many, many things, guidance to pilot on navigation cues, weather data, whole bunch of things, basically flight planning and those kind of things, helping in that. And there are lots of different kinds of sensors there are hundreds of sensors on the plane. These are very, very, jetliner today is an extremely complex system. And then, and then we have these different kinds of aircraft now, like your commercial airliner, and the new ones coming like small drones or air taxis if they ever take off, and so on. So you can see the goal. So there's an extremely high reliability requirements, as you can see. Like a probability of a catastrophic failure has to be less than 10 to the minus 9 catastrophic failures per hour. And so this is a very tall order. So of course, you cannot have train, as we have seen in previous talks yesterday, that this is such a rare thing that there is no data on it, not enough data to actually deal with this kind of a thing. And complexity, just look at the Boeing 787. So these were, of course, figures published from Wall Street, that the software development and certification on the Boeing 787 cost $30 billion and about 10 million lines of code, approximately. Because Boeing would not release the official figures, of course, so people estimate. And basically, also you've seen many incidents happening. There was a crash on the Potomac River. There have been many near misses and so on. So these are a couple of quotes from actually experienced people, from famous people, that the safety in avionics, aviation has been primarily forensic. What that means is that something goes wrong and you find out, okay, why it went wrong, and you go change your design or code or whatever to fix it. And there's many, many examples of that, including 737 MAX. And actually, 737 MAX actually talks to both the codes, that innovation is antithetical to reliability. So this was from Professor Avizinis way back when, that anytime you try to do a new thing, it's going to cause problems that you don't know, so unknown kind of thing. And so basically, the question is that a hallucinating, non-deterministic GenAI, how do we bring it to help in the system design, pieces of the system, maybe generate pieces of software or verification and so on. And basically, can we partition things? So I'll talk about that in the next slide. And then domain-specific approaches like foundation models. We have been hearing about that yesterday, and hopefully these become a reality in the future, more of an industry-wide acceptance, as many panels have talked about that. And then the other thing I think we want to talk about is, especially for the safety critical system, is combined formal methods-based verification with GenAI. That if you generate pieces of the system using GenAI, how can you formally verify those as much as possible? And okay, so the last thing is, can we use GenAI to improve the safety? Like, it's forensic, and new things cause more problems. Can we use GenAI to help predict those things rather than just be a forensic thing? So yesterday, so we're finding some commonality here with other talks, of course. So yesterday, Bhaskar showed insect, a beetle. So now there is a commonality of an insect in agriculture with aviation. How? So what happens is that this is the Australian mud wasp. And what they did, and this happened in Caribbean, but because of similar mud wasps. So basically, while the plane was parked at the gate, in an hour and a half, they built a nest in the pitot tubes. And And you know, you have probably heard about pitot tubes in the recent incidents and all that. So this is a little tube, which a hollow tube in the front, and its impact pressure of the air is calculating airspeed. And airspeed is very vital because airspeed, the lift in an aircraft is proportional to the square of the airspeed. So if you have to control it very, very precisely. So they built a nest, and one of the pitot tubes on one side of the pilot, which was pilot's side of the cockpit was feeding to. And so they got a wrong airspeed reading, and they thought the speed was too much, and they tried to decrease, and the plane crashed in the ocean and killed 150 people. So how do we predict those kind of things using GenAI in the future? You know? So here is one example of what you can do. So these are very complex systems, so they are built in layers. And I added a layer at the bottom called domain ontology, which is basically a general term to relate to the real world, including, it starts from physics, very basic physics. When you're writing software, depends upon what kind of software it is. Maybe you don't need a lot of physics because you're not doing finite element analysis, but you're not talking about the airframe, but you're writing software to do some control and voting and those kind of things. And then the next step of the ontology would be the terms like airspeed, altitude, attitude, which is the navigation parameters, what's lift, what are the surfaces, what the human-machine interface looks like. And the next step is then, which we see at the macro level, is the aircraft, the runway, the air traffic control, and environment. So these are very, very important. So this terminology is there. Currently, it's not explicit. It's been transferred via word of mouth and various documents you read and you find out. So, but then in the future, I think we want to basically make that standard and explicit. And then there is an architecture, and then you have OS and middleware, which does scheduling and I/O. What I was trying to show is what can we relegate to humans pieces and what we can relegate to GenAI. So the applications can be, some of them are very critical that you see in the middle. Some of them can be not very critical. They are different design assurance levels. So some pieces of the application, so it's very modular. So some pieces of the application don't impact catastrophic failure. They may just cause a minor annoyance to the pilot. No. And then they can turn it off, and they're not flight critical. So those kind of things maybe can be generated using GenAI, and the other things can be still done with the human experts, especially the lower levels. Because imagine you would not want Apple to create a new iOS using generated code from a LLM. Same thing. And then what GenAI can be used for is also in the verification, analysis, simulations, and verification, which we saw some examples of that yesterday. So one critical thing to point out is that when you are using GenAI to generate components within the system at the top, we want it to be very constrained and not like it's like AX plus B. You need to do that and nothing more and nothing else. Whereas when we are using GenAI for analysis, we want it to hallucinate and go as much out of distribution as possible. So they're very, very different kind of considerations in where you are using the GenAI, because we want to know for it to enumerate some possible scenarios on the right-hand side here, which could tell us about a potential failure mode. So one thing we are doing is, especially for the design part and the software development part, is in aerospace, and the certification guidelines that come from FAA and other agencies, the guidelines are how to develop software. So basically, you always start from a requirement specification. And then you show that the requirements are valid and they're the right ones. And then you show that your code you created adheres to the requirement. So what we are doing is, one thing we are doing is that on the left, you see natural language expressing requirements. On the right, you have let's say you have the code. Then there are good points and bad points on each side. In the interest of time, so we created a notation called clear, which is a formalized notation of English language. So we have English language phrases for describe all various kinds of behavior. So this is, we are talking about behaviors of the software as it looks at the modes, handles responses to events, and does control or provides an alert to the pilot or whatever. So that kind of software, what is the behavior? So they are very different behaviors than what you see in a general code, general software, because things are very time dependent. And they are time dependent responses that when this event occurs and another event occurs, and this event has occurred, and let's say something bad happened, and then nothing has been corrected for the next 5 seconds, then you create an alert, for example. So in the specification language also declarative, so you can specify each requirement independently so that they can be tested independently or reviewed independently. And once you do that, then we have tools that can generate code, or they can generate verification tests and all those kind of things. And basically, some of these tools use formal methods, like model checking and such at the bottom. So one of the things we did was that we created a GenAI-based front end to this clear so that a system engineer can sit down at his desk and describe some behavior in plain English, very informally. And we can create very formalized, clear requirements from that. And the way we do that is, of course, the LLMs have not been trained on our clear because they have been trained on C, C++, or whatever, or Java, right? So we created some RAG and context, and we are able to control, because clear is more like English. It's surprisingly well actually generates clear, even though the foundation model has not been trained on it. So there are some examples of how we do things. This is just, and this, of course, GenAI is being used in other places as well. So I will stop here.
Like the aviations. Okay, thank you, Devesh. And I guess when you said clear, for those of you who walk into the airport, have you seen the clear? They always want you to pay some money to get clear. I thought you were selling because you're in the aerospace industry. So you were doing something to do with it. But apparently it's not that, okay? So anyway, now we are going from hardware to kind of software issues in terms of verification and validation, which Devesh kind of pointed out, the importance of doing those kinds of things in this Gen AI world. And now our next speaker is going to be Chai Wen. Now he's going to kind of, again, he's going to do both hardware and software, I guess, in terms of where Gen AI is going to be used for. So again, as you see that there's a hardware aspects, there's a software aspects, and we're trying to touch both of them in various domains, the EDA domain, the electronics domain, the chip domain. Then we went to aerospace. Now I think we're coming back to the chip domain. Then we'll go into the mechanical domain or manufacturing.
Hey, thanks. Everyone, I started my PhD actually in computer engineering, specifically in EDA design. And we did a 1 year of study on a lot of space simulation, a lot of those tools, playing with those. And then when the AI the AI becomes popular, then my PhD advisor said, oh, the EDA community is pretty saturated nowadays. How about we start a new research called Evasion AI? So in my second year, I started doing all this AI stuff. And after many, many years, nowadays, I think test. I think after almost 10 years, I think we can probably see that now this generative, not generative, efficient AI, and a lot of people also doing that. And I'm starting looking back for EDA again, because nowadays there's a lot of national priority that we want to emphasize this semiconductor manufacturing stuff. And it's because of this like personal research experience, we aim for using generative AI specifically for the complex design. One specifically is the chip design. So that is the the story of my current research cluster, one is on efficient AI, one is using AI to solve to help the EDA community. So I put a figure here. We have done something. If you take a look at the top of those two figures, one thing is we want the AI to become better in terms of doing the image classification. This is the screenshot we took a few months ago. So nowadays, this is ImageNet, which is before the generative AI area. And nowadays, they can achieve very high accuracy, always outperform a human expert, right? On the second figure is we use the generative AI, specific natural language model, to solve mathematical reasoning problems. And we developed a framework called MACM that was published in last year, New IPS, and we developed a multi-agent language models that can reason on this mathematical, for example, linear algebra or some equation solving, and we can rank out top 3. I think at a certain point we even were top 1 when the Gemini came out, and we were pushed down a little bit. So we see that these actually are very promising. Nowadays, people can use this to, we call it agentic AI, to solve even more complex designs. So for example, we are using this agentic AI to solve the chip design problems. And then on the other side, we look at another pictures down there. Nowadays, the natural language models, they're getting bigger and bigger. We talk about the hundreds of billions of parameters. We need some computer system to host these models. So there are a lot of works going on. We were also developing some, for example, efficient with the model compression, such as the pruning, quantization. Quantization nowadays is even industry standard. If you're using NVIDIA packages, we're going to use that some quant, 4-bit, 8-bit floating point, something like that, to make the generative AI run efficient on the algorithm, on the hardware. But on our side, nowadays we also even getting involved with this. How do we even using one GPU to fine-tune natural language models? So some of our PhD students is actively developing that. On the other hand, is exactly the training efficiency. The training efficiency, I took a photo. This is our students' reproduced result for that paper. If you want to train a heavy workload, for example, video generation, we need to use many GPU classes and train many days. Then we can generate this video. It basically is a person eating noodles. And I guess I showed the same figure as what Sachin has already showed. The training has become also very expensive nowadays. And I even put a note in the bottom here. So that's the year in 2016. Professor Fifini, their group usually hosts this ImageNet challenge, right? There's a lot of top players. They become a millionaire later. In 2016, actually, they closed this challenge. They closed challenge in 2015. There was a GAN paper came out during the image generation. I think that's a personal perspective. I think in that year, we actually opened this generative AI era, because a lot of people are not just satisfied doing the image classification. We want to do the generation tasks. So this is the background of what this efficient generative, the motivation of that. Our group was in part of this process, and we developed many frameworks, including, I can mention the pruning, quantization, or even the mixed floating points, or even of some efficient numerical representation, such as power of 2 or mixed power of 2, that is customized for the hardware. And we also work on like GPUs, CPUs, FPGAs, or chip design, or even more emerging technologies, even like optical computing or superconducting devices in collaboration with Japanese universities. And another challenge we recently realized that, again, this is also our motivation, is the security issues. This also is the question by the organizer raised, how do we address this? Can we address these generative AI security issues? Some of our students in the early years, we actually test that. So nowadays, machine learning as a service is a quite popular standard. So you want access the machine learning models. You don't have the GPU, it's fine. We can use AWS. We can use Microsoft Azure to run the models over there. We can use our own data, and we keep our you can keep your data locally by using the federated learning mechanism. However, we find out that even if a third party, they do not directly have access to your local data, but then they just need to do some query, and eventually they will be able to reconstruct your training images or text. So this is something we have done, and we have some publication over there as well. A natural way is how do we protect this data and model? A natural way is we can add some crypto protocols such as FHE or MPC or TE, those techniques. And we were wondering how much overhead this kind of protocol will cost. You can take a look at this figure here. This figure shows that very counterintuitive in the plain text research. So, for example, we found out in the right loop, the nonlinear activation, it's very simple. Just need to compare with 0, right? Then, if we want to put a crypto protocol on top of that, this right loop, right now in the crypto domain, will dominate the whole process and cost hundreds of times of overhead. And later we have some research, how do we reduce this overhead, so which is also another trend of nowadays neural network is called a linear neural network or polynomial neural network. Basically, we want to reduce or get rid of all those nonlinear operations, and there's a trade-off to play with. You also have to maintain accuracy, but you also reduce the nonlinear operations. So this kind of neural network nowadays will be very popular in the security if we want to develop a secure neural network using those crypto protocol, or even, again, also I think it's a coincidence that in another, I just recently know that in another emerging computing domain, such as optical neural network or even superconducting, so those devices, they cannot support the nonlinear operations. They want us to reduce the nonlinearity of that. And nowadays, we have a pressure to work with those researchers to develop these physically informed neural networks. And another thing, I gave a 19 talk yesterday talking about that. This is actually on the how do we use generative AI for design a chip. So one of our panelists wonder what the generative AI design chip looks like. So this is the one chip layout designed by pure 100% of large language model. And we actually used, this is old technology. Skywater used to be a company in Minnesota, still in Minnesota, I believe. So we use their 130 technology, nanometer technology, and we use their PDK, and we use the open road, it's called open source software. And then we designed that. And yesterday I showed that we only need to provide a prompt. And then we have our internal framework or do the RTL generation. And then we link that to OpenRoad. We do the physical design. We do a lot of this principal routing optimization, DRC checking. And then eventually the agent will be able to optimize the design and then generate this thing for us. And this is, you can take a look at all these figures. So we use the AI to generate the core of the AI algorithm, such as we call historical array or CGRA, or even just a general matrix multiplication, which is the intensive and also the core operation inside of this generative AI stuff. And then I think this will become a future, this will become the closed loop that we use AI to generate AI, and that will assist us to use AI to generate AI in the future. Yeah, so that is concluding my talk.
Thank you, Chai-Ming. I presume that you're also generating all the software, but someone needs to test the software too, in terms of, there's a lot of code that you're generating using LLMs, and the code may or may not be a kind of accurate code. So that's an interesting problem on how to test this automatically. Okay, anyway, so that's the end of the discussions on the panels. And now, not the end on the panel, there's one more. So the design part of it was over. So now we are going into the manufacturing aspects of things. So now we are an expert on manufacturing. So that's are you ready?
Thank you, Ram. Thanks, Anant and Vipin, for inviting us to the panel. Can you all hear me? Okay. So one good thing about coming to the last is I can say that's all I wanted to say and sit down. Or I can take another. You said 1 hour, no? I have? So originally we didn't want to show any slides. Yesterday Ram suggested why don't you start showing some slides and say, so I apologize for a very busy slide. It was prepared for some other reasons, so I couldn't modify that. And one good thing for coming from a funding agency is I don't have to tell what research I am doing. All I have to tell what other people should be doing. So that makes my life easier. So let me see. So this is a slightly busy slide. Let me explain, then you'll understand. On the top, you can see what is the overall life cycle, starting like Ram said, small m and capital M, starting from the design and all the way to the supply chain. So you have a design and understand how GenAI can be used for making better designs, whether it is a product or electronic type or a product of electromechanical type or anything, even chemical for that. So once you have that product, and then how do I realize the product in a very efficient and effective way? So that's where product manufacturing comes into picture. So the 80-20 rule comes here. 80% of the decisions are taken during the design, and the 20% is going to affect the downstream. So for example, in battery manufacturing, the electrochemistry, what materials choices you have will dictate the downstream, what kind of roll-to-roll processing, what kind of metrology equipment you have. And we are talking about scaling. How do I scale this manufacturing to 100,000 to 100,000 units to millions of units? So from lab level to all the way to the commercialization level, that's what we are looking at. So one of the important thing of product realization is how effective are your manufacturing assets, whether it is the electronic VCAD, VLSI, and all the semiconductor manufacturing that you talked about today. But even some of the examples that we have done in chemical industry, food processing industries, cement manufacturing, everything has different type of process issues, whether you're using discrete manufacturing, assembly-centric manufacturing, or continuous manufacturing in terms of chemical industry, or in food processing, which is batch processing. So you have to have the same level of complexity. So the centerpiece of that is cyber-physical system, and then how those cyber-physical systems have to be designed with all the design principles. So controllability, observability, cybersecurity, reachability, availability, all those entities have to be built into that, not as an afterthought. So this is where I think some of this GenAI can help to understand the systems engineering from in a different perspective. Okay, so in systems engineering we have physics, which was driving us, but when we are talking about as designed, as manufactured, as performing, has to be connected well, that's where I think some of this AI and GenAI would help. So what are the enabling technologies? We talked quite a bit about AI, machine learning, and all that. And also we have digital thread. I think today somebody talked about standards required in terms of how do you exchange the data. In my previous life, I worked on standards quite a bit. So standards and standard formats, ontologies plays a very important role. And digital twin is one of the important things that we have been talking about in terms of how do I connect the physical and digital. So it's more different from modeling and simulation that we are all familiar with. The MS&A is mostly a static model, whereas in digital twin is a dynamic model. So then the software systems that we are providing, those days are over. We don't want a monolithic software system. We are all now talking about apps and orchestration, Dockers and whatnot. So how do I make sure that these systems are built in a modular way that we can plug and play? So in fact, one of the DOE-funded institute that I manage is Smart Manufacturing Institute. If you go to sesame.org, you can go to their marketplace. All the apps that they have developed for manufacturing, whether it is cement or anything, they put that as an app in the marketplace, something like a Play Store. So we can download it and orchestrate it and then use it. So that's where I think we are going in terms of. On the right side, you can see starting from ISA 95 model to connect, everything is connected to everything else. So now when you are talking about hyper connectivity of manufacturing systems, so how do I make sure that the hierarchy that we talked about, the Internet of Things at the bottom to all the way to the business processes. So digital transformation of manufacturing is not just simply about transforming your design, manufacturing, and equipment and supply chain, but you have to also do the transformation of your business processes. So how does that come into picture? So you can see that how we are going, not only the forward problem, AI and GenAI, we want the inverse problem. So give you an example, in battery manufacturing for a given performance metric, what kind of material choices you have, what kind of variability you can tolerate across the entire production. So these are kind of inverse problem we are trying to solve in manufacturing. We did a project on cement. Cement is a very old technology, not much of new technology has come into picture, and is one of the biggest material, largest material that we use for in the world, not just for the construction, it's that the biggest one that we use. But it has a very highly energy intense manufacturing process called calcination process. And there the technology is very old. We kind of try to understand what kind of feasibility there for predicting what is the quality of your clinker before the clinker comes out. So these are the kind of technology that we have used in the AI. There we are mostly used to predictive capabilities, and also what kind of rheological model that we have, physics-based model combined with them to understand that, okay, predicting is fine, but then how do you make sure that the clinker is coming to the quality that you want? Then you need to have the feedback control. So that's what controllability, observability. So one of the biggest questions that we have trying to solve is, just because we can put sensors and collecting data, is the system is enough information in the observed? So this is one of the things that observability that we need to understand, whether just because you can get the data, is the system is providing enough information from the observation to understand the internal of the system. So that's one of the biggest open problem, I think, still. So the second topic is digital twin. So I think, Ganesh, you talked about digital twin quite a bit today. In fact, we are working with NITRD to develop a national plan for digital twin. So I had a workshop last November about digital twin for manufacturing especially. So you can see that picture there, it is the bidirectional connection, okay? So what do you mean by bidirectional connection? What is the latency here? What is the wired and wireless connection that you want? What kind of fidelity you need? What do you mean by cybersecurity there? You know, if you're going to sell a GE engine, they also want to sell a GE digital twin of that engine. So how do you make sure that the cybersecurity comes? So you have ethics, safety, and if you're going to throw AI into that, then you have a much more complex problem in terms of life cycle of the digital twin itself. How do I design the digital twin? How do I maintain it? How do I retire it? So similar to what physical asset has to be done, we are going to have a life cycle issues there. So before we jumped into digital twin, what I did was I used, like, many of you are familiar with the Zachman framework. So the Zachman framework is basically goes into what, why, how, where, when, and things like that. And then it does the reification of each layer. So I just did one extraction of that here. What is the digital twin? Why is it required? What is the motivation? What is about data? How is about process? Where is about supply chain? Who is about people? So you can see that connection that each of that has to happen, and how GenAI and AI will help. In fact, Department of Energy have something called EnerGPT, which is used internally for us. So the other thing that we are looking at in manufacturing is we spend a lot of time and effort in improving the productivity, cost, quality, throughput, the usual KPIs. But the problem with that is, if you don't connect it to the demand of what these products are, then you don't know whether you're not actually making the effectiveness of this whole thing. So I'll give you an example. If I am a small shop which I'm producing, say, cupcakes, and I'm producing 100 of them every day, and suddenly I say I want to produce 150, And I tell my people, say that, do you have the sugar, do you have this, do you have the supply chain, do you have the equipment, etc. They say, yeah, we can do it. And they did that, and then the next day I produced 150. Is it the productivity? Unless I can sell the remaining 50 also. If not, then what do I do with that 50? So this is where the traditional make to stock, make to inventory versus make to order. Make to order is a dynamic scheduling. So what they call is lot size of 1. Can I produce a lot size of 1, still make profit? So the demand connection is very, very critical. I did some work on this recently to look at what are the macroeconomic issues, what are the microeconomic issues, why those two things are not connected. And here is a challenge. I think there is a tremendous opportunity to connect the supply and demand, and then it goes back to macroeconomics and microeconomic issues. So that's one of the things that I think there is an opportunity here if you want to use AI and GenAI. This is not well connected yet. And the majority of the manufacturing is make to inventory versus make to order. But make to order is very tough because a lot of issue because of the demand volatility and all that. But there should be a combination of these two. I think if you want to have a domestic manufacturing innovation ecosystem, we need to connect this very well. Otherwise, in fact, I have a project with 4 of the national labs, what we call battery accelerator program. So just because I have a very good electrochemistry, that doesn't mean I have a good battery. The battery is only when you are able to produce 100,000 cells, and then the variability of those cells are, and one of the biggest tests in battery technology is they take a nail and nail it, and if it explodes, you are done. That battery is gone. That technology cannot be supported. So this is where I think the variability issue of not just the material science, material choices, material substitution, manufacturing, production operation, roll-to-roll processing, metrology equipment, AI, all that are great unless you connect it, whether you can scale it. If the scaling has to be done, there should be a demand. So that's what we are looking at. In fact, this is not talking about cell level. Battery that we are all using is not at the cell level, it is at the battery package level, pack level, okay? So that's much more complex problem. So that the variability analysis of that is extremely complex. So anyway, so I'll stop here.
Thank you, Susan. And thank you, Susan, for all those insights. I mean, he said a lot of things that needs to be observed. But if you look at the overall panel, there is one of the insights that one could get here is that you have both the neuro-symbolic kind of reasoning and also physics-infused kind of things, because you have to have physical knowledge into the system. Not only your neural networks people are talking about, not only the symbolic reasoning like ontologies, which Devesh mentioned, but you also have to have the physics incorporated into this. And in addition to all these things, Sudarshan says there's one more layer over that, which is this demand layer kind of thing. You don't want to produce things which there is no demand for, and you cannot measure your productivity without taking the demand into account. So there's a lot of factors which go into this, and GenAI is going to play a role in several stages of this whole design, manufacture, supply chain, and business process as such. And you've seen some glimpses of that in this particular panel. And I kind of, then again, thanks both the panelists and you all for listening to it. And if you have some questions, quick questions we can answer. I don't know what the time problem around here is. Okay, 10 minutes is what we have, and then you can ask specific questions if you have. And then we have addressed a set of questions in the beginning, and I'm just going to go back to that. I don't know whether we have addressed everything or not, but at least I asked the panelists to pick their favorite ones and go ahead with it. Let me see if I have the. I don't know what happened.
Yeah, maybe I can go.
You see the questions here or no? You're not seeing the questions.
Yeah, can I go ahead and ask one?
Okay, you can go and ask the questions.
Yeah, thanks to the panelists. I think because another perspective of the workshop is how can some of the domain sciences innovate new advances in machine learning. And one perspective, just to elaborate a bit, and on advances in machine learning, alternate history of machine learning is also easy availability of data and benchmarks. So ImageNet leading to AlexNet, machine translation leading to invention of transformers, and lots of other. I have been very inspired by Sachin and his student Vidya's work in electronic design automation, trying to make open source data sets and computations work, or at least get started with it. So I'm very curious to hear from him and other panelists about how can we make that aspect where machine learning researcher or the broader community is very interested in working on a problem, like a PDB, which led to AlphaFold or Rosetta Fold in EDA, and we can design new things.
Well, thanks for the question. So I can talk about a few experiences that we've had. The biggest constraint in at least our domain has been confidentiality and the inability to disclose pretty much anything. So some of the work that we did, for example, was generating artificial synthetic data sets. And these are synthetic but realistic data sets. And I'll give you a specific thing. So one of the big problems is when you build a chip and it takes, say, a few hundred watts or whatever, then you need to make sure that your losses in supplying that power are not very large. Now, in order to sort of test a new algorithm for this, whether it's conventional or AI or whatever, you need a good data set and you need an extensive data set. The only data set that was available for forever was one from 2008, which had sort of one current pattern, and the whole community was working on that. So basically what we did was we used GANs at the time, but you could just as well use diffusion models today, and you could probably get finer granularity with that to generate these sort of synthetic but realistic data sets. Now, even for this, you still need an underlying data set on which you can train the model. So this is where having good students and innovative students is helpful. So what they did was they looked at what could look like a chip. And it looks like, well, chips are manufactured with sort of rectangular blocks. All the wiring is in the X and Y direction. There are very few diagonal wires except on the PCB. But on a chip, there aren't any. So they figured, well, I mean, if you look at most US cities, they're laid out in a grid pattern. And so they said, well, we'll look at Google Maps. We'll filter out a bunch of maps. And they did the hard work of taking out rivers and filtering all that out. And they said, well, OK, a warehouse is a chip design block. A highway is a bus that connects multiple blocks. And then there are relatively few hotspots. So in an urban landscape, there are very few trees. Those turned out to be the hotspots that draw the most power. And they used that to build the equivalent of a foundation model. And then they trained it on a sparse data set. So that's sort of a small contribution from what we did, not knowing as much about GenAI or AI as you guys do. But then the idea is that something like that could be a trigger. Where do you how do you make up for the paucity of data sets? This is not just a problem for us. This is a problem even, for example, in medical AI, because you're still bound by confidentiality. Maybe different constraints, but still the same idea.
Yeah, thank you, Sachin. I think, Vipin, I guess you mentioned about that AI plan, which came out from White House recently. And in fact, part of that plan is to produce these data sets. And I guess in the afternoon, maybe Nikunj is going to talk a little bit about there's one of the things that mentioned in that plan is about a NITR-D AI strategic plan was mentioned in the president's plan that they put out. And one of the things there is the data sets is going to play a major role in terms of how do you have the standardized data sets so people can use that for machine learning, and what's the role of the government in that process. So we're going to address that at some point. Okay.
So can I make a quick point on that?
Yeah, go ahead.
So as part of the National Plan for Smart Manufacturing, we were asked to develop a report with the national academies. So I had an opportunity to lead that effort. One of the chapters is about the data commons, and what they came out with an idea of data highway. So we talk about data for manufacturing, and you talked about confidentiality. And so I give you a couple of examples. One institute I mentioned is smart manufacturing. The other one that I manage is cybersecurity for manufacturing. these two go hand in hand. What we did was we worked with these companies to sign NDAs and all the stuff, and then the manufacturing data that, for example, General Mills and all the company that we worked with, once they saw the value that it is actually improving their performance and things, and they said, we don't care anymore. We want to share the data. And they want to show that they are the champions of using this kind of technology to improve their performance. In fact, I had a project with Honeywell. The Honeywell project was the landing gear. They have to infuse much more carbon into that for strengthness and all that. So they use vapor deposition and all that. That technology is very proprietary to them, as you know. So, but once they saw the value of this, they said, we want to share this data, but make sure that all the IPs and everything goes back to Honeywell. And then cross-licensing of this technology. I think this public-private partnership of those kind of ideas that I worked with those companies is helping them. So if you go and ask them to give data, nobody's going to give you data. But if you tell them here is the value of that, then they understand and then give that. But asking them to give a data, immediately they think that it is going to expose them for something, or maybe some intellectual property theft and things. But if you tell them this is how it is going to add value, this is how it is going to be handled, this is the data governance plan for that, it will be used only for the purpose that we said we will use, not for any other purpose. So we put all that data management plan and everything, and it really works well the moment they understand that it is actually increasing a value proposition for them. Okay. So unless until you tell them, you cannot just knock at their door and tell that, give me data. That's not going to happen because they don't even know what you want, first of all. What use manufacturing data means. I can put a sensor and give you terabytes of data. Every second I can collect the data and give it to you. So that doesn't make any sense. So.
Thank you, Susan. I think the report that you are mentioning is available on the web, I guess. That's what I presume.
On the web, you can go and look at the app, but the data, if you want to get, you have to talk to them, okay. You have to sign an NDA and all that, and then they'll give you everything you want, actually.
Okay, thank you. I think there's a couple of questions. Quick questions are.
It was great. So I recently heard, I guess in the last talk, mention of standards, and then the moderator comment, mention of standards. And in the present era, I am wondering, the group thinking about the investment, how much you would want community-provided data sets to go into converging on standards versus are we at a moment with what GenAI can do, in particular, kind of doing a lot more raw to useful translation for us where we can invest less in converging on standards or in getting those contributions to align with an existing standard, and more on making sure we've got higher volumes of more relevant data, annotated plain language or however it may be, in what form it comes more raw from the community, if that's a more worthwhile investment in these times of kind of, in some cases, scarcer funding for data building and publishing.
Yeah, you want to answer that, Susan? Or?
Tell you, mainly because I lived in NIST for some time, and when I work at DOE also I continue to do that. So standards are of two types. One is what is the content, what is the information that is going in that. For example, if you're sending a product information, what is the assembly, what is geometry, what is the CAD model, etc., etc. And then what communication protocol that you're sending, what is the handshake that happens with the standard. So that particular standard, in fact, most of the work that SIMANI, which is the Cybersecurity Institute, and also the SESME, we use OPC UA standard, which has a meta language, meta information model about how do you describe your system, how do you describe your sub-assemblies, etc., etc. So that's where the ontology comes. How do you do that? In terms of standards and protocols, US used to be a leader in that, in terms of all these ISO technical committees and things. but not much now, at least to my understanding. But that's very important because people don't understand standard is not just a document, it is in a commerce. That's why it is in the Department of Commerce. I just want to ask, this is a university, how many courses teach standard as part of the course curriculum? For example, ASME Y14.5 GD&T standard, which is the mechanical tolerances standard, or whether it is OPC UA or any other standard. So that is one of the issue. I mean, if you go to industry and I ask them, many students are not aware of the standards, which are very, very critical for industry. I think that needs to be added. And the second important thing is, so far, I haven't seen at least what is the best practice of developing an AI model for manufacturing. So how do I generate data? Which data I need to generate? Why that data is important? What is the physics of that? How do I do the data pre-processing, post-processing? How do I send it to machine learning and get the data? No general standard step-by-step best practice has not been developed. So everybody is trying their own way, everybody is getting their own model, it's not repeatable, it's not generalizable. So that's where we are now, currently. So one is all these models, GenAI and all that, we get excited. But in terms of the real manufacturing in industry and things, we need to have those very rigor standard best practice for applying AI and machine learning.
Yeah, and also continuing on that a little bit is that if you look at the President's Action Plan, which Vipin showed, they explicitly mentioned an institute at NIST called CAISI. So just Google that and see. It's a Center for AI Standards Innovation, and you'll see more action from there in the future. I think that's very pertinent to the question that you just asked. Okay. So anything else? I think we're almost the time. So I leave it to the organizers to, because it's almost 11 o'clock. Okay. Thank you then. Thank you all.
Fantastic talks, fantastic questions, panels. Let's just take a 3-minute quick break for the bathroom, and maybe Sapna, you could set up your panel.
I don't see Vipin around, so. And I'm pretty sure it's past 3 minutes of the break. All right. Good morning, everyone. You have the last panel for this morning, and we stand in the way for your lunch, so we'll try to stay on time. This panel is focused on materials, and it worked for a flicker of a second, and now it doesn't want to work again. So. Okay. I'm not sure why it keeps doing that, but all right. So I thought I'll give a quick overview of sort of just what we think when we think materials, and we've seen flavors of this keep coming up all through the workshop. But I also wanted to sort of highlight why when we think about materials and we're trying to think about modeling materials, whether it's actually physical modeling or through AI, we run into challenges, right? So I asked ChatGPT to make me a collage of materials, made pretty a boring one, so I said make it an interesting one, and then that's all it could do. I still didn't like it, so I went, searched, and found a better picture for materials. The display does not want to cooperate today. No, it's the display that's the problem.
Oh, is it the, oh.
Yeah, because it keeps going out. It's yeah, but it keeps going out. The minute I talk, it'll stop going. Right, and it keeps timing out, like, right? So like it starts off and then now it's going to disappear off in a bit. Don't know. We can try. I don't know if it's the adapter. We tried a couple, but yeah, sure, let's try that. Yep. Yeah, let's try that.
Maybe put directly onto this thing. You can connect. When I connected this directly into this.
Let's try it.
And then put return.
Sure. Okay. Let's hope that saves the day. All right. So then I went and grabbed this picture. This is sort of the picture which came with the news of Google and quantum AI, quantum computing, right? So when you look at this picture, everything that you see here is essentially materials, right? From this chip that we're using, and we heard a lot about chip design and what it comprises, including sort of the material design for it, and we'll probably hear a little bit more in the panel. And then whether you're thinking of this light here, these wires here, or this packaging, right? This is a cardboard, this is probably a steel packaging. No matter what you're thinking about, including the clothes they're wearing, it's all materials. And we want to design all of these materials with different properties. I don't want my clothes to be as stiff as this material, right? And so that's kind of the aspect of materials that we're always trying to optimize for and trying to achieve. So if you look at a word cloud, okay, so again, I use ChatGPT for this, so you can see I have a lot of fun with ChatGPT. I said, create a word cloud of materials, and it did. And you can see it shows a very broad range of materials, from thinking about ceramics to alloys to superconductors, semiconductors, which we typically would call hard materials. They're like solid crystalline. But there's also lots of soft materials, which would be the squishy materials, like hydrogels, amorphous polymers, or some other bio-inspired crystals, biomaterials, etc. Right? So they have a very broad variety of materials, but with that comes the challenge of properties, right? So now if I look at a word cloud of the number of properties these materials can have and we want to try and optimize, it's even more crowded from everywhere, from getting its hardness, softness, thermal conductivity, glass transition, expansion, specific heat capacity, viscosity, etc. We want to be able to optimize for all of this. And it's so many properties that if you look closely, even ChatGPT got super confused. So you can see that this is actually not a word. It took a couple of properties and pasted over itself. It's kind of struggling here, kind of struggling here. It took it 3 tries to even get up to this, right? So it is that complicated a problem. And I like that ChatGPT allowed me to illustrate that.
I'll give you another example, because in general, in this crowd, we've thought about what we refer to as hard materials. Let's think about another aspect of maybe soft materials, showing you sort of a refrigerator of all kinds of biologics. So these are basically drugs, except they're not, powdered or solid. They're liquid formulations with something biology focused, and we'll hear about that in the next talk as well, right? So there's a protein or an antibody or a virus in there, such as for vaccinations, which we used to believe in. And if you zoom into it, this is essentially what it looks like, and this is essentially the kind of thing you saw when you went in to get your vaccination for COVID, right? And this has to be injectable, it has to be stable. And during COVID, we learned that you had to store them at really, really cold temperatures, and if you didn't do that, then you can't use it, and these vaccines are expensive, right? And this is true for lots of biologics. Because they can be unstable, you have to design what is called formulation. And you can think about it as a mixture of stuff that helps stabilize these. But what does that mixture look like? We don't actually know. In industry, they do a trial and error process. It's a very expensive process. Something works, we keep it. But even with that, we still need very many cold storage, right? Which is a big challenge. And so, of course, there's a lot of effort in trying to figure it out, but the challenge becomes the design space. I can have all kinds of sugar molecules, all kind of salts, all kind of various types of molecules which I can mix in different concentrations, and I could find maybe a formulation. So it's almost like saying, here is the spice rack, now try and find the best recipe, right? Which basically is an infinite search space. And so it's these kind of problems that we could probably solve through machine learning, but the challenge is that it includes a large scale of problems, right? So even if I take like the key ingredient, the biologic molecule that's involved, that I can break into many, many interactions and scales. So from very basic interactions, we all know oil separates from water. That's essentially what makes proteins fold, and this is why our body operates the way it operates. Two, more complicated, right? Then you can add some other types of interactions. You can add some structures. You can add a more complicated structure. This is what protein is, and this is essentially what AlphaFold and Rosetta Fold can detect or can predict, but they only predict the structure. But now a lot of these proteins come to form assemblies, and this is essentially the big working horse in your body, which both of those tools cannot do very well right now, right? And now all of this, we've thought about just structure, but in reality, what is important is not just the structure, but the dynamics. So here I'm showing you sort of a virus capsid that's falling apart, and this is similar to your vaccines that we use, right? And understanding how it falls apart is a lot more important than just knowing the structure. That's the easy part. And so this is what it makes these kind of systems, these things of materials really hard, and this aspect of going from structure to property really difficult. Because we are doing a lot of physics. We heard about this in the last session as well. We are going many scales, but we also have to think about dynamics, both at the very small scales, the microscopic, nanoscopic scales, but also, again, we heard about this yesterday, or earlier this session, is when the process conditions change, your material will change, right? So we also need to account for those kind of things here, and this is at least my perspective of why I think doing materials modeling and then also incorporating AI into it has consistently been a challenge. And also is a land of opportunities. Okay, with that sort of introduction, I'll introduce the panel. So you've already heard from me. I'm an associate professor in the Department of Chemistry, and some of the protein stuff that I showed you is the kind of research that I do in my lab. That simply means that they agree with my philosophy. That's the sign from the superpowers. Okay. And I'm trained as a chemical engineer, so I think, but I do my research on the molecular side, so I like to think all the way from molecular to processes, and that's why this formulation design is one of the projects that we do in our lab, which I'm super excited about. But we basically try to study a lot of this on computers, so we do computer simulations of these systems. So those are the kind of materials we work with. And I also told the members of my panel that, answer these questions in your introduction, so I'll do it really quick, and then I'll pass it on to Arnab. The scale, I tend to look at the microscopic, nanoscopic scales, but I do collaborate a lot with my wet lab experiments, and really we try to ask. There's something about sound effects in me today, okay. First it was the screen, now it's the sound effect. At least you will all remember me, if not for anything else, right? And so we try and really bridge these scales and ask, how do we combine all these different data sources to really get to the objective that we want to get at? I think GenAI has been really interesting and amazing in my field, and my field is very, very directly related to things that AlphaFold and RosettaFold did, so it was very exciting to see that. I will also go ahead and argue that the true Nobel Prize winners should have been the ones who thought about setting up and supporting PDB data bank. Without that, none of the other things would have been possible, right? But I do think one of the main limitations is this aspect of being able to capture the dynamics. That is still very limited. And in sort of our fields, we want to do the dynamics and the structure in context of the environment. And that is still, I think, a challenge for AI in general, but it's also a challenge to capture effectively in physical models. So it's no surprise that even AI struggles on that front. Okay, with that, Arnab.
Thank you so much.
Thank you.
Thank you so much for that wonderful introduction. And this word cloud is actually a great way to actually capture the complexity of the problem that we are looking at, but also it's such a combinatorial optimization problem that we are dealing with in materials, and that it's very easy to lose your way. And that's basically where I am coming from as well is, so by the way, my name is Arnab Banerjee, and I am a faculty in the Department of Physics and Astronomy at Purdue University. And I consider myself an expert in applied quantum materials. And to give a little bit of my background, I had been working with a lot of quantum materials. My journey started with biomaterials and lipid-protein interactions, by the way. And then I went into quantum materials because I thought that this is one frontier we really need to solve, because we can't really keep on making quantum our enemy and to say that, look, we have quantum effects, and so we need to avoid it, as we do many a times I have been talking to my semiconductor friends. We really need to make it our friend, because then that actually opens a very new frontier. And that is where I think that AI is really going to help. And so what I started working on is a lot of semiconductor materials. I have been working on metal insulator transitions and how to make that better, and looking at the critical scaling laws, and to see where is quantum properties really expressed and where you still have a classical explanation of the problem. What is really quantum? What is really classical? And then I started working on a problem of something called quantum spin liquids, which basically is a very new state of matter. By the way, you can get several new states of matter when you get into quantum territory. Microsoft came up with one, by the way. And these new states of matters have certain very new properties which you cannot get in normal classical materials or in normal semiconductor materials. And I have been working on quite a few semiconductors doing actual experiments. I do neutron scattering experiments down to low temperature and high fields, transport experiments, both thermal transport and electrical transport down to low temperature and high fields. And I make some of these materials myself, both in the clean rooms of Purdue, but also I make some of them in my lab with the goal to understand that what could be a supply chain from kind of a cradle to grave that we can make with this material space. While at Purdue, so I was a postdoc at Oak Ridge National Lab working on neutron scattering and data analysis, and then I was a scientist there working both in neutron scattering, but also I had a joint appointment at the Quantum Computing Institute at Oak Ridge National Lab. which actually really helped us bring this problem that, okay, if we want to really harness the benefits of quantum materials, we really need to first understand the quantum materials. And the best way to understand a quantum materials is using a quantum computer, which was Feynman's original dream. Are we there? Or if we are not, why are we not there? And where do we start? And secondly, what can we use these quantum materials for? Can we make them new types of ultra-sensitive sensors or new types of quantum memory, quantum computers, or new types of quantum communication channels that we can really make? And those are the problems that really faced us, and it was soon very apparent to us, and which is what I brought into Purdue when I became a faculty there, is that we need to create a quantum digital twin of the material. So we have the quantum material, and we get real data in quantum materials, and unless we have a quantum digital twin that resides in this AI space, cloud space, and in the computational space, then we cannot really predict what we are gonna do next. And that is where I think that we need a marriage of two techniques, one of them being quantum computing as it comes into maturity, and the other is, of course, AI. And I can probably talk later about what are the AI cases, but that's what my introduction is. Thank you.
Nathan?
So I'm Nathan Smansky. I'm a postdoc here at University of Minnesota in the Chemical Engineering Department and also an incoming assistant professor at UCLA in the Material Science Department. My work is primarily on, as far as types of materials go, bulk inorganic crystalline materials. So inorganic, typically these don't contain carbon. I look at a lot of oxides, phosphates, sulfates. Crystalline just means, you know, you have some very small unit cell consisting of, say, 10 or 20 atoms bonded to each other in different ways, and these small unit cells repeat many, many times in all three dimensions to give you this periodic crystal. As far as how we look at these materials, I'm primarily a computational researcher, so we use quantum chemistry calculations, mostly density functional theory, some machine learning, to really try to look at the smallest of scales. So at the atomistic scale, how does the types of elements that are in your crystal and the way that they're arranged give rise to properties that we can actually observe macroscopically? And application-wise, we look at a lot of energy applications, so lithium-ion batteries, thinking about how we can design better cathodes, better electrolytes, to try and give you a battery that can get to higher energy density, better cycle lifetime, and so on. I would say generative AI has definitely been, you know, picking up quite a bit in our area of these bulk crystalline materials. I would say like the past year, it seems like every week there's a new generative model with the goal of basically doing what we do, of materials design, but much faster. So the idea is you have some model, you say, hey, I want some material that satisfies these properties. Maybe it's a better battery cathode. And then it will suggest to you some crystal structure and some composition, which you then have to verify somehow, whether it's with more rigorous calculations or ideally with experiment. And there has been some success in these areas. There's a big Nature paper that came out, I think like last year, a few months ago, where they used GenAI to propose these types of materials, and they did actually find that they could synthesize at least one of them. So you have one success. So that's showing you that the GenAI for these bulk crystals is learning something and that it can generate a real material that you can then make. I think the biggest limitation, which we were asked about, is that yes, you can make it, but does it have the properties that you want for the application that you care about? So for example, in that paper, that Nature paper I mentioned, they looked at very simple properties like band gap and bulk modulus. These are things that are relatively cheap to compute, and because of that, there's lots and lots of training data out there that we can then feed into these GenAI models. But in reality, if you're operating a battery, there's much, much more complicated properties that dictate the performance of that battery, such as the dynamics of the system over time, that there just really isn't enough training data out there for. And so I think that's where, in my opinion, the biggest limitation lies with these generative AI models for crystalline materials. So maybe we can discuss that a bit later on more.
Kaichi?
Thank you for the great introduction on the quantum material and molecular science. And I view this panel is about multi-scale material and how to bridge different scale together. So first of all, I'm Kaichi from civil engineering. So I consider myself a very conventional material modeler, although it's very classical mechanics field compared to the next generation quantum computing is a little bit old date, but I'm assure you there is still a lot of unresolved problem in our field. And first of all, I would like to talk about a little bit about my research. My goal is try to develop the numerical methods such as finite elements method. Of course, in our group, we also try to do the hybrid strategy, combine machine learning AI into this numerical solver. But the goal is to predict the mechanics, the mechanical, thermal, and multi-scale response of a material in the large structure. In the larger structure, particular in extreme deformation that lead the material damage and failure. That's what I'm doing. So I will consider. In mathematical term, we call it a homogenization. We upscale the knowledge from the quantum mechanics or the molecular dynamics, but still, we know that there is a so-called emergent phenomenon. So once you put that material upscale to a real-world complexity and under complex environmental condition, new complexity emerge. So we still a lot of things to deal with there. In our group, we focus on heterogeneous porous media and composite. It seems a lot, but actually they share a common features. They have microstructures. And let me just introduce a little bit. Porous media is like a widely used to describe the geological materials such as soil or rock. And you can imagine there are some pore inside, so the fluid go inside. So you need to deal with the fluid. And if under some freezing condition, it expand, become ice, then you have the phase change. And also you deal with the fluid structure interaction, something like that. And composite is I mainly deal with composite in my PhD. I work on biological tissue, which consider the human muscle is like a reinforced composite. We have a strong material like a muscle fiber, and we have a soft material, extra cellular matrix. So we consider like that through the high fidelity simulation, we can use that to investigate a lot of interesting phenomena like how human aging really affect the force generation, the force in our muscle. Why people age, then we lost our capacity of generate the force, something like that. So overall, we believe, understand this microstructure, for example, the arrangement of this microstructure or the morphology, and also the individual properties essential for predicting the upscale property of the material. So a key motivation for our work is to develop a digital twin. This is our long-term goal for this materials system, such that we can accommodate different applied condition. So we believe this can support like a forecasting of a natural hazard, understand how the geomaterial, how it behaves under different conditions, and also enhance, even including the manufacturing, like the metallic manufacturing, you need to understand how really the phase change in the micro scale, but you cannot go in too deep scale due to the computational cost. So you need to sacrifice some accuracy, but live into certain level that you can do a high fidelity simulation while it's still feasible. And also design the resilient structure, which is back to my department critical need. So, speaking of digital twin, actually in our community, in the computational mechanics community, we have our first digital twin conference called Mechanics machine learning for physics and mechanical science in 2021 in San Diego. And actually next month in UT Austin, we have artificial intelligence and digital twin for earth science. So as you can see, the AI, this digital twin has been more and more popular in our engineering science domain. The second question is regarding the scale. So actually our engineering work on different scale as long as the so-called continuum assumption is still valid, which means the we assume the microscopic fluctuation must not cause significant variation in the average quantity. As long as this is satisfied, then we can work on. So from this mixed scale or mesoscale problem to larger scale problem, we want to create a unified model how to simulate that. Okay, and so in our field, the generative AI is by far, based on what I know, is still primarily applied to generative realistic microstructure. For example, the rock sample, people will a lot of using on that. So there are some work from some of colleagues in Columbia and Rutgers University to generate some rock sample and use on the like a freezing, thermal freezing application. And also our group, I use generative AI technique for doing the constitutive modeling of the biological tissue. That is some of our work before. So recently, I want to mention there is one intrinsic limitation. I believe is about the thermodynamic consistency in our field, because our field usually work on so-called high consequence events. So the accuracy, not just the accuracy, the stability of the output from the model is more important than purely design, because we want to make sure the final outcome after long-term dynamic simulation, the result is reliable. Motivated by that, our group is mainly focused on how to strongly enforce the physics understanding in the machine learning pipeline. Or more specifically, we try to don't sacrifice too much accuracy that already well established in our field, like a finite element model. We want to strongly certify that, how to encode the AI back to our numerical solver, discretization solver. And in terms of the opportunity, I view the generative AI, there is one great potential is in handle the curse of dimensionality. So, and actually most of my work is based on that, how to reduce the dimension of a parameter space such that because it's naturally related to the Bayesian idea, so you can give a really physically realistic sample. Compared to PCA, we recently have a work compared to PCA and compared to the VAE, we realized the diffusion model actually is really give a much better accuracy. So we feel quite encouraged of that. And in the long term, the great limitation I just mentioned is about the nature of our field is a high consequence event. So I believe we need to understand better about the uncertainty that inherit from the model. So this is very important. Traditionally in finite element, we really care about the conversion. Why we care the conversion? Because we believe as you refine the model, you can get better accuracy toward the ground truth. But whether generative AI can provide this property, when you increase the data, you really can train the model that make sure the accuracy is monotonically increased and the stability is still guaranteed under a threshold. So this is some unknown. So I believe this is one thing our field really want to help to also push this aspect. And yeah, so I think that's what I would stop here. Thank you.
Right, thank you. I suspect you'll see the theme of it being physically aware, being physically consistent, being able to have uncertainty quantification, and then it actually being realistic, like Nathan mentioned, synthesizable, or like Kaichi mentioned, it should be stable, right? Will keep reoccurring whenever we think of materials and trying to design new materials. So we have a series of about 5 questions that I'd shared with the panelists sort of to give our thoughts on it, but now that we have maybe about 30 minutes remaining, I'm thinking we'll spend another 15, 20 minutes talking about those questions as much as we can, and then we'll open up the floor for any discussions. And we'll get through as many questions as we can. If we don't, it's fine, right? So this is I think it's almost like a trick question, right? The first question is, what are the typical design goals in your field of material science, such as multi-property, multi-fidelity optimization, constraint discovery, diverse batch generation, and how can GenAI approaches support them? So who wants to go first?
Okay, I will start. So I think that there is a whole flowchart in which the field has to work, which is that one has to make the material, which has touched upon that it has to be makeable. And then when we make the material, there is the purity issue and how does the properties change along with the purity, and it's a continuous variable. I mean, you can get different properties for different purities and phase transitions. There is and when you make this material, especially hard materials, we actually look at binary alloy phase diagram, and to look at the electronic properties, we have to look at the DFT. So all of that kind of inputs into what is really makeable, and when you make it, what is the band structure that you have. And that is already a tough problem. As you know, that there is a lot of DFT AI tools which are being discussed right now, which are coming up. And then there is exactly what is synthesizable is, and at what temperature would you cook the material? And when you cook the material, exactly what is the band gap that you get, whether that's a direct or an indirect band gap, and can AI help there? But then there is this AI for data analysis. And for example, I deal with neutron and X-ray data. And neutron data, when you take the data set, you get like terabytes of data at a time. And it takes a graduate student, or even me, 6 months to basically figure out, okay, which is coming from phonons, what is coming from magnons, what is coming from spinons, what is a quantum effect, what is coming from single ions, what is coming from multi-ion effects. And that is one space where I don't think that if we can train an AI model to figure out where to look at such data, it would be extracted much quicker. And there is a little bit of effort going on in that effect at Oak Ridge National Lab with the Summit supercomputer, where there is a group which is already trying to look at some of these. And then there is this huge problem of parameter estimation. And parameter estimation, it comes by different names. So we call it Hamiltonian discovery, which is that if you have a data, what is the Hamiltonian it corresponds to? And it's a really tough problem. But that's the bottleneck, because once you know the Hamiltonian, you know how to change things, whether you need to add defects, whether you need to put strain, whether you need to put another material on top of it. That problem becomes easier. But Hamiltonian estimation, and Hamiltonian, by the way, in the computer science, you might call the Hamiltonian an objective function, so which is basically the lowest energy ground state that you can get in the material. And to do it classically is one thing, but to do it quantum mechanically is a QM, a hard problem, is what we call, and which means that in order to find the Hamiltonian, and I have been working with several companies, I mean with IBM, with Continuum, Honeywell, with D-Wave, and that is the same problem that comes up over and over again, is that how do we solve this problem? And one of the ways in which people have been thinking, and especially NVIDIA, with whom I think we will go through into an NDA very soon, is to see if we can use tensor network methods and get a gate-based description from tensor network methods to create a set of gates which we can say that that's a very good objective function to start with, and then move from there. And then there are other AWS is also very interested in it, from what I know. And once you go through a parameter estimation, then it is the property discovery part. So if you know the Hamiltonian, let's say, or if you have some idea, what are the properties that you can get from certain Hamiltonians? That will tell us how to tune the system. And device design comes right there. So what type of devices you can design. And so what we find is that there is AI in every space. I have already worked in AI a little bit to, for example, to look at the neutron data analysis. In fact, we had a material called dysprosium titanate and RuCl3, ruthenium chloride, and we got these huge neutron data sets, and we actually trained a machine learning algorithm to figure out what the Hamiltonian parameters could be. It's difficult because we were using a semi-classical model, which only is approximate, but we can also do a quantum model, and then doing the quantum model is the holy grail, but it's also the most difficult one where I think that quantum computers maybe someday would help. But at the same time, I mean, in the quantum computer, to look at the properties, you have to do something called time series evolution. Quantum computers are great in time series evolution because it's a Schrodinger's equation, which is working there through trotterization. But we have noise. Then how to cut the noise, how to cut the effect of the noise to look at the property that you really want to see. So those are all the problems that comes together and where I think that we can really take the help of AI. Thanks.
Yeah, so my thoughts are generally pretty similar to Arnab, so I won't repeat too much. But he brought up a great point at first, which is stability. So, you know, as computational researchers trying to design new materials or use GenAI to propose new materials, thermodynamic stability is usually like the first filter we impose because something that is stable or close to stable is much more likely to be synthesizable than something that is not. And I would say to contextualize this in the current generative models that are out there, typically they report stability rates on their proposed materials around like 10% or so, which depending who you ask might be great, might be bad. It sounds like a low number, but if every 1 in 10 material that you're proposing is something you can make and is actually great for your application, then maybe that's not too bad. But that brings us to the next point, which is, okay, now we need it to have the properties that we want. And I would sort of subdivide this into 2 categories, which is, one, the properties of your material in its nice, pristine form, basically the form that you've modeled it as an approximation, assuming that it's this nice, perfect crystal. And that gives you, you know, a reasonable starting point to try and filter the good materials from the bad materials. And again, GenAI, I think, does actually pretty well there. There's been a lot of work out there that have trained these GenAI models on sort of these simple idealized properties. But then there's level 2, which is, okay, once my material is containing lots of defects, lots of impurities, vacancies, inclusions, whatever else, that's going to have a really big impact on the properties that you care about typically. But these are things that still to this point, generative AI doesn't really account for just because they are so much more expensive to model, and generally there just isn't enough training data to feed into these Gen AI models. So again, I would say that's probably the point to focus on moving forward.
Thank you. As mentioned by the previous speakers, so I think it's very general requirement because in our field is require engineering or customer specific object. Based on for our targets built in natural environment, of course, the safety, resilience, and sustainability is always a general requirement, but different specific domain scientists have their own idea. For example, I learned from one of my colleagues in transportation. They point out that for pavement material, compaction ratio is really key property seeking by the MINDA, Minnesota Department of Transportation, because it really relates to the porosity level and how resilient the pavement can last, especially given the extreme weather in Minnesota. However, for the steel, for the concrete, that of course always is the material strength. How much can you resilient to the high load and the impact? fracture toughness is also an important consideration. So I would like to generate, but from a point of view, so actually I'm quite interested in the idea, I forget, I mentioned by which speaker, is about the foundation model of the material. I really see this, if it is successful, that will mean a lot, because we deal with so many different materials in our daily life, in our engineering. If we really can have a model that can majority to handle different characteristic of a material and can utilize in our design and optimization, that will be save a lot of effort. So speaking of that, there is another level of design in our field, is more like a structural material design, which means we not only design the components of the material, we design the structure, the microstructure of the material. Is like related to the so-called topology optimization in our field. Actually, I'm working with faculty Sunji in CS department to try to develop a more general constraint optimization framework can apply to this, our structure material design. So I believe this is also interesting directions. Thank you.
Wonderful. Actually, speaking of microstructures, I know Kaichi gave the example of concrete, but it's also very much relevant if one thinks about now biomedicine and thinks about designing drug delivery materials, right? Something that you can put in your body which would carry the drug to, let's say, your brain, to a brain tumor, sorry, right? And so in that case, you want the structure of the material to be such that it can absorb the drug molecules, but it's still as flexible enough that it can penetrate through your brain, or it can be injected to the location, but still delicate enough that once it's done its job, it can disintegrate easily and your body can remove it without it getting toxic. So there is not just, in all of these cases too, it's designing the microstructure stuff, but also aging, which I think is typically is harder because, again, their data is scarce. So even getting those aspects of materials is challenging. Okay. The second question that we had was, what are the most promising near-term and long-term discoveries in material science that could be enabled by GenAI, analogous to breakthroughs like AlphaFold and Rosetta Fold in the life sciences? And as the lead of the panel discussion, I'll just jump in and say this because I've been very close to this discussion about AlphaFold, Rosetta Fold, and its limitations and its benefits too. I think AlphaFold and Rosetta Fold really put us into this, I think, like momentum of trying to really use AI to solve a lot of protein-related, biology-related problems. And one place where it just has gone, I want to use the word bonkers here, is in trying to do the discovery of drug molecules, right? Small molecules that you can use as medicines, that you can use for treatments of various diseases. And the reason why it can work is now because we have this collection of lots of protein structures. We know where they come from. We kind of know how they function. And so now we could try to use this whole aspect of AI and generative AI to find those new chemical molecules that might actually function better. And I think this is a really interesting and very cool near-term success that can happen, but one of the challenges or I think two challenges that have emerged, both of these tools or such structure prediction tools can predict the structure, but again, as I mentioned, it's not guaranteed that they will actually synthesize in the lab. And in fact, there are studies where, AlphaFold predicted, let's say, 100 structures of different sequences, and when they went into the lab, not a single one folded into an actually functioning protein, right? So that challenge is still there, which basically means that we still need to capture some aspect of the physics to actually say, oh, well, is that structure even possible or not? And the second thing comes back to the dynamics, the time series, the fluctuations are super important at these scales. And they really make a difference in terms of whether your protein will function or not, because without those structural fluctuations, it may not. It's not a rigid body, so it's not going to function if it doesn't have those dynamics involved. And those dynamics change with the environment. And so being able to capture all of this in sort of any model, especially in GenAI, would, I think, be the next big step. And there are lots of companies, including Microsoft and stuff, that are trying to do that. But the challenge becomes having enough data, especially because we are trying to span a very high dimensional space of just the design itself. And so they have some models, but again, there's no guarantee that they work. But I think that's kind of the direction, at least from life sciences, biology perspective.
I'll be short on this one, but you have touched upon a very important point, which is modeling the fluctuations and understanding what are the various steps that are involved in the fluctuations, which site will bend, which site bends, and that has what effect on the other sites. And it's a problem which has a multivariate and a multidimensional character. And in fact, I mean, speaking for AI for quantum, I think that this role of fluctuations is also something which is being increasingly discussed as something that we need to understand using AI. In fact, there is a theme right now which is train the AI on the quantum data as long as you have the quantum coherence in this quantum chips, so that you can understand what would happen in the long time scale when the quantum chips have actually lost their coherence, because as you know, that coherence and noise is still a problem. And that actually helps us understand very minute fluctuations, very small scale fluctuation. Like if you know what is, let's say, a very high energy phonon mode in a material that gives you some properties, what is the lowest energy mode doing? Phonons are, by the way, certain types of particles which help to carry vibrations and sound energy. But they're both fast and slow of them. The fast are probably accessible, but how do we get to the slower ones? So those are problems where AI is being trained with the quantum data. But at the same time, I think that the role of AI is definitely from process design. And the dream that I have, for example, is to take it all the way from crucibles to chips. What is the process that where AI can really help? And what we are really talking about is designing materials out of the ideal conditions. Getting to the ideal material which satisfies that particular objective function that we really want. That's expensive. We can make a material, we always try in a lab, we try to make A and we get B. And that's pretty normal. But what I think AI is going to help is that what is B useful for? And what are already the good things that we have in B, and to what extent the properties that we want in A are already expressed in B and can be useful for other things, given that certain properties that you can already exist that you can have trained the AI model for. So that's where I think the victory really lies.
Okay, in the interest of time, we'll move to the next question, but we'll let Nathan and Kaichi answer that because Arnab and I have spoken too much. Go ahead. So the third question is, how should we evaluate GenAI systems in material science? What evaluation strategies align with scientific end goals?
Yeah, so I think, up until this point, we've talked a lot about stability, synthesizability, having the properties that we want. So in terms of evaluating your generative AI, of course, the obvious metrics to look at are what percentage of materials or molecules that you're generating are something that's stable, that could be made in the lab, and how close are their properties to the properties that you designed for. I think one other metric that we should really think about during evaluation is also novelty, or sort of the degree of novelty. We've done a lot of benchmarking in our group on these generative AI models to propose new materials. And what we find is that there's generally a very, very strong trade-off between the stability rate and the novelty rate. So, okay, maybe you can generate a lot of materials that are realistic, they're stable, but they basically match something that's been discovered for the past 8 decades. Or maybe it's not an exact match, but you took a material and you swapped out one atom out of 20 atoms in the unit cell. And most people would look at that and say, well, that's kind of a trivial change. Would you really consider that to be novel? And so I think as we evaluate these GenAI models, we want to kind of strike the right balance between generating some really new material, something outside the box that a manual human researcher would have never really thought of, while still being something that is realistic and could actually be made in the lab.
Answer the same question?
Yep.
Okay. Let me double check. So for this one, I believe I'm not the expert for that. I'm kind of just a user of this AI. So currently, in practice, what I do is I will check some similarity matrix. I just, the generative output compared to the ground truth. I usually will have some high fidelity simulation data, and also will have some collaborator from experimental to provide some sample. But I would like to mention one thing is that because Optimate, my goal is to do the inverse modeling or that kind of put this generative AI in the loop of a solver. So which usually allow me can generate some physics-based another level of output. So I will particularly check the physical consistency through this loop. So so I think I will more focus on the physical consistency, because as you know, generative AI maybe is good to directly produce the first level output directly for comparison, but what is the derivative of this output data? Then this is something is less controllable. So, but we will be really interested in looking at this kind of a matrix, which is important in mechanics or physics.
Yes, actually, please do.
Just to take for this, I might not believe it and it might be naive, but it seems like there are lots of things that AI could do for sciences. But it also seems to me, just for a devil's advocate point, that, like Nathan, you mentioned that we ran GenAI for a property with it was a simulated property, which it showed good results. But then I went to a lab or some other property and saw that it did not do well. I think this panel is perfect in this sense. There is a physics person, a computational person,
chemistry,
a machine learning person, like physics simulations, and a final experimentalist. So it seems to me right now what we're doing is we are doing GenAI on one property, filter the results, then go and check on the other one. It seems to me all of this should be in one loop somehow. So I think thinking about how all of you can work together is probably even more better for AI, I guess.
We certainly need a consortium here, right? That's what we are really defining. But I think that you bring a very important point, which is benchmarking. I think that what are the right benchmark questions and benchmark checkpoints that we should have to say that, look, we have benchmarked it enough that we know that the AI model works, either for synthesis or for looking at the parameter estimation or whichever problem, but at the same time, we should not be training it so well that it just misses what we have not given it. And especially we worry about that in physics, because there is always new physics which is remaining to be discovered, which is, I think that there has to be a loop which needs to be set up, a feedback loop, and the questions there would be, do we actually make another material, or do we actually tune the material in a way which AI informs us and see whether that really worked?
Yeah, I will say that it's also possible. I think one of the very amazing opportunity that AI gives is the ability to bridge these different scales and different properties and approaches, because typically that's been the hardest thing to do sort of in physical modeling. So just again, drawing from the work we do, the two experimental groups that we work with, one of them is a protein person and one is a virus person, and they actually put a real virus in with all the different formulations and check the infectivity. In our simulations, we will never be able to do that kind of simulation. The ones I showed, the pretty movie I showed, is one of the most expensive you can do at this stage, right? But what we can ask is, what can I learn from my molecular simulations that correlates with what they see in more real systems that then I can use as a filter in high throughput screening? And that bridge, I think, comes through AI because it's a complex function. It's very hard. And generally in bio, but I think this is true in materials, it's also a very fine balance of interaction. So there are too many knobs, and there's a lot of correlation, and I think AI there can do a really good job of identifying that and helping us sort of create that complex function. And that's essentially kind of the direction we've been trying to take. Right,
I have...
Yes. Okay.
I got it.
Sorry, we'll do this question, then we'll
you could have
come.
continued. So I think the title says, what the GenAI can do for science. I would put the other way, what science can do for GenAI. Because coming from where I am, if you take chemical engineering, there are two things that are important. Combining molecules, catalyst, separating molecules, membranes. And if you take batteries, the same thing. You take nuclear engineering, all of that, we are looking at the other way around. What are the things that we need without any application? Just material discovery is good, but without any application, you're just discovering stuff. But there's two things. One, even if you discover it, you don't know how to scale it up. Can you actually manufacture it? And in fact, battery manufacturing, the biggest problem is the supply chain. Okay, when you take the cathode, anode, and graphite and all that, you need the supply chain in terms of scaling up the production. So my question would be the other way around. What are the applications that you're looking for, and that might drive what GenAI can do or cannot do, actually? Okay. So the feedback coming from this to GenAI to say, here are your limitations, and if you want to do what we want to do, and what can you improve? So we always think that GenAI can solve science problems. It's the other way around, actually. So that's what we are looking at the DOE, so looking at what is that to use. GenAI is a tool.
Right.
Okay? AI is a tool. It cannot be this way, it should be the other way. So.
Right. So. Actually, I was reading an article recently, and I really liked what they said. They said it's not GenAI4Science, it's GenAI and science. And I think they go synergistically, and it's, like you said, it's a tool. And everything in science that we have access to is a tool, and we can use all of them synergistically. But I'll also let others answer.
I definitely agree. I mean, like you said about battery manufacturing, I know in especially computational research, a lot of times you'll propose some, supposedly excellent new cathode material with the right performance, but it relies on some weird chemistry or some weird precursors where the supply chain is just not readily available. And I know there has been some work done on sort of the forward ML to try and incorporate these metrics into the predictions so that you're only recommending materials or chemistries that could be manufactured at scale. I haven't really seen much on the generative AI side to do that, but I agree. I think it'd be a great idea to actually feed that data into these models so they're only proposing things that are reasonable.
I have a quick question following up on Kaichi's comment that you want to check the consistency of the physics, and I think that's a wonderful idea. However, what happens when your physics, so there's also unknown relationship in the physics that we're not so sure about, right? So in that context, how can you do the physical consistency check, right? So that's a question for Kaichi. The question for Nathan is, do you have some important insights about how to ensure that you get a diversity of the outputs from the GenAI so that you get something that's not really seen in the examples, right?
Okay, let me take the first question. Thank you. I think this is really the core question. I always think about this question. Actually, from my point of view, although we always speak of physics, it seems physics is like a ground truth and already there acceptable, but actually from my point of view, it's not true. Physics also have its resolution. Physics also has its uncertainty. Actually, if you look at the history of science from Aristotle, we based on the empirical observation to advance the theory gradually. So this is a good point. And in terms of practice, even when we talk about a well-defined partial differential governing equation there, which discretization method you use that to imply in AI actually will cause difference, will cause the performance difference, whether using strong form or weak form, the groundwater equation, it causes difference. So, but this is a less study area. So I fully agree. So of course, in terms of handles the problem, I see a lot of methods. For example, people using emulator, try to using neural symbolic idea. But if we look at the essence of this method is actually based on approximation theory. You still need a model. So it's still based on some kind of understanding, but as I want to ask the question in my introduction is that I always believe how to properly evaluate this generative AI input in terms of accuracy, conversion, and stability is still the long-term goal that we all need to really figure out. Okay.
Yeah, so your question was on how do we ensure diversity and novelty in the outputs that these models are giving us, which I think is a really great question. I think there's maybe sort of like a smart way and a dumb way to do it. Both are kind of equally valid. I think the smart way is that these models typically have some sort of latent space representation of the materials. So let's say you're working with an autoencoder, then you have some low-dimensional vector representation of this crystalline structure. And based on that, we can inherently measure distances between materials that are being generated. And so basically, what some models will give you is some hyperparameter that controls where exactly in this latent space are you sampling, and are you sampling sufficiently distinct regions of it to generate materials that end up being very different. But then those also end up usually having a much lower stability rate, so it's a trade-off. Maybe the simpler way is to just basically generate materials with these models, and then just reference whatever's being generated against every known database you have of materials that have already been reported, and have some way of measuring how different these materials are from what's already known. And then if you're generating a bunch of stuff that's already known, just keep generating, right? I mean, with these Gen AI models, they're not slow, right? They're usually very fast to generate a new material. So it really costs you very little to just keep generating new stuff until you find something that in your mind is sufficiently different.
It's made of speculation around here. So in 2013, the Nobel Prize in Chemistry was given for the development of multi-scale models for complex chemical systems. It's chemistry. In 2024, we got it for computational protein design, which you just mentioned, AlphaFold. But AlphaFold never explained the science behind why it did it. So any speculation what the 2035 Nobel Prize in Chemistry will be? Every 10 years.
That's a good food for thought.
So it will be for the chemistry that leads to new types of, I want to say the chemistry that leads to new kinds of quantum properties such as quasi-particles, which will completely revolutionize how we look at energy transfer, for example.
No, I'm not a chemistry science, but I just want to point out I work in DOE labs before, and I work on one project related to flow battery, so also using AI to help to do the inverse modeling, and also I work with hydrology using just, AI for subsurface science. Then I can tell, depends on the level of physics, the established physics, people have different perspective on AI. Clearly, the chemistry people actually like AI a lot, using graph neural network too. But so my understanding is like if the physics is less understood in the field, actually AI will advance rapidly.
I think it's also a little bit related to how quickly you can generate training data. And I think, at least in chemistry, good job of generating a lot of data because there were databases for crystal structures, etc. In sort of getting it a little bit higher to like soft materials, it became even more challenging because now you have to really account for dynamics. You are at a high temperature range where things move around. And you need to be able to capture that. And I think so there we don't have as much data that we can put together and like fit stuff to. So I think that's kind of where it's been a little bit more challenging, I think, AI. But I will say that, you know, if you're thinking about, at least when I'm thinking about future of AI, I would say an exciting advance for me would be where we can actually realize this dream of we want to find new things at the molecular level, whether they're new materials or new formulations or new sort of constructs, because in proteins and enzymes, you're not finding new necessarily enzymes that are too different. You're finding enzymes that maybe will do something different than what they've been made to do already, right? So that's a different form of diversity. But you can do that to then say, this is the way you go and realize this in reality, right? That would be really what we are all after. And I think approaches that will allow us to do that would be the biggest advance in my mind. All right, with that, I've been told to stop talking and let you go have food. Thank you.
Let's take our seats and let's get started for the afternoon sessions. We have a very Again, welcome to the afternoon session. This is GenAI for Health, and we're going to kickstart this session by a keynote talk by Hong-Fang Foon, who is from Microsoft. He's a general manager for Microsoft Health Futures. He has an amazing record and accomplishments at the interface of GenAI and health. I would say probably one of the best guys we could have found. We are very lucky and happy to have you here. He was also named as the Technology Champion of 2024 at the 6th Annual Healthcare Leadership Awards. So it's a big honor to have you here.
Thanks so much for the kind introduction. Can everyone hear me okay? Awesome. It's really excited to be here. And in the past 1.5 days, I actually were able to get out of my own intellectual bubble and start to learn a lot of different topics, right, from agriculture to hydrology, from chip design to material discovery. So in my talk, I will kind of like switch gear a little bit and kind of return to some of the maybe perhaps slightly more mundane topics, such as how can we cure cancer before we get one, right? So it's so excited to see all the kind of interest in AI. Personally, I started my journey 2 decades ago when doing my PhD in machine learning and NLP. That was when AI was in the last ice age. I literally have friends who were in the job market and they have to make a disclaimer that they are not an AI person, right? So it's a very, very different time. And I joined Microsoft Research 14 years ago and started working on this precision medicine. I was actually, at the time, I was really inspired by this 10-year anniversary of Human Genome Project. I was also extremely lucky because I was blessed by ignorance. I didn't know how hard biomed and health is. And by the time I realized it, it's already too late, right? So really here, I'm just trying to share some of my own learning over the years with lots of amazing mentor collaborators and teams. So I want to start the talk with kind of like one observation, right? So throughout history, if we think about it, technology really has proven to be the most powerful democratization forces. One example is that every one of us here, right, have much better healthcare than any king and queen in the history, right? So this really start to obviously back the natural question that can we empower everyone in the globe to have the same kind of high quality healthcare as the most resourced person, right, such as Bill Gates and Steve Jobs, right? And in fact, today's healthcare actually still have a giant growth space, right? For example, Steve Jobs, despite all the resources he has, still unfortunately succumbed to his cancer. So we might actually want to aim even higher, is to say, can we empower everyone to have better healthcare, right, than actually today's most resourced person? So this talk is essentially one long argument to say that both of these goals are not completely crazy, right? So in fact, with given the Gen AI revolution, arguably we already start knocking at the door, right? Now, it's so good to see the excitement about Gen AI, but I should also emphasize that we are still very, very, very early, right? So some people liken this to the moment when we first figured out that copper wire can conduct electricity, right? So on one hand, we are still searching for the equivalent of the light bulb, right? And in the same time, we need to be careful not to do the equivalent of electrocuting people. So that's a really interesting time, right? And the natural instinct is that we often want to shoehorn Gen AI into the existing workflow, but I want to also highlight that the much greater opportunity actually lies in can we reimagine the entire workflow process, ecosystem, business model, etc., right? So from a technology point of view, you can think about our entire research program actually boil down to learning the multimodal language of a patient, right? And all those modalities are trying to tell us something about a patient. And if we can figure out what they're saying, we can start to create this so-called virtual patient, right? Essentially a patient digital twin that can be used for prognosis and predictive medicine. So that's exciting, but AI is really no magic, right? So sometimes it may appear magical because we actually apply the right algorithm on the right data. And in biomedicine, actually in the past couple decades, right, there is a really exciting sort of rapid digitization of a lot of the data, right, starting from genomic sequencing to electronic medical records. So there is this sort of long-standing dream about real-world evidence that is now quickly becoming a reality, right? So when you think about it, every day there are literally billions and billions of data points capturing patient journey from diagnosis to treatment to outcome. And if we can crack the code and distill all the insight underneath, right, we essentially have a population scale free lunch, right? Free out the top, probably one takeaway you will find is that I'm a firm believer of free lunch, right? And so, of course, real-world evidence is not a new idea, right? People have been milking, like insurance company milking claim data for decades, right? But the big difference is that in the past, a lot of the focus has been limited to the available structured data. And unfortunately, vast majority of the fine-grained patient information actually lie scattered in all those unstructured data, right? From notes to imaging to multi-omics and so forth. And now the GenAI basically afford us a very, very powerful tool to start to actually understand, interpreting all those kind of unstructured data, right? And so to make our discussion more concrete, let me show you two marquee examples. The first is clinical trial matching. So as many of you know, unfortunately in cancer, standard of care often fail, and then the clinical trial become the last hope. However, even in the US, only a tiny fraction of patients were able to find a matching trial. And ironically, on the flip side, right, many clinical trials fail because they couldn't find patients in time, right? And as you will see very soon, this is actually an example where actually even today's GenAI, right, can already start ushering in a major transformation. My second example is immunotherapy, right? So as we talked about earlier, actually even today's best healthcare still have a giant growth area. And one example is like think about immunotherapy. That's really the cutting edge of cancer treatment that basically work by mobilizing the immune system to counter, cancer mutation, relapse, and all those kind of good stuff, right? And indeed, there are really spectacular success, such as Keytruda, right, that can work miracle on some of the late-stage patients. And also, many people believe that this is exactly a direction where we eventually will solve cancer, right? Because the immune system has the blessing of natural selection and can really counter a lot of the what make cancer really hard to deal with. However, if you look at even the best kind of immunotherapy today, right, the overall response rate is only 20%. So this is an example where there is actually a giant potential that we can go well beyond even today's what the best doctor can do. When we think about biomedical discovery, obviously top of mind would be the early R&D, right? So these are indeed very foundational, very exciting, but in the grand scheme of things, they're only 10–20% of the cost. The vast majority of those astronomical costs and the time actually lies in a lot of this super mundane later stages, like how do you run a trial, how do you actually conduct post-market surveillance, and so forth. And those happen also to be exactly a sweet spot where real-world evidence can already immediately have an impact. Modular the fact that we have to be able to, figure out those data, right? So then really the trillion-dollar question is that can GenAI deliver, right? So people joke about like the buzzword basically evolved in the past 3 years, right? From GenAI to multimodal, and this year, surprise, surprise, is agent, right? When you look under the hood, obviously, it's not all pony and rainbows, right? So there is still lots of challenges, and naturally there were also skepticism and so forth. But this really reminds me of this Amara's law, sometimes attributed to Bill Gates, right? That we tend to overestimate short-term progress, right? And that's actually exactly what led to the hype, right? But in the same time, we also tend to underestimate the long-term kind of like transformation, even though those are already happening quietly in the background. So in terms of kind of like GenAI application, actually the major transformation already happening in the background on the productivity gain side, right? So this is the regime where actually human experts are perfectly capable of doing this stuff, except that it's just so tedious, so time-consuming, so expensive, right? But this is exactly the sweet spot of current Gen AI, especially in the text modality. Now, we are still very far away from automating discovery for creativity gain, but every step along the way can really unleash a giant value creation. So one of the marquee examples for productivity gain is this so-called universal medical abstraction, right? So basically, there is tons of this key information about a cancer patient or any patient, right, that are scattered in all those clinical biomedical texts, right? And prior generation of AI suffered this, what people sometimes jokingly call the death by a thousand cut problem, right? So it's probably not hard to build a particular model to extract a particular attribute from the nodes, right? But when you start to have hundreds, if not thousands of attributes, then you start to get hosts. Now, what's amazing is that the frontier AI today, right, even basically even 2 years ago when GPT-4 first came out, they already have acquired sort of like this kind of amazing capability that can actually start to extract a lot of this kind of attribute out of the box, right, with natural prompt, right? Arguably the minimum thing you have to specify is like what are you trying to extract, right? And those frontier AI are smart enough to be able to actually do that, right? And oftentimes match or even surpass previously sort of like state-of-the-art, like task-specific, attribute-specific models. And also, this is not just, we are not just go easy on Gen AI, right? You can actually put them on some of the really hardest kind of attributes, such as clinical staging, right? AJCC have a 600-page book, right, that basically specify, based on all this condition, right, like whether this staging should be 3A, 2Bs, and so forth. What's really amazing is that you can actually literally ask GPT-4 to read the freaking menu, right? To basically put the instruction into the prompt, and then amazingly, they basically can follow those instructions. So what this implies is that actually already a lot of profound kind of like transformation can already start happening. Right? For example, every year, 20 million new cancer patients in the globe. Traditionally, right, you hire these poor abstractors or registrar, right? They have to parse through hundreds of nodes, and each cancer patient can take them hours, costing hundreds of dollars, right? And with Gen AI-powered universal medical abstraction, it takes seconds and costs a few cents, right? So what's the implication is that remember our first example, clinical trial matching, right? The implication is that actually on the technology, pure technology front, right, we can already empower, basically we can basically scan all those incoming nodes 24/7, right, and we can scan all the trial, right, and all the updates and what have you, and then we can do 24/7 just-in-time clinical trial matching, right? And so this can already have major implication, and we have over the year we have lots of amazing collaborators in the clinical side, right? In particular, with Providence, a very large health system in the West Coast. Actually, we have shown that this actually can start working end-to-end, including in some of the high-profile trials that, as reported by New York Times here. And I also want to highlight that clinical trial matching, in the grand scheme of things, is very important, but it's only a kind of appetizer, right? So what the capability can enable you to do is to reimagine the entire clinical trial operation, right? A single cancer trial right now can cost you $100 million, right? And a lot of saving can and speed up can potentially already at our fingertip, right? For example, one really major implication is also health equity. So even in the US, 85% of cancer patients are treated in these community rural hospitals, right? And they often are completely ignored. They are like the dark matters for clinical trials, right? Because they simply don't have the resource to hire those trial coordinators to be able to match them to the trial. But with this technology, we can already arguably instantly kind of like democratizing all this access, right? And actually enable all those patients to be able to have the trial. And then for the sponsor side, right? For the PI side, they can easily figure out where are the patients, right? Today it's purely guessing game, but you can actually give them a tool to say, give me any trial criteria, right? I can immediately tell you where are those patients, how many of them historically, what are the trends, and so forth. So this is very exciting, but this is only the tips of the iceberg, right? So when you think about text, right, it's obviously an 80-20 modality for patients' information, but they are really sort of like just imperfect human translations. So over the years, I make a lot of friends in clinical side, right? They tell me all kinds of jokes, right? So radiologists will tell me that sometimes they don't agree with themselves 2 weeks ago, right? And pathology told me that if they turn the pathology slide 90 degrees, sometimes they see different things. Right? And that's obviously very natural, right? Our visual cortex are evolving in the jungle, evading tigers, right? They are not doing MRI back in hunter-gatherer days, right? So the question then is like, can we actually be able to go back to the raw signal, right? So all those CT, MRI, omics of you like, right? To try to figure out, they are trying to tell us something, but today we are just not doing a very good job in translation, right? Can we do a much better job in translation? I also want to emphasize that individual modality is great, but they are also inherently limited, right? So only by kind of like synthesizing all of them together can we recapitulate sort of a really holistic kind of like patient representation. So I'm a machine learning person by training, so this is my kind of nerdy way to think about what is precision health, right? So I basically think about it as we are trying to learn a function, and then the input is this multimodal information about the patient. And then what do we care about? Essentially are two things, right? One is like, can we predict the disease progression, right? The prognosis. The other thing is, can we predict the counterfactual treatment response? If we can do those two things accurately, then we are really golden, right? Now, obviously, this is not so easy, right? So the patient information is not a snapshot, but actually a longitudinal time series. And most frustratingly is that most of the information you want to know actually is missing, right? And then the observable information often have noise, have biases, and so forth. But this is exactly why GenAI can be so promising for precision health, because the gen part, right, is basically referred to this mathematical concept of generative model over the joint distribution of all these variables, right? So it seems like we're trying to do a much more work, but actually end up that we are making our life much easier. And so by basically modeling all this joint distribution, what we end up with is that a really powerful and also principled way to basically say, number one, let's really compress all those observed information, right, into this compact representation of patient embedding, right? And number two, we can invoke the standard probability inference. Conditioning on all those observed variables, we can predict those missing stuff, right? And also, when you think about it, right, the longitudinal medical event prediction, that's basically a special case. So this basically motivates us of a research agenda to say, can we portray a very powerful biomedical frontier model from all those real-world data, right? And then the GenAI disruption means that now for the first time ever, we can start to imagine building this really high fidelity representation that can almost start to serving as a patient digital twin. Now, given such a digital twin, right, so then at the inference time, we can start to do population, sort of patient-like-me reasoning at the population scale. When you have a cancer patient, right, and if there is a resource, the first thing you would do is to try to look for a second opinion. Now, if we have this kind of patient-like-me reasoning, you can snap your finger and you can get a million second opinion right there, right? You can basically look at all those most similar patients. You can say, hey, what treatment have been applied to them, what kind of outcome have been observed, right? And then you can immediately improve the patient care, right? You can also start to compare all those exceptional responder versus the non-responder, and then you can start to poking at why those 80% of people don't respond to Keytruda, right? So there is a discussion about this concept about emerging capability. So basically it means that if you have high enough capacity in your model, right, and you feed it high enough for free lunch, right? So let's say the whole public web, right? Then the model will start to have this phase transition in terms of capability, suddenly become really, really good at doing a lot of stuff, right? So now we can really start to imagine what if we were able to start to feeding, let's say 8 billion, right, multimodal longitudinal patient journey, right, to this kind of frontier model, what kind of insight can they unlock, right? So that would be sort of really exciting, and potentially we can now shatter the glass ceiling of today's healthcare common sense and go way beyond to our second goal, right? So this is very, very exciting, and And I will argue that this is ultimately sort of like the creativity gain, right? Which is like, can we empower human expert, right, to consume, all 30 million papers, 8 billion patient journey? Obviously, we are still far, far away from, getting the moonshot, right? But there are some tiny, tiny baby steps there. One of the really perennial challenges here, right, is that there are so many of all those kind of modality, multimodal complexity, right? And also, not only we have a long tail of this kind of modality, but also we often have very little data here, right? So brute force approach doesn't really work nicely here, right? So over the years, we basically try to figure out, again, as you can see, my font is about free lunch, right? So all we are obsessed about is to figure out what are the recipes to kind of consume those free lunch. And I summarize them to basically 3 big free lunches, right? The first one is basically, I think a lot of the speakers have gave already really nice introduction about, is basically that this idea about like any unannotated data point that you have, you can turn it into a self-supervised training instance by introducing this modality-specific encoder-decoder pair, right? So, and what they do is basically compress the original input and then decompress that to recreate the original input, right? And also for text, there is somebody already spent billions of dollars, so you don't have to do anything, right? Now, this is a very powerful paradigm, but for individual modality, there are also unique challenges, right? So, for example, in precision immunotherapy, the holy grail is that can we learn to master this so-called tumor microenvironment grammar, right? So that basically model how those tumor cell, immune cell interact with each other, and actually the pattern they interact with each other hidden a lot of the secret about whether the patient can respond to the immunotherapy or not, and also can we fundamentally reprogram the so-called cold tumor, right, into the hot, which will respond to the therapy, right? If we can figure out the grammar, we basically are done, right? So this is actually sort of like motivate us to start looking into digital pathology, right? And arguably, we already have a very powerful tool, right? So all of you are probably familiar with Transformer, which is the workhorse of the modern Gen AI. And it basically works by essentially modeling, you have image, right? You have 2 pixels. You basically try to pass messages between the 2 pixels repeatedly, right? It can basically, in this way, it can capture arbitrary complex patterns, right, in the image. However, it has one Achilles heel, right? Because it has to model those pairwise, dependency, then the computation grows quadratically in the input size. Now, unfortunately, digital pathology has among the largest images in the world, right? So a single slide, if you're using standard transformer, right, a single slide will cost you 1 billion times in compute compared to standard web images, right? Like cat and dog is fine, right? Once you go to digital path, like that's a challenge, right? We are really lucky to have amazing collaborators from Providence, for example, in this case, and University of Washington. We basically steal an idea called diluted attention from speech recognition, and then to adapt that to digital pathology. So in the interest of time, I wouldn't go, I would point you to our paper in Nature. We essentially, in this way, we basically developed the first digital pathology foundation model that can truly scale transformer to the whole slide images, right? So since our Nature paper publication, really excited to see actually the download have been already exceeded 1 million times. Even more excitingly is that some researcher in Mount Sinai and Eli Lilly, they basically conducted the first they demonstrate the first real-world, real-time clinical deployment of a fine-tuned gigapath model for precision oncology across multiple continents and institutions, and they recently published this in Nature Medicine, and those are really the sort of the gratifying moment for us. This is great, and also there was exciting progress in like CT, MRI, single cells, and all those good stuff, right? But even assuming that we learn a really good unimodal language, right? Even if we can figure out how to represent individual modality, we still have a second but even bigger challenge, right? So each of those modality, you can think about them as basically telling you something, but in a distinct language. So essentially, we basically have a United Nations problem here, right? So we have lots of languages, right? And they each speak gobbledygook to each other, right? So what we basically need to figure out is that how can we do translation across those modalities, right? So our machine translation friend, what they do is that they basically introduce this resource-rich language, typically English, right? They're using that as a bridge and so-called interlingua to basically bridge across all those languages, right? So you can translate from language A to English and translate from English to language B, right? So this is exactly how commercial MT system, machine translation system, scale to hundreds of languages in the world. So what we are proposing here is that let's steal their playbook, right? And there is a very natural kind of interlingua modality, which is the text, right? We already have very powerful kind of like foundation model for the text modality, right? But also, we also have the second kind of giant free lunch here, right? So for any modality under the sun, right, even the most exciting cutting edge new stuff, typically the study of that modality is conducted in natural language, which means that you will leave paper trail, right? So for example, you have a radiology image, oftentimes you can find a radiology report, you have a pathology slide, you will find a pathology report. Those are imperfect human translation, but still they are kind of like free lunch, right? So as long as the signal outweighs the noise, they can give you sort of like some nutrient, right? So then what we are basically trying to do is to piggyback on those encoder, decoder you already learned in the first stage, right? And then we're just focusing all our attention and compute to train a lightweight adapter layer that essentially serves as a translator, right? So you basically do this for individual modalities. So now you basically modularize your modeling. So now you avoid some of the extreme data sparsity, right? You can also implicitly align everybody to the text semantic space, right? So now they start to talk in a similar kind of like variant of the language. And also another advantage is that the text, all this kind of frontier LLM, right, they already capture entire world's knowledge, right? So you throw a EGFR or a gene, right, or maybe a diabetes or something. They don't see it just as a string, right? They basically have all the knowledge about those concepts behind the scene. So now by actually grounding the modality to the text semantic space, you also allow implicit backprog of the knowledge infusion back to the interpreting all those individual modalities, right? So in the interest of time, I will not go into technical detail. You can check out some of our early work on LlamaMet that start to sketch a general recipe here, right? More recently, we basically following this approach, using the natural language as a unifier to essentially develop this biomap parse model that basically bridge across 9 imaging modality, 64 object types, right? This basically enable you to essentially, you can talk to the image, right? You can conduct elaborate, holistic image analysis by essentially just talk, right? So very excited to see just before the workshop, I checked the monthly download count. It become a little bit obsessive, right? But I saw it just surpassed 2 million times. Really try to wonder where are those people, right? So, but very, very exciting. So in the same issue of our paper, Nature Method also published an external review that says some nice word about our paper, so really heartening to see that. So far, it's all good, but we still have one more giant, arguably the largest free lunch out there, which is the patient journey themselves, right? So many of you are probably familiar with GPT-4, right? It basically seems to be doing this arguably brain dead way to say, let's predict next token, next token, next token, right? It seems very brain dead, but if you apply that to trillions of tokens, suddenly some magic happens, right? So we are basically proposing that we can actually do the same thing on the patient journey by essentially learning, forcing the model to learn by predicting the next medical event, and so forth, right? In the interest of time, I will not go into too much detail. I will point you to some preliminary paper that we put out. So we try to conduct a first scaling law study of it. Hopefully in a couple of weeks, there is a even much larger study that with a partner that we can talk more about publicly. All these are really exciting, which also lead us to start to think even bigger and aim higher, right? To say, we don't have to just embed patient, right? But we can actually embed the trial, we can embed the drugs and so forth. And so eventually we can potentially develop this so-called sort of like universal embedding calculus, right? For precision health and biomedical discovery. That's ultimately we can potentially sort of generalize into really sort of like new domains and rare conditions. Now, there are many, many exciting frontiers, which I don't have time to talk about. Obviously, there are multimodal reasoning, right? So reinforcement learning and all those kind of good stuff. There are agent, right, and so forth. And it's not every day you have your CEO talking about your work on main stage, so that's why I can't resist to put the image there. But I want to conclude by actually leaving with provocative notes, right? So with what we have today, we actually have a really powerful tool already at our disposal, which is that if you give me any research protocol, right, I can snap a finger to conjure up this virtual case arm and virtual control arm, right? And this basically gives us a population scale free lunch on hypothesis generation and testing. Now, this is to show that we are not completely crazy, right? So there is already some very promising, even though very preliminary work with our collaborator at Providence. We basically show that for this marquee lung cancer trial, including the original Keytruda trial, right, we can using the real-world data to simulate the published hazard ratio. So I want to add a disclaimer. I'm not saying randomized control trial is going away anytime soon. But what we've started to feel more and more is that we can harness those real-world data to make those trials to be much more efficient, much less costly, much, much faster, right? So I want to highlight my team who really do all the works, and also our wonderful collaborator without whom we can't do any of this. Thanks so much.
Wonderful talk, and what a great way to start the panel. While, Anant, you're setting up the panel, maybe in the middle of the questions, I can take them while people are setting up. Yes, and then I'll come to you. Yeah. Oh, yeah, you can take it.
You had a slide where you had multiple model, like in the previous couple of slides back, where you had MRI, CT scan, a graph, bar chart. No, just you have to go forward. I think you skipped too much.
Oh, too much?
Where you had a bar chart, where you had CT scan, MRI, like a bar chart, and then he showed what is the. My question is, which type of diseases require which type of information? You had a bar chart with CT scan, MRI, like that stacked up, different one, 10 to the power 3 of CT scan, so that one. So is that irrespective of any disease, or you have to throw all that into that? So the reason I'm asking is, my son was diagnosed with something called CRMO, chronic recurring multifocal osteomyelitis. And then after so many tests, so many this, so many that, then they said it is idiopathic. And then they said, okay, it is autoimmune disease. And then finally said, yeah, he will outgrow. So what is the point in all of that? So many data. So I'm just wondering, what is your thought on which disease require what type of data, so that you don't put through patients on hundreds of tests?
Absolutely. So in fact, if you look at the NCCN guideline, right, so for the cancer guideline, some of the most complicated, like non-small cell lung cancer, right, it's a giant decision graph, right? It basically is a sequential process where it's, I think about, again, I'm a machine learning person, so I think about is every step you try to maximize your information gain, right? So you're trying to, based on your current sort of like hypothesis, what are the more information gain? I think that could provide probably a principal way that we can start to structure those. And I think you also raised another really important question, which is like, So far, there is a reason why we fixated a lot in cancer. It's partially because a lot of the data are already in the clinical, record system. When you think about autoimmune, when you think about mental health, when you think about neuro, a lot of those stuff, the data is actually outside of the clinical, right? So you don't know yet which, number one, we don't know yet which modality give you the ultimate information. And then number two, exactly like you said, it should be an optimal kind of sequential kind of maximize information gain process. Yeah, absolutely.
So anyone has questions? Because it's true. A couple of things. Could you put the slide with Marty Tenenbaum?
Put
the slide with Marty Tenenbaum.
Oh, Marty Tenenbaum. Yeah.
I just want to take a photograph.
Yeah, absolutely. Yeah, he's a great mentor and inspiration. So when I first started this journey, Marty is the one who have been basically talking about how AI can help democratizing cancer cares and all that.
Yeah, we kind of go back 40 years or so. Okay.
Small world.
Small world. Yeah.
Awesome.
And anyway, he's a great guy. So the question I have is that we're talking mostly about treating diseases, but you also mentioned preventing diseases. So that is scientific wellness, for example. Like you have all this data that you are coming into the picture. Now what happens is that if you actually have, let's take, as Leroy Hood puts it, blood as a biomarker, and as you're taking this blood longitudinally across the time, you can detect that this guy is potentially going to get a particular type of cancer and prevent our Alzheimer's or Parkinson's, whatever it is, and prevent it before it is happening. So is that being incorporated into it?
Yeah, so you might notice in my title, I put precision health. When I started, it was precision medicine, right? But that was like treating the disease, right? But eventually what we want is to, if you look at actually the cancer mortality, it's mostly moved by a lot of the prevention, right? So treatment have made some dent, but prevention is a much bigger bang for the buck. Unfortunately, prevention and early screening also have lots of other challenges because your signal to noise ratio are just so low. And then you also worry about over-diagnostic, over-treatments, and so forth. So for example, Grail is a company, right, that have a grand vision to say take liquid biopsy from blood and be able to detect cancer very early on. So far, I think we haven't got enough powerful data and model yet, but I think that's absolutely the trend, is to go earlier and earlier and do intervention before actually the patient become really sick. Yeah.
One more.
Thanks, everyone.
And I'm handing it over to Anna.
Well, while the computer is booting up, I might just as well take the opportunity to thank Professor Kumar for setting up this wonderful meeting. Most of you are my friends, and it was a joy to see you all again, and I made a whole bunch of new friends, and I realized I have incredible taste in people. I make good friends. And also, for those of you who don't know, Professor Kumar is my PhD advisor, so I get to come back to my guru every year, so this is wonderful for me. All right, so this is GenAI for Health and Life Sciences. That's the title. We're going to keep this attractive, so we're going to have short introductions and opening statements from people. Ask lots of questions. I have about 3 or 4 slides, which is absolutely wonderful that Hoifeng spoke before me, because basically that's going to repeat what.
I'm going to hand you this microphone.
GenAI is going to change this world. I'll just stand here. Yeah. So it really has a profoundly important role, and our experts will all speak to that role. I'll give you some examples, and these will look very familiar because you probably saw things like these just now in Hoifeng's talk. So I just picked out some slides from my own papers the past 4 or 5 months. So that's that's something called annotate any cell, and I think Hoi Fong set this up beautifully. Pathologist's job is to look at that little slide and try to figure out which one of those cells is actually cancerous and make some more judgments on it. That's, of course, a miserably hard job, and in fact, as Hoi Fong said, you turn that thing sideways, you see different things in that picture. So this tool basically lets you annotate pathology images like this. It's a beautifully simple semi-supervised tool where it segments every cell, moves it to a latent space, and then as you sparsely annotate cells, it recomputes that latent space in such a way that cells separate themselves, and once you're satisfied, you can say commit, and the moment you commit, the entire slide lights up with every cell and says these are the different kinds of cells. So it's a beautiful little tool. It's actually not published, but it's being used in a lot of hospitals right now. So at some point, I have to get my act together and get the students to write this paper. But it works. Hoi Fong, by the way, why aren't you here? You are on the panel. I apologize. I should have seen this. Here's another example. I think Hoi Fong mentioned this as well. This is multimodal as well. So this is how do you take transcriptomes and generate images out of them. So this is really cool. Data prep is a lot harder here. And the beautiful thing is you can actually do this. So we have pathologists on our team where we take transcriptomes and we generate the image. And the first time we did it, we didn't actually, so our pathologist, his name is Mario Sola. We didn't tell Mario that this was actually synthetically generated. He looked at it, he goes, oh, melanoma. I'm going like, no, that's synthetic. And indeed, yes, the transcript had markers for melanoma, which is why the image looks like it has melanoma. So we can do these beautiful things where we can generate images out of transcriptomes. And the reason you might want to do this is because if you simply give 20,000 transcripts to a pathologist, he would not know what to do with it, but you give him an image, he will immediately look at this and say, that's a melanoma. So we can do this beautifully and very simply. We can do more. So that's an example of where you take a single cell from a tumor sample, and I can tell you for each, remember a single cell means you get the transcripts from each cell. I can look at each cell and tell you, okay, that is a tumor cell, that is likely to be non-metastatic or locally metastatic or distant metastatic, and I can, with very high likelihood, predict where the distant site is going to be. Pretty cool that we can do these things with great accuracy now. This is even more fun. So once you've done all of these things, you can predict drug response. So now you can feed these models either the transcripts or the images themselves and say, I'm going to expose this cell to these drugs. What's going to happen to it? And I can generate the entire trajectory of what's going to happen to that cell. So I don't want to talk for too long. Just some examples of stuff, and that's just from our group, and I imagine there's like hundreds of groups like ours doing very similar work. So really, really powerful technologies that you can pull out at this point, and a lot of, I mean, Hoi Fong just set this up beautifully. These are all multimodal models which basically operate in some latent space where you can move across all of these modalities and make very powerful predictions. All right, I'm going to stop at this point because you've heard enough of me. We have a wonderfully distinguished panel. Professor Jagdish from Michigan, Professor Ghosh from Texas, Professor Pakmov from Minnesota, of course, Professor Fu from Minnesota, Professor Bayat from Minnesota as well, and of course, Dr. Poon, you've just heard from Microsoft. If it's okay, we'll just start in that order. We'll have some opening statements. We have a bunch of questions. We'll start with the questions, but I will just open it out anyway. I mean, we'll take every question, we'll have an answer, and then please feel free to ask questions, and we'll make it wonderfully. It's late in the afternoon. People are starting to get sleepy. Let's keep the energy up. Maybe that'll be a good thing. Please, Jag. I'm sorry.
So I am from the University of Michigan. I'm a computer scientist, and I direct the Michigan Institute for Data and AI in Society. We work with people across the university in many different disciplines. And when I was thinking about this panel and what I would say, I think the most relevant current work that I'm doing is with colleagues who are actually clinical care providers at the University of Michigan Hospital. And I think my summary statement there is because of the way laws are, there is a non-scientific barrier to adoption of new technologies, and there is a great deal of thought about how one should do this and how one can go about doing this in terms of existing workflows. And I don't know, I'm just going on, right? Okay. So I want to tell you about a couple of different things. So in terms of GenAI, one place which is basically a no-brainer is providing after-visit summaries. It's easy to record a conversation, easy to transcribe it. We've got any number of commercial products, including from Microsoft, that do a very good job of summarizing meetings. This is not the same thing as summarizing a meeting. If you've looked at your after-visit summary, there are usually some specific action items, et cetera, et cetera. But even in this sort of scenario, and then this actually legally turns out to be a very straightforward thing, because irrespective of how the thing is generated, there is officially a provider review and sign-off. And so it's simply reducing effort, and the care provider is still taking responsibility. But even in this really easy case, it turns out that there are gotchas. Gotchas include things like patients who will talk off topic with their care provider. And some of the stuff is just merely irrelevant. There's other stuff that's potentially embarrassing or sexual in nature, or, not between doctor-patient, they're talking about their behavior. Things like this, which have nothing to do with the specific medical complaint or issue being that was part of the record. And so there is a need to actually sanitize things. And these are the sorts of customizations that one has to come up with. Not rocket science, but you need to understand the application and tune the product if you're going to do this right. So that's one easy case, right? The same thing becomes a very hard case where you look at responding to patient requests on a patient portal. Because that's a place where a chatbot should be able to do stuff, and nobody is going to risk having a chatbot doing that. And that is, I think, in terms of current technology, I don't know how we get around that. Right? There are a whole bunch of very smart people looking at how to do better, but how to do better is not it requires a certain big step function. So there isn't a gradual path there. Right? We've all been talking these 2 days, and I guess for years now, about hallucinations and the issues they cause. I'm going to end with one more vignette. This is, again, this is just a different modality. So when there's this whole field of reconstructing models of 3D things from a bunch of 2D images, right? And your MRIs and CAT scans and all of this stuff, right? So there's a lot of good signal processing and math that is used for this primarily, and the goal always is you want to take as few of the two-dimensional images as possible, subject the patient to as little radiation as possible, have your machine occupied for as little time as possible, right? And still get a reconstructed image that is high quality. it turns out that generative AI, specifically diffusion models, are a good way to do significantly better than the traditional signal processing techniques. And so there's a bunch of stuff that some of my colleagues are doing that really has legs. The big technical challenge here is that you're often looking for small artifacts that occur rarely. And so if you're using a generative model, you want to make sure that your generative model isn't going to miss those small artifacts and generate the artifact-free image, because that's the more common thing to expect. I'm going to stop here, and I'll say more in reaction.
Okay, I'm good. I'm not seeing it. So, well, I think I'll start with Amara's law, since you brought it up. And the other reason I want to start with that is because I can set the clock back, because that gives me an excuse to talk a little bit about history. So in 2013, which is 12 years back, Vinod Khosla, the famous venture capitalist and technologist and so on, he wrote an 80-page article saying 20% doctors included. And basically what he was trying to argue is that 80% of the work, this is 2013, remember, so before GenAI and really before deep learning. Deep learning just got started. 80% of what physicians do and their staff do can be done better and cheaper and more reliably by data science and software. In fact, he made a huge statement saying, in 10 years, software and data science, there was no GenAI there, so will do more than entire field of medicine and biological science, which are two huge fields, right? But he was not, well, of course, these are VC people, they always think much faster ahead, right? And he was also putting a lot of money into a whole bunch of healthcare startups. So turned out Amara's law applied, and the initial development wasn't as fast as expected, but now it's really started ramping up. So you're trying to get lunches, which I'm not sure if they're free, but they're pretty cheap, okay? So let me try to, the reason I brought this up is because some of the precursors of what is happening now were actually being set at that time, and we need to understand that both from the technological viewpoint and also from the the processes that the medical, that you just alluded to, the medical industry operates on. So there are some fundamental shifts. One is to try to move from pay per visit to value-based healthcare, where the better predicting outcomes will lead to faster and cheaper treatments, because you're being paid for the not for procedure, but for the patient as a person, a fixed amount per patient. The second major trend was digitization of health and healthcare, and the associated movements like quantified self and the activist health consumer. You want to go to WebMD and then say, hey, but WebMD told me this is what's wrong with me, and then the doctor says, okay, smart Alec, shut down and open your mouth. Okay, so all those things, and I think they've all led to this. And initially, I think one of the reasons the adoption wasn't so, the usual data issues and so on, but also, this is a very mature industry. They're very careful about everything they do. They're very strict processes and so on. So it's not that unless you rigorously prove something, it's not going to be adopted. Okay, so I think there are many reasons, I think, why it didn't escalate so rapidly. And IBM found that at a great loss of treasure and time, that IBM Watson Health could not be adopted as fast as they would think, just purely based on the technical merits of the product, because there were so many other factors at play. But I think with GenAI, several things have happened. There's, of course, the remarkable improvements in image understanding, which I'm sure you'll cover, so I'll shut up on that. But the other thing is, there's this whole problem of data, but suddenly you have a technique where you can understand and digest huge amounts of text. right? If you think about a patient's clinical review, actually the patient's clinical review chart is the starting point for care. And the review chart may go over many years and across different modalities and have great amount of information, right? And the problem is, you can't even, just to extract that reliably and get it into a table is highly problematic. It's not even clear what the table should be. And in fact, many variables in the table may not be useful, may only apply to at certain parts. So for example, the fact that you are susceptible to falling may not be relevant while you're being treated, but may be relevant when you're discharged. And how will you go home? So suddenly that variable becomes, so suddenly, this technology can now reliably extract lots of deep, rich information in a cleaner way from medical charts. Okay? The other thing to realize is that, again, it's all tied to text, and that's why I really liked your positioning that pathology, whatever, they're always notes. But the other thing about things being tied to text is that in this technology, you embed text into a semantic space, right? Where similar texts and hence similar patients, hence similar trials, hence similar treatments, et cetera, can all be mapped to one or a set of latent spaces, right? And then you can try to make connections between these latent spaces. And I think conceptually that's a very profound tool. Why? Because you might be a very rare patient, but still you have a very long medical history. There are many other aspects of you for which there'll be somebody who's similar. But the similar is in a soft sense, of course. You're in a latent space. The same with drugs. I'm from the machine. I actually forgot to introduce myself. So I'm from the University of Texas, Austin. I'm in the EC department, but I do machine learning for healthcare. And so I have courtesy appointment, for example, with Dell Medical School in the Department of Population Health, which is ironic because I normally am not interested in population health. I'm interested in personalized health because we want to predict at the individual level, right? But anyway, that's the department they put me. I did not quibble about it. So anyway, that's my history. So what was I talking about? Yeah. So in machine learning, if you have a drug, you say, okay, this is drug A, you give a class label, or outcome B that has a class label, and then you try to predict the label, right? But if you think about it, the drug actually has a lot of description. It's this whole chemical description, et cetera, et cetera. So there's a lot of, it's just not a label. There's a lot of very rich information. And now, why is that more useful to think about that in terms of that rather than the label? Because now I'm hypothesizing creating a new drug. Okay, I have not done clinical trials on it yet, but I have a description of the new drug. So now I can map it into the same semantic space and try to see from the known interaction of patients with the previous drug and the other drugs, I can try to guess which patients may be recruited for a trial for this new drug, and even whether the new drug may be useful or not, and try to guess its outcome without running any clinical trial. So this is actually a zero-shot clinical trial prediction, right? But these things are actually possible. We've actually done some experiments. I won't go into the technical things, but this was the key idea. And even without hypothetical drug, you have some information about it, and you can make a pretty good guess, even without running it. So I think these are some aspects where suddenly I think this promise, which was made 12 years back, has really become turbocharged. I think the lunch is not free yet, but it's getting cheaper, okay? So I can elaborate many more on this. And then the other aspect is, of course, the various processes, explanation of benefits, interfacing the customer, the insurance part and customers. I've worked with several companies on these. All these various medical processes have also become much better and much cheaper. Even the synthetic human voice, which is now much more realistic, has a huge role in making medicine much more affordable and accessible, even explaining what's happening. So maybe I'll give a last anecdote. So 5 or 6 years back, I went to my physician for the annual, and he has a scribe, right? This is the guy who makes notes when he's talking. And I was seeing what this guy does, and I said, sir, I think AI wasn't popular then, so algorithm can actually do this transcription very easily and reliably, and you eventually will not need this type of a human scribe, right? And he basically gave that look, smart aleck, shut up and open your mouth type of a thing. And that was the end of it. And then last year when I visited him again, I saw that he had a little earpiece and a little mic here, and there was no scribe. Okay? Also, there's much better connection with the medical terms, so things can be auto-corrected and so on. And so clearly it is happening. So, sometimes the technology was there 5 years, 6 years, 8 years back, but it's happening for multiple reasons. One is there's much more pressure on the healthcare industry to reduce costs. There's also much more, because of the hype of AI, it's lifted all boats. So there are many more people who are willing to try it out than there were a few years back. Okay, so with the example, I'll pass this on. Thank you. Oh.
Thank you. Okay, so for introduction, my name is Jasmine Fu. I am a faculty member in the math department here at the University of Minnesota. I am also the co-director of the Therapy Modeling and Design Center, which we started last year. Maybe I'll talk more about that in a minute, but just to give you a little bit of my trajectory, my background is in math, applied math. I started out in uncertainty quantification and stochastic finite elements, stochastic spectral methods. But then sort of quickly or early on in my career moved into mathematical biology and medicine and got interested in developing stochastic models for understanding cancer progression and evolution. Did some postdocs at Dana-Farber Cancer Institute and Memorial Sloan Kettering, and have been working basically in quantitative biology since then. So my research group, one big mainstay of our research program is to develop models of treatment optimization and drug resistance. And this sort of speaks a lot to the themes we've heard a lot about precision health and medicine, precision treatment. And in recent years, we've also gotten really interested in developing models for interpreting and pulling out deeper insights from experimental data that's being generated in novel experimental platforms. So you may have heard about things like organoids, organ on chip, spheroids, microtissues, these sorts of really cool devices. They're all model systems. So we want to take what's happening in those platforms and translate them into actionable clinical information. We need to understand how to interpret data from organ on chip, right? So we've been really interested in applying mechanistic models to understanding when something happens in an organ on chip, what does that mean? What does that mean will happen in a patient? And I think that's a really hard question that speaks a little bit to why I'm here, why I'm interested in this topic. So I think all this is to say, I think in this room, I would be considered a domain scientist. I'm not really an expert in AI/ML, but let's see. Maybe I'll talk a little bit about some of the work we're doing at the Therapy Modeling and Design Center, where I think there's a lot of potential for connection with GenAI. So we are, basically our vision is to apply mathematical and computational modeling to help aid in the therapy development process. And so there's many points along a drug development pipeline in which I think quantitative approaches can help from the target finding, which is a common topic in probably in this room, all the way to optimizing the design of particular nanotherapies, identifying which patients are going to benefit the most, which patients aren't going to benefit from a particular therapy, understanding toxicity constraints, figuring out how to best deliver the therapy. So what's the dosing regimen? What should you combine it with? So all along this pipeline, there are so many opportunities to apply quantitative modeling. And maybe we'll just mention that there's been, a sort of policy shifts like quite recently from FDA and other governmental agencies signaling kind of a shift away from wanting to do as much animal testing for toxicity in drug development. And they're really sort of wanting to bolster things like computational modeling and ex vivo experimental platforms, so these organoids and organ on chip and things like that. So coming back to the connection to GenAI, a lot of the problems that we see in the center have the kind of characteristic that, we've got many different types of data. Maybe we have 2 or 3 different types of in vitro data, so 2D cell culture, organ on chip, organoid. Then we've got multiple model systems, so not human, but we've got mouse data, non-human primate, things like that. And then maybe we've got a small smattering of clinical human data if we're lucky. So huge discrepancies in model systems. Huge discrepancies in the amount of data available in each of these model systems. Basically, the closer you get to human, the less data you're going to get. And one of the things that I'm really interested in is trying to understand what are the commonalities that we can pull out. What are the lessons we can pull out from one model system that we know are going to apply in another model system, and how can we translate this ultimately to the clinic? So, a lot of our expertise in the center has to do with really interfacing closely with the biologists, with the clinicians, with these people who are creating these amazing new drugs, therapies, biologics, things like that, and really understanding, what's at the forefront of the mechanistic knowledge of how these things work, and really understanding from them, what are the design levers? If I'm making a nano ring medicine, what are the things that you can change about it that we might be able to optimize? We want to be able to use these kinds of knowledge to build models that we can then take to optimization and say, okay, well, here's going to be the profile of your optimal design. This is what we think you should try next. But of course, we don't know everything about the mechanisms. And so is there a way to leverage this very, very imperfect data along with these partial and imperfect mechanistic models to put things together and develop principled approaches to figuring out how to best support this therapy development pipeline. So I think I'll stop there.
Hi, everyone. My name is Mahdi Bayat. I'm a faculty member in the Institute for Health Informatics and Medical School here at the U. My background is electrical engineering. My journey in healthcare started with working on non-invasive, basically imaging techniques for non-invasive surgery. And I did a postdoc at Mayo Clinic afterwards, which I went through that Arama's law in a way, and starting with highly enthusiastic, basically from that engineering and scientist mindset, going into witnessing how the actual practice of medicine is performed and how the knowledge and the research basically gradually being translated. into the practice from that small angle that I had and the opportunity that I had. Basically, trying to understand what is that we can do as engineers, as tool developers, and in future or in career development as scientists, as contributor basically to knowledge development in biomedical science and medicine that can actually help patient care. And after that, I had an opportunity to join Case Western Reserve University, and I worked on, I was very fortunate to collaborate with physician, clinician, scientists at Cleveland Clinic and also University Hospital, which is affiliated with Case Western Reserve University. Like I said, my entry into the healthcare has been through the window, basically medical imaging, starting off with creating reconstruction techniques for novel imaging methods, and then gradually entering into the domain of image analysis and most recently deep learning, and basically at the scale. We created these narrow, basically supervised model for specific applications. A lot of physicians created these problems that we have this imaging techniques that create this high yield imaging, but we have no idea how to analyze them and make sense of them because it's really very difficult and the data is prohibitively large for any analysis to be done. I think that was a very good entry point into utilizing these data-driven models into the field. And I really enjoyed the supervision that I received from the clinicians that basically is the problem is articulated, dictated by the physician. It's one of those rare situations that we as basically as scientists and researchers, we find that we grab the opportunity that sure, let's see what we can do. And that was a particular project on imaging of the eye, revealing some of the structures which are very basically crucial for the development of glaucoma and congenital glaucoma in general. In particular, so along the way, you come across a lot of problems that you face. So a lot of the assumptions that we make about the image acquisition, heterogeneity basically, or harmonization of the images, they fail very quickly. Patient motions, a lot of different things can swing basically the data and skew the data in different ways. And that sort of basically helped me to understand what's the domain basically knowledge has to do and has to say in the practice of medicine in general. In going through the full cycle of the Amara's Law, basically, I recovered from that. And now I'm a faculty member in Institute for Health Informatics. We have data, we have hypotheses, we have a lot of ideas that I hope that we can find that sweet spot, the balance basically, where we can make a fair and good assumption about the type of problem that we can tackle and address with the type of tools that we have and the type of data that we have access to gradually basically push this front forward. And I'm highly encouraged to basically the pioneering work by Dr. Poon today and so many other leaders in the field, which I look up to these works, and we would like to build on those. But also at the same time, I would like to bring that critical view that I went through basically and learned going through these major healthcare providers and see how we can basically close the loop and bridge the gaps basically to make them more translational and useful for patient care.
Thank you very much. Would you like some more minutes or should we? All right, excellent. The energy in the room is low, so let me start with a couple of jokes. And I was trying to find this meme, and I couldn't find that meme. So there was a meme that a few months back, or maybe a year back, somebody sent me. It said, in 2015, Bill Gates said, in 10 years, we won't need radiologists anymore. Computers will basically make the job of radiology automated. And then also in 2015, there was a quote which said, this is Elon Musk saying in 10 years, we will have self-driving cars, blah, blah, blah. And the picture was somebody driving in Atlanta somewhere in a 1990 Honda Accord, and it said, and here's a radiologist driving a 1990 Honda Accord in 2025. I thought that was funny. I think the other joke was, as we were talking about this came to my mind. I don't know if you've been following, there was a controversy of one of these GenAI companies, which it turned out had a whole slew of Indians sitting on the other side of their Gen AI, and you type something in, and a gentleman in India would respond to your prompt. This is real. This is not a joke. This is the modern day Mechanical Turk, but the joke part of it, as it came to me, was we were talking about automated radiology and things like that. Well, that's not really different from what happens right now. I mean, we have a radiograph. It goes off to India or some other country, and that's at night. That's day there, and a whole bunch of doctors sit and write a report, and the report shows up here. Now, that is a Gen AI model for all we care, but it is intelligence. But nevertheless, two jokes. So let's start with the question. So the first question is, how can Gen AI be used to generate new scientific hypotheses in biology, validate candidates? But I think the essence of this question is that disease by its very nature is rare. Individuals are all different. We are not all the same. If we were all the same and diseases were all generic, this would not be a major challenge. So the key challenge, in my opinion, in biology is how do we model pathology that is not the norm? By definition, it's a pathology. And then how do we do it in a way that's patient-specific, which means that it is not the norm. We are all unique. So the question, there's a zeroth order challenge. Yes, how can we characterize a nominal pathology? We can do that. How can we come up with a cure for a nominal patient? We can do that. But the crux of this question is, how do we incorporate the rare event and the unique aspects of individuals? And we can keep it short, and we can open it up to questions as well, if anybody wants to take this question.
So I think that the rare pathologies problem is not unique to medicine. I think that we've heard that same thing in multiple contexts over the past 2 days, field after field. I see people nodding, so I'm not going to say more about this. I do think that the overall population versus individual is a very important distinction and is one that is not often enough made in the AI community. We build models and we evaluate them on an overall error metric aggregate. And what we seek to do is to be right more often than we're wrong, or to be right most of the time. And in a number of cases, patient care being one very clear case, but wherever humans are involved and there are human consequences to decisions, we care very deeply, or at least particular individuals care very deeply about exactly what happens in that one specific instance. And the error metrics that one needs to apply for models to work in these circumstances, I think we just need to think about what that is. There's all kinds of stuff that I've seen in terms of fiddling with the error functions and using the same crank in terms of designing AI models, and I don't think I think that helps, but that doesn't quite get us there.
Maybe I will add a couple points. When the Human Genome Project first concluded, right? They basically tally all the mutations, and then the result is actually somewhat disappointing, at least among a few folks, because the head torso, the head portion, right? The most frequent one are all the oncogenes or your tumor suppressor that everybody knows, right? P53, yeah, of course, right? KRAS and blah, blah, blah. But then the really frustrating part is that there is a giant fat tail of all those variant of unknown significance. Like, what the hell do they do, right? So are they actually contributing to the cancer? So I think actually the underlying challenge is actually representation, right? So that's actually why in cancer, this cancer hallmark is such a powerful concept. Basically they said, hey, maybe cancer target, there are 3 billion base pair out there, so many target, right, that cancer can work on, but they are not random. Right, so they are actually organized because biological processes are there are lots of modularities and components, right? So then if you look at the cancer hallmark started with 8 and now 12, and you may add to 20, still a very small number, right? And those mutations, so this lead to also the concept about genetic pathway, genetic network, which means that cancer may be targeting, if you look at the representation and the mutation level, they may look very, very sparse, right? You may call it it's rare. But when you look at actually the representation of like module, functional module, pathway, network level, then suddenly they are not that sparse, right? So then, of course, the challenge then is that how do we do this representation learning efficiently, right? So in the old days, and obviously like back 20 years ago when I started in NLP, we joke about we're basically manual feature engineers. Then we pass on to an optimizer, right? Convex optimization ruled the world at that time, right? So, but then what I think a lot of the Gen AI, starting from deep learning, actually what they do is that when the human manual engineering start to break down, when you have giant dimension, when you have lots of missing data, when you have lots of noise and biases, then that manual kind of engineering become difficult, then that's actually when GenAI can try to automatically start to uncover some of the connection underneath and learn a much better kind of representation, right? I always think about like GenAI basically is doing a glorified PCA, right? So it's a nonlinear dimension reduction, but that's fundamentally what they're trying to do.
Yeah, and I think what I would like to add is in medicine, things are seen holistically and not individually, right? And that's one dimension. The other dimension is there's a lot of redundancy in diagnostic medicine. Like if one physician or one diagnostician basically is not sure, it passes on to another diagnostician basically, to another colleague, to someone else, get another opinion. So there's this basic notion of refinement at different stages and multiple basically, the redundancy that we see in commercial jets, for example, that you have so many backup systems that if one fails, the other one takes over, the other one takes over. And there's hierarchy of these, right? Because the task is so essential. You never ever want a commercial jet to fail, basically. And for the case of human health, it's the same way, basically. So if we want to brute force a single model with fixed parameters, basically one size fit all situation to address this and capture that rare case, it's doomed to fail. The only way to do it is to basically to forget about this assumption, to put this assumption away. Models have to become flexible. Models have to be more redundant. Models have to allow basically an opportunity to be tested from different angles, so those rare cases can kind of eventually be sampled and eventually be seen by the model.
You should feel you have to, Jerry. By all means, your opinion is very valued, but we do have 8 questions to go through. But please.
So I want, okay, let's see. So yeah, there's the representation, and I think if a holistic view of a patient's record, then you have more flexibility on focusing on the right representation, because something that looks very rare, is quite likely also showing up in some of the other part of the medical record. The other thing I wanted to point out is you can see something unusual. The standards by which we can mine the medical literature, which is extensive, has taken a quantum leap in the last 3-4 years. There are a couple of papers on that. Most of them involve a human in the loop, but you can do that, and you can try to search for evidence of some other patients in some place long time back who had something similar. And I think that's a great new tool that has come up as well. And finally, again, a human in the loop story I read recently from Mayo Clinic, which is nearby. So pancreatic cancer is number 10 in occurrence, but number 4 in fatality, because it's difficult to detect it early. So what they did is they found out people usually they get detected in 4th stage, which is pretty late. But they went back, and since they had lots of records of CT scans in the past, they would go back and look at CT scans 2-3 years back, and which were flagged as okay, but now they know that this guy actually was detected later on. So they relabeled them, and then now the classifier can focus on these things that were missed earlier on. So there were also those aspects which are helping us capture more rare events.
Any questions from the audience before? Please, Professor Shaker.
Thanks. So one of the issues that ARPA, Edge, and others are bringing up in this space is distribution shift, right? Because our patient sample is a small fraction of the population. But once you build the model on that data and you're seeing new patients, you start to see slightly different distributions. And I think they wanted us to figure out, is there a way to monitor that your distribution has shifted from learning samples to what you're seeing today within the same hospital. Obviously, if you go across hospitals, there are other kinds of shifts which have been explored. So, but I just wanted to come back in the GenAI context. How do you think about these distribution shifts within the same hospital or across hospital? And how can we monitor, if our models need to be retrained or adjusted to maintain their accuracy?
I can start with my perspective, and maybe our panel can add to it. I think the problem with distribution shift is a subspace within which that shift happens. So the idea is, if you think of our representation in 1,000 dimension, most of those dimensions have a nominal shift anyway. I mean, there's enough noise in our nominals that you will see noise everywhere. But the signal in a distribution shift will happen in a subspace of dimension 7 inside of this dimension of 1024. But it's a very statistically significant distribution shift in a very small subdimension that is hidden in a very large, noisy dimension. That makes the problem particularly interesting and challenging. I will let our panel add to that.
Yeah, so that's a great question. I think there is probably at least two kinds of shift, right? So one kind is like, as you talk about like a regional, like if you, I mean, AI is no magic, right? So if you force it too hard, it will just hallucinate, right? So if you have only see one patient, I mean, good luck with the generalizability, right? So I think and that problem is partially social challenge, right? It's like, can we figure out appropriate social construct with privacy, compliance, and insurance, and all those points that you guys have talked about to make sure that, actually using the real world data that patient actually and the voters are in, right? So then, I mean, there is no fundamental reason why there couldn't be a learning from all 8 billion peoples, right, except the social contract, right? I would say that's one challenge, which is like, did you subsample enough of the patient that actually, so that you can generalize, right? And then I think there is another, perhaps even more interesting distribution shift is over time, right? So actually I learned a bunch from hydrology about how the terrain change and all this kind of good stuff that actually changing the game, right? So I think like, for example, there is a lot of study to show, like, for example, some of the cancer happening much earlier, right, with younger people and so forth, right? That I think a lot of that would also change with a lot of the for example, how do we diet, how do we exercise, and so there is also a temporal change there. And then I think another one, which is I mentioned about the AJCC staging guideline, right? So they are, I think, up to 11th or 12th edition by now, right? So you might have staging. Let's say in December 31st, this guy should be 3A. After the new year, it should be 2B, right? So there's also some of those kind of like maybe somewhat artificial kind of semantic drift. So I would say there are very different kind of the drift. The regional drift that I think you talk about, I think it's fundamentally really a sampling challenge, right? It's like if we do sensors, if we do survey, if we don't have enough sample, then of course AI doesn't have that much magic. You can do representation learning and so forth to hopefully ignore a lot of the spurious kind of like stuff, but still there is an extent. You can extend the generalizability. I think the temporal and other things are also very interesting challenges.
Please go ahead. I do want to make sure we get through all of our questions.
Okay, so I'm just going to quickly say that I think that we actually need to modify how we think about the problem. I don't think the problem is one of distribution and distribution shift, which are aggregate measures. Even if we had samples from all 8 billion people in the world, we would worry about very small minorities who have certain genetic characteristics, for instance, that might be very different, maybe some isolated small tribe, things like this. Even if they were in our sample, it isn't clear that they would be properly represented in the model. And so we really have to think about, is there enough in the model to cover the particular individual, new individual who shows up?
I think at the core of this is the model explainability. That has to be, in terms of healthcare, has to be encoded into the model, it has to be completely transparent, it has to be basically one of the main features up front. I'll give you an example, like if a data set is taken from X-ray in one hospital, which happens that the prevalence of certain disease is really high in that hospital. Another model is trained on an X-ray technology, in different machine, and the prevalence of the disease is pretty low. If the models are swapped basically, and then one model is being, and these two technologies are slightly different in terms of noise or some other imaging contrast or features, it's very likely that the models basically just learn those more overlaying features as opposed to the clinical features that manifest the disease basically, and might collapse and fail or might basically create false results. Or in the case of COVID, for example, the model trained on pediatric lung cases versus a model which trained on adult cases. In pediatric cases, the reaction was not really as severe, and in adult cases were severe. So a model that sees a small lung would immediately says that this is not a severe case, without even basically seeing if there is any extensive reaction. So there has to be a way to explain to the end user, in this case the clinician and the physicians, that what is that the model is basing its decision or basically output on, to then create that kind of explainability and trust.
Thanks, Mahdi. And we're going to be, let me move to the next question simply because, and we'll come back, Sudarshan. We will have time for So let me quickly move to the third question as well, second question, because the third question sort of touches on all of these issues as well. So let me set this third question up. And I think, as Mahdi said, there was mention of Mimic-4 at some point. Mimic-4 is primarily from East Coast hospitals. East Coast has a certain population demographic. You can build a model on Mimic-4, and you can build a model from Texas, and you'll probably get two different answers. And that question sort of hints at it. But basically what that question says is that a model that is 95% accurate on a cohort is not 95% accurate on an individual. In other words, you apply a model to a cohort, you say with 95% accuracy, I can predict that whether somebody drawn randomly from that cohort is going to have a certain disease or not. Yet, if you give an individual the model an individual, the first result doesn't mean that the model is going to be 95% accurate for that individual. We can go into the depth of that question, but nevertheless, I think most of us understand what that question is. That is a big problem, and that problem gets in the middle of a lot of things. If you ask me, should I accept a model-based diagnosis? As a scientist, that would bother me. I'm an Indian. South Asians are more predisposed to things like triglycerides. If you take somebody of my height and weight and that person was Caucasian, that wouldn't even be a concern for them. So how do we make sure that whatever we're doing, which we are building population level models, have anything to do with individual level pathology or diagnosis or care? Please.
Yeah, so this is a really important question, and I actually don't think that it's specific to GenAI. This is a question that has been, sort of plaguing the field of, how do we choose clinical trial objectives? How do we, choose treatment optimization objectives? What's best for one person is not necessarily the same as what's best for the cohort or what's best for a particularly vulnerable population. And there are even other sorts of versions of this problem. What's best in the short term is not necessarily what's best in the long term. That's something that we see a lot in cancer therapy. You don't always want to go for maximal tumor reduction right when you start therapy. you might be better off keeping this thing around for a long time because it's more likely to stay under control under certain situations. And then bringing in economic, what's best for a patient's, length of time without progressive disease is not necessarily what's best for, insurance, pharmaceutical companies, things like that. So I think a lot of these questions, have been thought about in other settings, and maybe a lot of them kind of veer a little bit into, policy and economic decisions. But I think as sort of like practitioners of, people building models for individuals, for populations, for practitioners to use and think about, I guess, my personal opinion is that, it's our job to be aware of all the different possibilities for objective functions and to lay out all the options for people who are making these decisions.
Any other thoughts? Excellent. Oh, please.
I want to also add on to say that important part of is to how do we represent uncertainty, right? Because like everything in biology, right, is a probability game, right? So you take a drug, the molecule, how does it metastasize? How does it, whether you bind to a protein or not? That's all probability game. So I think one thing, but that's actually something that it's a little bit hard for during our evolution, right? Like it's that kind of uncertainty modeling, not necessarily especially for the longitudinal, long time scale, that's not what we intuitively would be doing. So I think that's probably really important when we think about, let's say, a virtual patient or something, right? No matter how accurate they are in the kind of like raw accuracy sense, there are actually still uncertainty remaining. And I tend to think about that, that's sort of like the uncertainty could vary in different patients, right? So and for certain patients, the prediction can be very, the confidence window can be very small, but for some patients, the confidence window is very, very large. So how do we even kind of reason about those uncertainty quantifications, and how do we represent them? How do we actually get the model to calibrate? GenAI will always give you some numeric thing. Whether you can trust that to be probability, that's a completely different thing, right? So how can we calibrate that?
So I think the answer here is that introspection is a very important aspect, and maybe we should think of introspection more in models. Let me quickly come to the second question, and I think the essence of the second question is as follows. So if you think of how we have, biology is a very data-rich field. I mean, there's tremendous amounts of data, but that data is on a canonical organism. It could be on a model organism or a canonical organism. When we sequence an individual, it's an abstract human that we're sequencing. It's not my sequence. Now on so there's a wealth of data that's sitting in different databases. Now separately, there's a very sparse sampling of me as an individual. Yes, maybe I have, somebody took my temperature, my blood pressure, 5 other measures, maybe my blood work. But that's an incredibly sparse sampling of me as an individual, as opposed to all of this rich data that exists as a canonical person. Now, if you want to think of what is wrong with me as an individual, how do you build a model of me as an individual from this very sparse readout that I'm getting and this very dense set of data of a canonical individual that I have on the side? So in other words, if you're building a digital twin for me, how would you go about building that? And it's perfectly okay to say, hey, this is a ridiculous question, or this is very hard and we'd rather not talk about it and move on.
I think the goal number one should be, in order to design an end-to-end system which can address the final question of addressing basically those rare situations or the situation that we don't have enough data, we should build on the capabilities of some of these emerging models like foundation models to create soft outputs as opposed probabilities or soft outputs as opposed to the final decision, basically. Because the whole change of decision making in healthcare is more complex than just the correlation that we can tease out from basically the training model that we have. It has to go to the causal sequence of reasoning, basically, that what is leading to what. I think the first help or assistance or to leverage basically these models, to leave it at that soft output level, or at most create those probabilistic outputs that can basically then inform a physician to which direction basically they focus more. Is in case of multimodality, this could be an aggregation of several embeddings basically. One of them can stand out. For example, gene mutation basically has a lot to say, but the distribution is significantly different from analyzing the pathological basically slides or histology that has been observed over so many basically the slides or so many basically time samples. Yeah, I think that is one thing that I can think of immediately of.
And I think that kind of answers the last question as well, which is how do we design loss functions that are explainable in some sense? Professor Kumar.
I just wanted to go back to the previous question, and then you sort of said, well, does it make sense only in this context? You know, and I think what's most. Is it okay? Yeah. Is it okay? Yeah. So what I'm finding most amazing is that the question being asked in one domain actually resonate in a different domain. So as I was listening to you pose this question, I could sort of think of the presentation by Paul from yesterday. There are a whole bunch of lakes, millions of lakes. You understand the different processes, you study them in limnology over decades and decades and decades. But given a specific lake, you're trying to figure out, is there a lake hypoxia? You know, for this one, what's causing the oxygen level to go down and the life to not survive? That's the specific lake that you're interested in because that's in your backyard. And how do you bring in knowledge of all the different processes to bring to bear? And of course, here you're talking about soil processes and then the vegetation processes. Over there, you're talking about cell processes. And in some cases, you have physical knowledge, biophysical knowledge. Some cases, you only have data, perhaps, right? But I think this question is perhaps a abstract question, potentially could be asked in many, many different contexts. And I think one thing that I'm hoping through this dialogue, which is very unique in the sense that either you go to GenAI meetings, AI meetings, where everybody is methods-oriented person showing their cool methods on specific problems as an illustration, or you're going to different communities where they're so steeped into their own discipline that that's what they study. So I think this meeting is what helping me, and I am hearing from others as well, that they're seeing these connections across different domains. And my hope is that through these connections, through these kinds of questions that are being asked, you know, on your panel and of course many others that we have seen, maybe we can abstract out some high-level questions or model problems or model formulations that could help us drive this entire field. And it reminds me of how in the 60s and 70s, when the computer science was in infancy, it was like you can write a program and it works, right? You know, just like GenAI model and it works, right? You know, of course, what worked 60 years ago is very different than what works now. The scales have changed, but the level of lack of structure that we had in 50s and 60s dramatically started getting reduced by the 70s, when people started building up this abstractions of algorithms and data structures and problems like traveling salesman and shortest path and minimal spelling trees and sorting, and people then figured out how do you take those problems and build formulations for them. And of course, the formulations that we're going to think about today for GenAI are going to be completely different. You know, it's a very, very high-level problem. And through some of these questions, my hope is that perhaps as a group, as collectively, as people talking to people from different disciplines, we figure out what are the abstractions that we need to pay attention to. And I see at least one abstraction in one of your bullets here. That's number 3. And I think there were other ones that came up from time to time.
I think Jack also mentioned the rare events, and I think Hoekong mentioned UQ and
Exactly. And the other dichotomy that beautifully Hoekong
showed in a slide was productivity gains versus, what was it, discovery gains? I think they were creative gains. And I like that. See, these are not the kinds of things we were talking about 5 years ago. Today, I don't think we would come up with this kind of distinction. And today I can sort of see, I can see how somebody could become very productive using the kinds of patterns that generally exist. I don't have to worry about, for the productivity gain, what happens rarely. I'm focusing on things that happen very frequently, right? Now, for the creativity, whether rarity is a plus or a minus depends upon whether you love hallucination or you don't. In some cases, having hallucination is good because it makes it more creative, and maybe one of them would help you discover a problem. I saw that, I think, in the manufacturing panel. I think it was Devesh Bhatt or somebody who sort of talked about the fact, well, maybe right now we are reactive. Something goes wrong, and then we try to go diagnose it. Well, if I had a whole bunch of hallucination, it doesn't matter, 99% of them are bad, but if even 1% of them help me diagnose a problem, I'm a winner, right? As opposed to, in some cases, you don't want any hallucinations because, so these are the kinds of model problems or model situations. I don't even know what the vocabulary is. I think if we can come up with, I think we could potentially advance the field beyond saying, hey, it works, or it doesn't work, right? You see yourself see things saying, this thing works and this thing doesn't work, and I think we got to go beyond that. And hopefully this workshop is helping us taking a small step toward the direction. So I like your question when you sort of said, well, maybe I should move on. No, you don't move on. When I looked at Paul and sort of say, look, this looks very, very interesting to me.
Yeah, thank you. I think the concept of abstractions, most of the time we discussed today, I think you guys are all expert. I'm not a healthcare guy, so I may be asking something very fundamental. Cancer has been talked quite a bit, but coronary diseases like heart diseases and gastroenterology issues, and also there are something called orphan diseases, which we don't care about in this country, and also communicable diseases like malaria and other things. What do we learn? What are the canonical set of issues across all of this? I know that this itself is a difficult problem to solve in one disease, but if you're going to go disease by disease by disease, we'll be just chasing them. Is there something beyond, because we are talking about hypothesis, scientific hypothesis. What is the canonical set of issues that cuts across all these diseases, and how we can generalize these abstractions to that level? Because if you're going to spend so much of money and effort in solving cancer, and that too cancer of a particular organ, okay? But cancer can happen everywhere. And then how do I generalize it to heart disease? How do I generalize it to other issues? And especially malaria kills more people across the board. And what do we do? In fact, Microsoft has the malaria issue. In fact, my daughter worked on malaria research for her PhD. So my interest is, are we going after some point solutions for diseases or something bigger? So that's the idea.
So I'll start with my 2 cents worth, and then I'll let our panel chime in. So I'm a computer scientist, much like half the people in this room, but I dabble with NIH quite a bit. So I think broadly you can think of diseases in the form of inherited diseases. These are mostly diseases of the gene. Degenerative diseases, these are diseases of use and age. Infectious diseases, these are diseases that we catch from each other. Maybe there are a couple of other categories. And I think there are mechanisms that are common to these. So for example, infectious diseases, you almost immediately start to look at the immune system. I would almost argue cancers are in some way degenerative. You accumulate enough mutations and bad things happen. And once again, you think of how interventions, immunotherapy is probably by far the most promising approach right now, but immunotherapy has got issues as well because certain cancers don't respond to immunotherapy because the microenvironment becomes very immune hostile, so prostate cancer doesn't cure very well with immunotherapy. And then you start looking at models of how do I make the TME of a prostate more immunocompetent as opposed to immunohostile. So immune system is sort of basically probably one of the big mechanisms by which we hit a lot of these diseases, communicable diseases. Okay, I will let the panel chime in, and I'll come back and
Yeah, I really love this question, so I can't resist to take a step. So I think what you asked actually is a really all-encompassing question, right? So because when I think about it, like, it actually really touched on multiple things beyond just AI, right? Like, for example, you talk about malaria. That's actually a semi-solved problem in the sense of technology, right? But it's just like, you know, we have to get the medicine or in general, think about all the preventable disease, right? Like, why do we have, you know, some of the disease that are completely controlled by vaccine in the past and now suddenly, you know, blooming up, right? Like, those are not technology problems. Those are social failure, right? So I would say there is one big part of that, right? Like, for example, in some of the, you mentioned about malaria, and obviously that's a personal passion for Bill Gates, right? So his foundation spent a lot of resources in like African, right? So I kind of dabble, sometimes chat with those folks. And oftentimes, some of the most high-order 80-20 problem is like to get them a clean toilet, right? To get them a pharmacy, right? So to get them clean water, right? And then next order of importance would be then get some preventable like vaccine or HIV prevention, those kind of good stuff, right? So that probably is one big bucket of thing. You mentioned about cardiology, right? The reason I'm sort of like, I personally, I'm afraid to touch it is because a lot of the intervention would be behavior changes, right? It's less about, you know, I mean, obviously I can't sometimes still resist drinking Coke or sugar waters, right? So I think those are a little bit different. And when you think about cancer, actually, in the old days, cancer actually are viewed in completely compartmentalized, right? Like famously, like lung cancer doctor don't talk to blood leukemia doctors, right? And only when we start to discover the genetic foundation, then suddenly you start to have all this pan-cancer, FDA approval drugs and so forth that target mutation rather than target the organs, right? So, but I think as you mentioned earlier, there are also still like organs still dry because the microenvironment is still shaped by those organs, right? So it's kind of really fascinating multi-scale problem. I think it's like when we think about disease, it's like maybe there is a very high level that unifying a lot of the diseases like our normal functioning just get perturbed, right? But then when we start to drill down, it's sort of like almost like hierarchies, a multi-scale problem, and also the time scale is very, very different, right? And also, I think I completely agree with what you said. It's like we shouldn't just build, let's say, imagine if tomorrow we have an 8 billion patient journey, right? We shouldn't build a module like just focusing on cancer, just focusing on cardiology, just focusing on diabetes. That's kind of like often the currently, I would say venture to slightly overgeneralize is that currently we have this mentality of a little bit like divide, divide, divide. That's why like a lot of the clinical trial end up having very little participant, right? But I think what potentially this kind of representation learning and GenAI can allow us to start to go beyond those discrete, like let's say 10,000 ICD code. Let's stop thinking about just as a 10,000 separate, completely separate thing. Can we think about them as a continuum, right? In the latent space, I think many speakers talk about, right? In the latent space, they are actually a continuum. There is actually lots of connection. And then that will be, and for example, like you mentioned about cardiology, right? So cancer actually right now, a big problem is that the cancer drugs are toxic. It damages the heart, so cardiotoxicity become a problem, right? In the old days when patients only live for 6 months, you don't worry about that. But now they can live for like 10, 20 years, then that become a major issue, right? People have died of a heart attack rather than cancer. So I completely agree, like we really need to have a holistic way to model all the comorbidities and so forth.
Just if I can add, when you talk about malaria, I know it's a question of social thing, but the drug resistance malaria is one other issue, and also overuse of antibiotics. In fact, in AAAS meeting when Ram and I were there, the person presented about what the biggest problem that is going to happen in the next 5 years in the world is the antibiotic resistance drugs, and then it's going to come and hit us very hard. So anyway.
Thank you, Sudarshan.
Just in the interest of covering all the issues, I'm going to merge those two questions. So both of those two top questions have to do with the role of priors and what does bias and confounding variables and uncertainty do in what is obviously very, very high dimensional data. So let's, if you might have any thoughts on how do we incorporate meaningful priors into AI models. So it's not, I mean, yes, I can build an AI model that's going to classify something and say you got a certain disease, but that doesn't make any sense because there's not a statistical significance associated with that prediction. That statistical significance comes from the prior. Caucasians don't get sickle cell disease. So just because you can predict with 95% accuracy that somebody doesn't have sickle cell disease, it may mean absolutely nothing because the occurrence of sickle cell disease among Caucasians is less than 1% anyway. So the question is, how do we make AI tools to be a lot more prior aware in some sense, quantify their own statistical significance in addition to the prediction, and perhaps be aware of bias and confounding variables and uncertainty in both the measured variables and in the outcomes.
I think when we're talking about the confounding parameters and other basically factors influencing the output or the decision of a model, we're getting into the decision support, basically part of the medicine, where you have the feature space that is coming from different modalities. Now the decision has to be made. And there are so many confounding parameters, basically. Someone in basically an elderly person has lost basically bone density, has received certain therapy, which then make them more prone to fractures or bone health issues. And now there's something that's suspected, basically. Should we factor in the osteoporosis, which is happening in the background, or the certain therapy which might have accelerated certain processes? I think this is, again, lends itself in more on the decision support part of the, which is, it has to be integrated within the basically the clinical diagnosis of the disease versus the predictive power of the model. And the model should not be brute forced in all cases to incorporate all those confounding factors. My take is a model has to do what is built to do best. Incorporating those confounding factors, which are not going to be sampled enough, which is not going to be basically built into the system, is really something that might not be even feasible, at least at this stage. As opposed to that, again, creating these multimodal systems, which each of them can do their job the best way, and incorporating with other parameters, confounding factors, to then build that more robust decision support, I think, is the way to go.
So Madi, let me be adversarial here, simply because I enjoy this. I mean, of course, I have incredible respect for what you just said, but let me play the devil's advocate here. I would say that no AI system is useful without some strong basis in the prior. No prediction makes any sense unless you tell me whether that prediction is statistically significant. And you can't make that prediction without considering both the confounders and the priors.
I don't disagree. But we're getting into the domain of basically decision-making and the probabilistic modeling, incorporating the priors into creating those probabilities. So, and I'm sure that you can, you agree with me that the correlation that we're getting doesn't mean causality, basically.
Well, that's a whole different problem. We haven't even gone to causality yet. We haven't even gone to the Bayesian world yet. I'm saying, can we at least get to the Bayesian world as opposed to the causal world?
I don't think I disagree with you on that. I fully agree with you.
Okay, good. Jedi, please.
So apologies for changing the direction, but I just realized, talking about probabilities, that if I don't leave in 3 minutes, probability of missing my flight will shoot up. So I just wanted to quickly go back to the out of distribution question, because I think people may not realize that in healthcare there's a meta level out of distribution problem, which is very critical if you're trying to build any commercial product. And that is, if you just move to a different hospital, the schema might look a bit different. The rules for making annotations may be different. The instrumentations might be different. So nothing else has changed, but you just move to a different hospital. And suddenly, it's out of distribution in a meta way. And if you have a commercial product, you have to deal with this. Otherwise, you can't scale. Every new engagement needs a lot more time to get going. And right now, they're being able to tackle it by moving everything in representation space. So even though the schema is different, you can actually now infer across multiple tables with different schemas. Even the columns don't match. You can still do it by moving in the latent space. And the second thing you do is to have some human in the loop, like nurses and so on, to occasionally. So I think those are, and I think these two methods are also relevant to tackle these.
Yeah. So let me just take the last question in the interest, and 5 seconds. What is fairness? What is a measure of fairness? And just in an analytical sense. So yes, outcome fairness is, I could argue, is not a good measure of fairness. Do you know of a measure of fairness that you believe would work for an AI model? Good. So the answer is we don't have a universally accepted measure of fairness, which is a challenge because without a measure of fairness, you can't define compliance. Without compliance, you cannot get tools certified. So that is a challenge that we sort of have to deal with here. All right. I would like to thank our panel. Wonderful, wonderful insights. I learned a lot. Thank you so much.
Very simple banner. All they can say is we don't have money.
All right, guys, let's take the seats. Hello, we get started. All right.
All right, please return to your seats. We're going to get started. Thank you. So we'll get started with the federal investments in AI panel. And because this is about investments and we all want money, I decided to use the green color for the title of each slide, hoping that would induce our agencies to give us some greenbacks to talk about, to execute on all the research that was discussed here yesterday and today. So we have a distinguished team of 5 panelists. Raja Acharya from NSF, Raju Namburu from Army, Nikunj from NASA, Sudarshan from DOE, and Ram Sriram from NIST. The panel is going to be discussing these 5 questions. And we have about 40 minutes that is allocated for the panel. So I would read out each question and then leave the panelists to make comments about it from the perspective of their agencies for 5 minutes. And then we'll entertain a couple of questions from the audience, and then we move on from one question to the next. Sounds good? Before we get started, one caveat that the panelists here are in their personal capacity. So do not take anything that they say to be the opinion of the agency itself. These are their personal views based on their professional experience. It allows them to be a lot more free and help us understand how the thinking might be in the future. So let's dive right into it. So the first question is about the reflection on the AI action plan from the White House. So the recently released plan outlines a national vision for advancing AI. I'm sure all of you have read it. So from your perspective, what aspects of the plan are most relevant to mission-aligned science and engineering research from the vantage of your respective agencies, and how might they shape future directions? You could go in any order and pass the mic around.
Yeah, I'm most excited by the AI-enabled science. I think the NSF, DOE, NIST are given the edict to promote AI-enabled science in material science, chemical biology, neuroscience. That's very exciting. World-class scientific data sets. Essentially, they're trying to specify a minimum quality for data sets, and also are interested in pushing controlled access to federal data sets. So this is very exciting. Making HPC AI infrastructure available to the scientific community. Examples of this from the NSF point of view is the National AI Research Resources. And recently, today, they announced the Allen Institute is awarded with NSF the NVIDIA in order to study the AI models and solutions to the tune of, I think, 150 million. It's part of the mid-scale AI infrastructure. I am very positive that AI infrastructure is going to be a very important part for NSF, and I think along with other federal agencies.
Yes, so certainly the AI-enabled science is a big interest, but also the science of advancing AI is of great interest to us. Of course, the AI-enabled science is maybe more of interest since our domains include sciences, several of them. But we do have a few programs that are also interested in advancing the science of AI, not at quite the basic research level that, let's say, NSF is, but a little bit beyond that is certainly of great interest. And also the data sets and facilitating AI use for them, especially in areas like earth science. NASA has a ludicrous amount of earth science data, and we have a whole program that really is devoted to try and making those data sets more useful for everyone. So certainly AI is going to be a big part of people's use of these data, and so enabling that is important for us as well.
If you want to specifically talk about the AI action plan, since it was released, it is coming down the pipeline. It is also related to some of the gold science standard document that was also released. So with respect to what we have been doing in DOE, I don't know how many of you are familiar with the DOE as an organization structure? Many of you familiar, not familiar, so that I can, okay. So DOE, most of the work is done through performers, mostly the national labs, DOE national labs. And then we also have various programs through funding opportunity announcements, which are slightly bigger in terms of dollar terms, so a few $100 million, something like that. And then we have public-private partnerships, which are manufacturing USA institutes. And we also have something called research hubs. So, for example, we have a critical material institute hub to understand what are the issues with the critical material. And we also have water issue, desalination issue. So each of them are using, I would say, how those things are actually propelling AI to the things. It's not like we are going to solve all the problems with AI in that. What are those issues that are relevant for AI? Where are the data-rich environment in that? And then how do we use that opportunity there? So that is the first one. And in terms of AI bigger projects to manufacturing, especially, we have a lot of programs on AI for chemical industry and continuous process industry. We also have in fact, many of you may not know that we do a lot of work with the FDA related batch processing type of thing. But with respect to the AI as algorithms, AI infrastructure, high performance computing, Office of Science is the major focus there. Many of you are familiar with the OSCAR, so they do that. We also have a program called High Performance Computing, HPC for material innovation, and also HPC for manufacturing. The idea is to provide HPC infrastructure to companies to make use of that and solve problems in that area. But the idea is not just nobody can use HPC infrastructure every day. So we provide an opportunity to see what kind of problems, class of problems require that level of HPC, and then see what kind of model reductions you need to do so that you can continue to improve your. The other thing that we are looking at in AI and GenAI, in fact, the meeting is going on right now in DOE about how to use AI for GenAI for the entire process of what we do. We do workshops, we do stakeholder engagement. Based on that, we write what is called funding opportunity announcement. And then once we do that, then we release that. There is a selection process, and then the program management aspect comes in. So we need to, I have to work with every performer on a weekly basis. What is the milestone? Where are they going? What is the missing, etc. So we want to connect the entire thing. So that is the general idea that they are trying to do, to see what we spend, why we spend, and how that is actually measured. What is the impact of that? And the other thing, one of the biggest problem for us in the government is, why do you need public money? Why do we need to fund certain areas? why are you picking winners and why are you choosing winners and losers, etc. So they are trying to see how we can have a traceability of our funding to the impacts it made. So how AI and GenAI can help so that this is the impact that we are making and why that impact is actually relevant to US, and how scaling up. One of the problem is lab level things are all fine, but the scaling up is a big, very, very, very important thing. So they are looking into that. So it's a kind of multiple scenarios there. They also have NNSA, which I don't get involved, but there is a lot of work going on in NNSA. I don't know how many of you are familiar with something called small modular reactors, SMRs. And there are a lot of work going on in that in terms of digital twin and applying AI and all that stuff there. So that's the kind of bigger picture there.
Okay, I'm Raju Namburu. I work for US Army, but I participate in a lot of DoD panels and all, maybe certain things. I'll talk about a little bit from a DoD point of view. And when all this White House plan came, I think sometimes the plans can be there. If the money is not there, we cannot talk. But one good news right now is NDAA, National Defense Acquisition Act. This usually goes through House and Senate, and then it gets into funding for the DoD. And for 2026, I think DoD is expecting about 900 million plus, or billion plus, I'm sorry. So in that one, they specifically mentioned generative AI for national defense. They want to invest money for that. Initially, they want to go about maybe 2 to 12 kind of different areas. They just want to look at them. Maybe I can talk a little bit about what is they're thinking right now. So they want to really get engaged with generative AI. It may mean different things to different communities or different, when I say community in the sense like it could be people who are doing little physics kind of a thing, or maybe on the battlefield the soldier is doing something, or a combination of things. So we are expecting, I think this came up, and we need to start working maybe once 2026 comes to have some plans of what is this supposed to be. And then we may have different meetings trying to get different experts from different fields to really establish something. That's what usually the process goes on. So, but the good news is there is funding for generative AI is going to come. And within the same thing, I think there's a big push already going from last 5-6 years on the digital engineering. When you mentioned digital engineering, all the way from design to build to test and redesign, what are the whole process, including maintenance. They collect a lot of data on all the DoD vehicle systems or any kind of systems and all. So they want to get that into more of what is that AI can do to help that whole process of digital engineering. So please stay tuned. I think things are going to come out, spell out a little bit more clearly of what are the areas we are looking for.
Okay, thank you, Raj. Again, I'm Ram from NIST. So the National Institute of Standards and Technology, NIST, used to be actually National Bureau of Standards before, then I became NIST. It's not as rich as other organizations around here. It's only $1 billion organization, which is 10 versus 10 to $40 billion organizations. But we actually have two kind of things around in NIST. One are the laboratories which do research work, and the others are the NIST the Advanced Manufacturing Office and the CHIPS Office, who are the ones who kind of give large grants. Some of you are involved in the SPOT USA, which is actually a CHIPS grant. And the Advanced Manufacturing Office has also put out something called a NOFA for AI in resilient manufacturing systems. So they'll announce sometime, depending on what the political situation is. So the thing here is that I belong to the labs. So we do a lot of R&D kind of works along with the lab. And I belong to a lab which is information technology lab, and they do mostly computer science kind of related work. So continuing Raju's optimism, I'm kind of optimist in a sense, because you must have heard about all this budget cuts and things like that, and many universities are worried. But however, if you're working in AI, you don't need to be worried too much, okay? Because there's a lot of emphasis. What is going to happen is that if they, let us say, if they cut a particular agency by 70%, then they'll say the 30% of the money we are giving you, but all the money has to be spent on AI. So those are the kinds of things that you're going to see. So for AI people, it's very good as such. So NIST itself, like one of the questions that you asked is how do you place it in the AI action plan? Now the AI action plan, which came out, most of you probably read it, there were 3 pillars in there, okay? And the 3 pillars are mostly to accelerate innovation. Pillar 2 is build America AI infrastructure. And 3 is lead in international diplomacy. So these are the 3 major pillars, and a lot of stuff associated with it. And NIST, along with our brother/sisters organization, has been quoted 29 times in this one. 29 places it has been quoted. So I believe we are going to play a big role. Now, again, as you mentioned, Raju, that there is something to do with appropriations and the White House saying things. So the White House can put an executive order, but the Congress has to appropriate money for us to do works. So it looks like right now, in both the Senate and the House, things are looking good for AI work as such. So we might see future funding in this area. So as NIST itself kind of works, it does fundamental research in measurements. So we work on what is known as the AI metrology and metrology for AI. Actually, let me tell you what that is. So it's metrology for AI and AI for metrology. What does it mean? Metrology is measurements. So we actually measure AI systems. So a lot of you are kind of actually building AI systems. A number of questions have been asked about bias, fairness, and so on and so forth. So we actually look at developing techniques to measure those things. So it's a measurement, art of measurements. And measurements involves lots of things, and standards play a big role in these measurements. And we even have an institute called CAISI, which is actually mentioned the Standards Institute in the action plan over and over again. So those are the kinds of things we do. And then we also do, rather than metrology for AI, we do AI for metrology also. We use artificial intelligence to measure things as such. How do you measure things? How do you better measure things? So like, for example, like a lot of physical units can be traceable to NIST, like the length and the kilogram and so on and so forth. Now we have the information age. So you have the informational measurements too that you have to make. By the way, actually, one of the things which happens, we are going to the SI system is a lot of people are worried if you go through the SI system, how are you going to order the pizza in centimeters? That's a big worry. So we are measurement people. And one of the things that pizza did a good job in India by changing them from SI system to the old system by selling pizza in inches. Otherwise, in India, I don't think they sell pizzas as centimeters. They all sell in inches anyway. So you got to be careful in terms. So we are all measurements people. So these are the kinds of things we do. We do a lot of work on voluntary standards. So we contribute to both the national and international discussions on AI. So these are the kinds of things we do. And I think probably you're going to talk about how we are interacting with academics, now or later.
Well, there's another question there.
Okay, so I think I'll pass the thing. I'm just only giving you a brief overview of some of the activities do. We are a small organization with a big impact.
So given the importance of this question, even though we are running a little behind, I would entertain a question or two if anyone has one.
So my question, right, so as a scientist, I see AI as a very powerful tool, but a tool. I also think there's a lot of value to still doing basic science research, and I sort of still believe that that's a good way of, extrapolating, which we don't yet do with GenAI. So when I hear things like, yeah, you're going to cut some part of program and then that funding is going to AI, it concerns me. It makes me wonder what's going to happen to our strength in sort of, basic science research. And I was wondering if you guys could comment on it or help me reframe if there is a different way of thinking about it.
Very quick, very brief. If you look at the AI institutes, right, Many of the AI institutes are funding fundamental science. I think therein lies the issue here. And the second thing, it's not easy for everybody to do quantum, but everybody does AI nowadays. That's what the issue is.
Yeah, I can save a bit of time since you're kind of actually referring to my answer to the second question here a little bit. So within NASA, of course, most of our funding programs are in different sciences like earth science and space science and the like. But without even asking, many have proposed including AI as part of that. It is only use of AI, not R&D, but at least that's a way that we're essentially kind of driving AI research, because we end up finding out what the needs are in the sciences. And you get that initial use from whatever would be funded in those science programs. And that drives some of what I mentioned earlier about the few programs we have that do have some applied research in AI. And I can imagine that can drive later, let's say, what NSF programs may solicit.
So the question is, every administration, when they come with their priorities. Okay, so whether you take one, you always have this issue. You take it from somewhere. You have to get it from somewhere. So that's always the case. But as you said, it's not like everything is pouring into one area. But they are looking at. In fact, we had 6 workshops. I don't know how many of you participated in that. It was all over U.S. called AI for Energy, AI4Science. And it was done over a couple of years. And then the report is available. You can download it from PNNL website. And recently, IEA, International Energy Agency, they released a document called AI for Energy and Energy for AI. So they talked about all the issues related to that, including chip design to the data center issues and everything. But with respect to materials innovation, material discovery, so there is an Office of Science which does that, a lot of work. We are in the Applied Energy program. So we are looking at, so this goes back to some of the question that investment. I just want to share one of my thoughts. Where I sit, I read so many proposals, so many of them. And the real estate is given is 10 pages, for example. So this is not a complaint, but this is one of the feedback I want to give to the university, is 8 pages is all about their research. And remaining 1 page is what all they have done, what facilities they have. The 1 page remaining is what they want to do. So this is where I think you have to look at it very carefully. What is that you want to say? What is the problem you're going for? So this is exactly what emphasizes the point that why basic science research explained in your proposal will reach all the way top, saying that no, this is all what's going on. So that's one thing that the university has to do. And also the university administration at the top level has to also write what they feel about the science and why they support science. And if you follow AAA Science magazine, they have written an editorial and all that. But I think it will come to some level of normalcy soon. You always have these things happen, but I am optimistic. Hopefully everything will settle down. But it's a two-way process. The university system also has to showcase why they should not be talking about what they are doing purely. They should say why they are doing, why is that critical, how is it important, etc. So anyway.
No, I think just expanding that, I think if, for example, DoD is giving some funding and say, this is a problem they're working on, then we go through that and look at the gaps. What is that? Right? Certain things could be easy things to do. Some things they need a little bit more. And certain things they need some of the basic things and new things to come out. And we have within the DoD, Army Research Office, Air Force, Office of Scientific Research, and ONR. These are the ones which are the mouthpiece for the universities. But within the other thing also, whenever you're talking about the computational aspects of in computer science, it's not 6.1. It's more than 6.1, right? So maybe reaching to the labs, because that's what needs to do them. Because if you talk about impact edge, if I do these things, this is what I can help you. So in a way, you need to understand what is it we are trying to achieve. Without understanding, you say, well, this is my greatest idea, then it's going to be hard to sell it. So I think we are looking for collaborations across all those things, even though whatever happens, that's going to happen. But what our talk is coming, as you said, that's going on, but still the gaps is what we are going to work on, trying to figure out how to solve the problem.
Yeah, I'm going to be quick here because of the interest of time. But I think what you mentioned in terms of the future proposals, the important thing would be is interdisciplinary type of proposals kind of thing, collaboration between the computer scientists and the engineers and the scientists. So that's what is going to play a role. And the other thing I just quickly point out with Sudarshan's following on that is that when you write your proposals, there are the small proposals and the big proposals. In the small proposal, you have to emphasize your technical impacts and so on and so forth. In the big proposals, when they talk about a $100 million kind of thing, it's not only the technical things that matter. You might write a really good technical thing, but there's a lot of other things going on in terms of organization, in terms of commitments from the university, all kinds of things are there. So you have to be careful. A lot of times when academicians write the proposals, they emphasis on the technical things and forget about the rest of the things. But the government works differently.
Just to exactly that point, I missed that. Thank you for reminding. So when we have a $100 million proposal, it's a big proposal, for example, they ask, some of them they ask 2 million, and some of them ask 200 million. So the 2 million their proposal is written is that we are going to shake the earth, okay? But the 200 million, they'll have a toy problem. So that is exactly the problem. So you have to understand what is the commitment, how many hours are spent, what resources you are going to, what is that you're going after, why is it critical, what did the industry take. Like DARPA, the DARPA catechism, why is the problem important, etc. So that's exactly what we do.
Thank you. Let's move on to the second question, and in the interest of time, I would request the panelists to stick to remarks for about a minute or so. So in academia, we not only like to receive funding, we also dream of helping the agencies spend their resources. So how in this Gen AI area, what forms of input from the research community are most useful to your agency in shaping your programs and priorities? And can you give us any guidance on how you can engage us most effectively in shaping the field, setting the priorities, and so forth? And you could go in any order, but please stick to a minute or so.
Brief. The number of proposals that was submitted from the university for a large program in DOE is very little. We either the usual people submit, or if you want to be really successful, you need to know how to form a very good team. That is also a huge research effort, actually. See, they probably grow across the wall and then have some couple of names, but we are looking at the bigger picture there. So that is the one thing. And we also look at, because DOE labs are quasi-academic setup, how many of you actually work with the national labs? What is the thing that you have done with them is also a good thing for us. We don't purely go by your H-index. We don't purely go with your publication track record. Yes, it is useful. That's all to that.
So, okay. Now, just quickly, in terms of, I guess your question was, how can the academicians help us? So one of the things that we kind of do is we have workshops like this, either at DOE or at NIST and things like that. So there we look input from the academicians to see what your problems are, or what you think are the fundamental problems.
Thank you. Raju, you want to? Oh, Nikhil, go ahead.
Yeah, just a quick kind of addition to my earlier answer. I mentioned that most of our programs are really driven by the science and the science needs. A suggestion is to have the PI for the proposal be from that domain, because that person can explain the problem that we care about and can explain where AI is needed. Because remember, basically, we don't give a damn about AI or any technology, right? It's what we care about our particular problems. Help translate AI into our problems and let our people see where AI has value.
Thank you.
Yeah, within DoD, typically, earlier I was talking about the gaps and certain things. What is it if we want to go with, say, cybersecurity on the battlefield, whatever new things coming up and all. Typically, we hold workshops to get some academic experts and these things to listen to them, so that we try to develop certain things. So that is one kind of input. The other thing is MURI. I know some of the people participate in MURI, but MURI topics mostly come from the academics. I think you guys need to be more proactive in sending those things. Don't wait for certain things. So it's a two-way street. So I think you need to be proactive in these things. So some of the workshops, certain things, whatever, they may not advertise widely, but if you know certain things, maybe try to get that information.
Raj, you're remaining.
Yeah, I think what Vipin did last year at NSF, he organized a conference on scientific computing. I mean, AI for scientific computing. And that was very important because they had a whole bunch of NSF personnel there, and that's a very good model. CCC organizes workshops of future kinds of areas to invest money in. That's organized by CRA. That's a very good vehicle for doing this. So I'll stop there.
Workshop report that you have done, if you can publish it in IEEE computer or ACM, so that will reach DOE senior leadership. So you need to see how you can bring this up to a wider audience, so that it's Office of Science people, and we also look into those type of things. It is referenced in our strategy document. If your report is referred in our strategy document, that adds value and things. So for us also to see that it's not that we want to do all these things because we want to do it. It is a third party, like a workshop like this, who are experts, who are saying that these are the areas that we need to be doing. So that adds a very good input for us when we write our funding opportunity announcements.
So that's a great suggestion. So a position paper might be a good output of the workshop as well. Thank you. So moving on to the third question, it's on the scientific foundation models. As you know, the White House AI Action Plan has emphasized the development of scientific foundation models. What are some of the challenges and opportunities that you see in supporting such models within your mission-driven context? You want to start maybe at Raju's end this time, or?
Sure.
I can just quickly say one thing. How many of you follow what is going on in DOE labs? They have a tremendous amount of foundational models developed. You should take a look at that and then try to work with them. If you work with them and then submit proposals and things like that, that adds really a good value for DOE to see we are attracting the right people for this proposal funding opportunity, and what is our return of investment that we are going to get, what is the risk that we are having here. All these things when we assess, when we see that kind of feedback coming from you, it is really helpful for us.
So Anand Grama asked a question today, just before. You have a sparse representation of Anand Grama, and we need to combine that with a very high resolution representation, right? So I think this is very important to have a foundation model that will adopt and adapt over time, and ability to and flexibility. And I think the scientific community at large should be involved in the derivation of the foundation models and not maybe just one lab. I think that's important.
So yeah, actually, for NASA, adding to what you said, Raj, that we do run missions, space missions, airborne science missions. So anything that helps with running foundation models on board, already we know about the work in like quantized models or taking parts of the foundation model that are appropriate for particular subproblems, running those on board. That's certainly of interest.
Yeah, within the DoD, sometimes the lingo is what I think earlier I mentioned that is generative AI for national defense kind of a thing. And when you talk to them, what is generative AI you're looking for? They'll say cybersecurity, mission planning. And then what are the things people understand, right? That's what I think sometimes. If you think through carefully, maybe let me put it in a different way. Physics-informed generative AI, if I'm doing weapons development, either materials or any kind of things, maybe that's what I'm really looking for. Or data-driven generative AI, that's what mission planning, command control, a lot of data is coming. They want to evaluate those things. So it's a different way they look at these things. So sometimes understanding the terminology also helps. So I think that's where I think talking to some of the researchers within the DoD, maybe you'll get a flavor about what is that. But if you look at a global point of view, that's what they're looking for impact. Okay, whatever generative AI is done, this is how it helped the soldier to do something. This is what in the current battlefield something happened. But what is the science behind it? What is that originally happened and all? Well, they got some data, whatever from observation, or maybe sometimes they don't have data, so they generated the data and they have some sensor data from there. They're trying to get some generative AI to work so that it gives the decision maker what are the decisions they can make. And so it's a multi-model thing. How do you combine those things, right? What are the gotchas? How do you make sure it's going to work? I think within DoD also, one of the things, whenever we talk about AI, mostly this comes back to trust, reliability, and consistency. So whatever models that they are there can be promised it's going to be trustworthy. So those are kind of things which revolves around, those are the kinds of gaps which we'll be looking from academia to say, I think this is what is going to really get the right way to solve the problem.
I'll pass in the interest of time.
Okay. So let's move on to the fourth question, which is kind of like an open-ended question. So give us your best advice. As you know, academia is feeling a little lost this year, given all the changes that are happening in terms of funding priorities and funding regulations, et cetera. So how do you see the role of universities and research institutions evolving in response to the national AI strategies? So what changes are needed from our side to better align with your agency needs and priorities? Again, those of you who have some opinion on this, feel free to respond, and it's okay, not everyone has to.
Just one thing is that I hope computer science departments show greater regard for interdisciplinary research. Right now, they really don't. So, for example, you have to have publications in computer science journals and conferences. Those, in turn, if you develop a machine learning algorithms for a specific domain, they're not interested. The departments aren't interested in publications in those domains. That all needs to change.
I would just talk about large-scale projects. I've been involved in review of AI institutes, and one of the common problems is that the PIs, the individual investigators have done a good job in their own domain, but they have not talked about what is the real problem they're trying to solve from the overall umbrella. And I think this is a very, this problem arises over and over again. And I think one of the problems academia has to address is we have many junior faculty and many even senior faculty who are doing their own research under this big umbrella, but how can they be compensated for working for the big umbrella? And it is not very clear what that kind of compensation is, because it requires a lot of effort, and they might not get the normal return on investment, right, in journal papers and things like that. For working in a big, huge group, it might happen, but it might not happen. So I think this is also an important problem.
Yeah, if you look at that White House report, maybe they said classified computing, because whenever you talk about AI, the data is kind of a thing which is central part. We cannot deliver that. Even it mentioned NSF is going to do classified computing, right? DoD typically that's what we do. So, and universities, I know some universities don't want to do touch anything with classified. So this is one of the new things coming. So I don't know how the universities are going to adapt to that. I know some universities have done that because the DoD, some universities work with us. So this is one of the, when the data kind of a thing is going to drive whatever algorithms you're going to develop, and you need to get the data, then maybe that classified or different way of computing kind of things are going to come into picture. Maybe that could be an important thing, which may be additional thing which is coming because of this AI point of view.
Again, in the interest of time, I'm going to combine a part of 4 and 5 together on here so that you can start from here onwards. So again, we are a small agency, an IST, and we do a lot of research, in-house research per se. So one of the best things to do is for researchers to kind of talk with the NIST researchers, and they have to develop those bonds. So because we have several programs, like, for example, we have a program for undergraduate students. Like if you have students who are in your college, like the fourth going to the fifth, or the third year going to fourth year, on the summer, they can come and spend with us and we pay them. It's called the SURF program. And they do some very interesting projects in terms of either your domain materials or in the engineering lab, or come to our lab and do computer science kind of activities. So that program, sometime in January, you have to apply for it. It's very, very good, both for interaction. The students, a lot of times the students come in, do a very nice project, go back to their advisors, and then because of their contacts, the advisors come back to us and so on and so forth. So it's one way of doing it. And the second interaction is that we have what are known as the NRC postdoctoral fellows. It's a very, very good program. This is like you finish a PhD, you have to be a US citizen. That's the only constraint. And then you apply for this program and you can stay for 2 years and you are a federal employee at that stage. And what you do in this, when you come here, is that again, you create your network. The student creates the network so that when they go and become a faculty member somewhere, they already have this. One of the pressures for the young faculty members is when are you going to get your funding from? So if they come to NIST, they already have contacts with DOE, because we also do work with ARPA, IARPA, ARPA-H, DARPA, and we do a lot of work with them. So again, you get all these contacts into this whole world of DARPA, IARPA, and so on and so forth through NIST. We do have some programs for faculties. Again, we did on the contact expense, come and spend sabbatical at NIST. So we pay the salary, whatever it is. Okay. Again, it depends on whom you're working with. So we have a lot of these programs, and the grant programs are very hard to get nowadays. But anyway, we do have some things going on if someone is interested in things like that. And then we have a prep program for universities where they don't write any grant proposals, but there are only some universities are involved in that. I don't know, Minnesota has not applied for it, okay? Purdue has not applied for it, I guess. So, but there are some universities, like University of Maryland has applied for it. So if you want to fund some professor in University of Maryland, we can do it without writing any proposals, nothing like that. So there's a grant. And every 5 years, this one goes in a cycle. It's in our third year. The first cycle was over, second cycle, it's in the second year. So after 3 years, look out for it. That's a good program to interact with this. So, I mean,
Thank you. We got started on education and workforce development, so please continue with that theme, Raju.
Workforce development, as you said, I think students is one thing with all the Army labs or DoD labs, they support students in summer. And the other thing is maybe faculty, usually, for me, I used to encourage junior faculty to come and spend summer there, and we pay them. So usually the networking is what they really develop during the time. And a lot of people don't take advantage of that. And I really encourage people to take advantage. And the other thing is also, some of our employees are junior, in the sense after their bachelor's, they join and all. They'll go for master's and PhD. And sometimes we want to send them to some universities, and maybe having some kind of a networking is really going to help for attracting those employees to come to your university. And then we have different programs, like VPN used to lead one Army HPC Research Center, which all these programs used to be transparent of getting students and faculty and certain things. So there are some programs which our consortiums are there within the DoD, still working on universities and all. They support them, but anybody is there, I think every time, I think maybe around November, December time frame, usually this announcement will come for faculty sabbaticals or students to come to the labs. Maybe taking advantage of that will be a good thing to do.
With respect to DOE, the only thing that we have national labs where you can go and spend sabbatical. That's where the research happens. Students are also postdoc. Many of them end up as either faculty or other federal agency, maybe not now. The other one is we have something called ORISE Fellow. I don't know how many of you are familiar with that. It is ORISE Fellow. The idea is to provide, we hire senior faculty, mid-level, and also junior faculty to get them involved in policy making. How do you write a strategy document? How do you develop a roadmap? How do you develop a funding opportunity announcement? How do you engage with stakeholders? This is a great experience for you to see how the inner workings of DOE is, so that you can come back and educate others how to write a successful proposal. The other thing that we have is called AAAS Fellows. So we host a lot of AAAS policy fellows. So that's another opportunity for any of you or postdoc or somebody who wants to come. And I don't know whether faculties are allowed to become a AAAS fellows. I'm not sure. But ORISE fellows, yes, you can. In terms of workforce education development, all our programs have a workforce development program piece. In fact, the public-private partnership that I manage, Smart Manufacturing and Simani. In fact, Simani is a great example. We took a truck, a big truck, and converted it into a lab. And then we drive the lab to a small, medium enterprise. And during lunchtime, some of them, they can walk into the lab and get trained in cybersecurity for free. So we tried to get them to the training. They said they cannot come. So we took the training to them, saying that, okay, here it's a training you can take. So those are the kind of things that how you can help building curriculum, micro-credentials, et cetera, et cetera. So the universities can help in that. In fact, I mentioned yesterday, Purdue University, with our funding, created a BS in smart manufacturing. So that, and we also work closely with the community colleges. Very, very important. I don't know how many of you transfer community college students to University of Minnesota. California, Berkeley has the highest percentage of community college transfer to UC Berkeley, actually.
Yeah, many of us do. Nikunj? quick, please.
Yeah, so at NASA, we need people who, they of course know data science, but they can work with domain experts, can learn enough about that other domain to be able to translate those problems into data science problems, come up with a solution, translate that back into the domain. So I'm happy to see the increasing number of data science programs in other departments where there is that focus. And of course, there's some also in computer science where they also encourage people to target problems in different domains, and hopefully they like the domains that NASA is interested in.
Raj, you have the final word.
Well, I think most of you have said the things I wanted to say. The only addition I would like to add is that industries, especially defense industries, have an incredibly hard time to find domestic students. And I think this is some place where NSF is very interested in. And there are certain special fellowships for encouraging this, especially in the area of cybersecurity and AI. And the only condition, I think, post-graduation for the PhD is to work in a federal government lab or an industry which aligns with the Department of Defense.
We call them smart scholarships.
Thank you very much. And I want to thank our panelists one more time. I think what the advice you gave us is very helpful.
Exciting day, and I think the last panel is now, the last panel is on the synthesis. Can you hear me? Yeah. So I think Vuk Mendik is going to run the last panel, and we hope to be able to get out by 4:30 or not too much after that. Thank you. But thanks. This has been an absolutely fantastic 2 days.
You can sit maybe here and then come up and present, if that's okay.
Oh, so I'm saying for the other panelists.
That out of the way here.
Okay, I think we should get started. So my name is Vuk Mandic. I'm a professor here at the School of Physics and Astronomy, and I work with Vipin and Shashi in our data science initiative. Welcome everybody to the synthesis panel. We have 6 panelists, and you've actually met all of them. They've participated in the workshop so far, and we'll reintroduce them in a minute. Each of them has been present for the entirety of the workshop, and for each of them has taken 2 questions or prompts through which that they thought about throughout the workshop. So they basically tried to synthesize what they hear in this workshop through that particular lens or lenses. So we have this slide deck which has grown to about 16 slides organically over the last 2 days, and I'm excited to share that with you. We'll go through the panelists one at a time, and since we're fashionably late, I know we promised 5 minutes, but let's see if we can do maybe 3 minutes per panelist. We'll start with Srinivas here. Srinivas, if you can maybe briefly introduce yourself and then just launch into your...
Sure, yeah. My name is Srinivas Alluru. I'm from Georgia Tech, and since I'm partly responsible for why we are fashionably late, I'll see if I can be quick. I'm going to address a couple of, three questions actually. So let me start off with question one. What are the most compelling, strategic, and potentially transformative Gen AI research questions that we could ask? So what I learned from this meeting, listening to all the presentations, is that there are like two grand challenge problems here that we could address. So the first one is about, can we transform AI from a prediction, Gen AI in particular, from being a mere prediction tool to a co-pilot for theoretical discovery? So let me elaborate on that a little bit. So if you look at the scientific breakthroughs that are made so far, such as AlphaFold for protein folding or AlphaGenome for finding the effect of SNPs, single nucleotide polymorphisms, or weather forecasting simulations like systems like Aurora, GraphCast, Prithvi, etc., they're all fantastic prediction models. However, what we lost are theoretical insights. So AlphaFold folds, everybody loves the way it folds. We know the answers, but we haven't really learned anything new in terms of how proteins fold because of AlphaFold. Now, AI interpretability may help a little bit, but it only explains how a network reaches its output, but it doesn't connect these explanations to the domain zones. So the question is, can we use Gen AI to somehow discover fundamental principles and mechanisms that reflect the predictions that Gen AI systems are making so that the humans are not used to just consulting AI as an oracle, but also develop a better insight into the domain itself. So that's one grand challenge. A second thing is there is a need for accelerating the development of scientifically grounded generative AI systems. So many of you are using Gen AI in your science, but you're also finding a lot of loopholes. So to take a stock, we have already seen remarkable progress in representing complex and high-dimensional distributions, but the performance sometimes seems to degrade when the data is sparse or noisy, and still a lot of progress is needed to properly enforce physical constraints and conservation laws, etc. And also, these models are computationally intensive, and when you try to use them in the real world, you often have to sacrifice either accuracy or uncertainty quantification and things like that. So accelerating research in this direction would be a good idea. The second question I want to address is, what are the recurring themes for Gen AI that transcend applications, that cut across many applications, and what are the needs, and how does that tie into White House action plan? So I have a big list here, so I'll go through it very quickly. One thing that was touched upon in many domains here is the need for development of AI-ready testbeds. There are disparate and fragmented data sets in your domain. They're often created in specific application contexts. There are challenges for harmonizing the data, making the data discoverable, and also generalizing what kind of data helps us build Gen AI systems that have generality, et cetera. So this comes under the White House Build World-Class Scientific Data Sets theme, and that is something that is recognized as important by many of you. The second thing is foundation models for integrating multi-model high-dimensional data and also physics-constrained exploration of vast design spaces. Another common theme here is the digital twins for natural and engineered systems. And an interesting twist that is important in some domains, such as neuroscience, is using AI-driven techniques to study natural systems. We saw an example of that, where AI-driven pattern recognition is used to sort of figure out the brain activity in response to different things. And finally, the development of AI cyber infrastructure itself, and not just the hardware cyber infrastructure, but also software cyber infrastructure to support the entire scientific discovery lifecycle, starting from design of experiment, data analysis, to investigation of alternative models and integration of Gen AI with classical methods. All of these things, I think multiple domains could use such software to accelerate, and we could leverage our common need to answer these questions in a way that's broadly applicable. And I'll stop with a brief answer to question 8, which is, what are the pros and cons of the myriad Gen AI techniques that have been developed? I'm not going to answer this. What are all these publications for? Hopefully they've all answered this to some extent. But I think the most important need of the hour is to let the users decide. So if we accelerate the scientific software infrastructure for building models, for experimenting and reasoning with multiple models, then I think people can pick and choose, and we have a better knowledge over time of what would work best for what types of problems and so forth. And obviously, there are efforts already, both commercial companies like Weights and Biases, which is now part of CoreWeave, and also open source platforms like MLflow. I think accelerating these would be nice.
Thank you very much, Srinivas. So, Bhaskar, if you like, you can speak from there or
Yes.
come up here, whatever you like.
First of all, I think this was a thank you for organizing this, Vipin and crew. This was a wonderful opportunity to meet people and also immerse myself into the GenAI what next questions, right? And so for the past two days, I think the highlights here are, and probably resonate with everyone. One is creating simulation data sets, right? So from a generative AI perspective, collecting high throughput experimental data for various disciplines may not be possible, maybe suboptimal. So creating synthetic data, whatever the synthetic data means, simulation data sets would be critical. And then identifying canonical problems, right? So geometry or like, and Vipin was talking about the traveling salesman problem as one canonical problem that could drive the discipline. Identifying canonical problems would be nice to have from an AI4Science perspective. Second is, and this is something that Anant and other people talked about, and Ganesh also talked about, right? So there's generalizability of GenAI tools, but then with that we need some formal guarantees, right? So and then this is a rich area from an applied math perspective, right? So can you show convergence rates if you have a mesh? Can we provide non-vacuous generalization bounds, trade-offs, and how much data is needed, data sufficiency, thinking about that, right? So that we can invest resources into collecting 1 million data points or 10 million data points, right? As long as you know what that curve look like, even empirically what that curve looks like, right? That'd be good. And then this is something that was a very nice initial kickoff by Anuj and others on terms of what are the different ways of rigorously injecting knowledge into the GenAI tools. And yeah, there are systematic ways of doing this, right? So that we learned architectures, losses, post-train conditions, and so on. And then the key thing from a science perspective is this UQ, maybe going beyond verification and validation and giving calibrated intervals of uncertainty so that we know when to get more data, when to trust the system, and so on, right? These are the 4 key themes that seem to resonate from question 2. And everything in blue there on the screen is basically how they link to the AI action plan. I think there's a lot of things here that link to the AI action plan. And then in terms of question 7 was, are there challenges for incorporating different kinds of priors? And so here, I think there's very interesting. So we talked about 3 or 4 ways of integrating priors, right? So in terms of architecture, in terms of loss functions, in terms of post-training. So is there a roadmap, checklist, right? So for this kind of problem, I should use this. For this kind of problem, I should use this and this, perhaps, right? So thinking about that would be super useful because we talked about materials, we talked about agriculture, we talked about ecology, and each of them have different flavors of these. Second is we have GenAI models that could be general purpose, but then we want to maybe fine-tune them for specific applications. So there could be a trade-off or a fight between model and constraints, or one type of constraint or the other type of constraints. So how do we actually think about this, right? So from a GenAI perspective, and can we come up with formal ways in which we say, oh, if you have this kind of generative AI model and this kind of equations, or if this kind of system, this is how you want to integrate, ensure that there's no constraint dissatisfaction, and so on. Right? Finally, there's this question about, I think Raj talked about steerability and generalizability and so on. So how do you think about modular designs, right? So Lego-like designs that integrate like hybrid neurosymbolic methods, and then how do you also integrate process-based differentiable models, right? So we have a gamut of tools. How do you integrate them in formal ways? And then finally, priors alter error behavior. So understanding this, right? So especially when you have a GenAI tool with certain distribution, and then you add constraints to it, the distribution changes perhaps, and how understanding that would be critical from a mission critical perspective.
Okay, thank you, Bhaskar. Our next panelist is Paul.
Great, thank you.
Can you introduce yourself briefly? Can you introduce yourself briefly?
Yes. I'm Paul Hansen. I'm from the University of Wisconsin in Madison, and I'm an ecosystems ecologist. And I just want to reiterate, I guess, what a great couple of days this has been, what a privilege it's been to be here, and how exciting from the domain side to see all the advancements and to learn and to be able to imagine what we can do on the domain side within the AI realm with collaboration. And so I was charged with coming up with a few questions that sort of synthesized a few perspectives over the last couple of days. And specifically from the domain side, so we could imagine more than one domain scientist being part of these questions that are being asked. And I've got two groups of questions on two different slides here. So the first have to do with data. There were a few different data repositories that were represented here today, and the question is about how we can grow the corpus, or how we can include the growing corpus of domain data in generative AI, and do it in a way that really engages the domains that produce those data through provenance tracking, providing credit, but more importantly, feeding back to the domains itself so that when scientists understand how their contributions from the countless hours that they've spent collecting these data, how they can inform and contribute to computer science and AI science, that it feeds back in ways that makes that a positive experience and kind of grows those interactions. The second question is what advancements will enable GenAI to fully use multimodal data and data with missing data? This seems to be a theme that crosses almost every application, and of course in ecology this is first and foremost, from everything from genes right up to satellites. The second slide is a little bit more about a human-oriented approach. The first question is, what would it take for GenAI to not only match, but surpass the predictive skill of a highly trained domain scientist? This resonates, I think, a little bit with what came out in the health discussion, where you train a system on a population. And now how do you decide, and what are the implications for applying it to individuals? And I think a question that's sort of posed this way resonates with anybody who comes out of the domain sciences too. A theme that comes up over and over again, and it's already come up a couple of times in this panel, is the inclusion of expertise from domains in generative AI. And here I've just highlighted three different areas: knowledge-guided machine learning, reinforcement learning, and then evaluation of both the frameworks and the outcomes of the generative AI. And then just a question that's near and dear to me, which is extreme value distributions, and how could we possibly do a better job at extreme events? So thank you very much.
Thank you, Paul. Jarvis?
All right, so again, I'm Jarvis Haupt. I'm with the University of Minnesota, Department of Electrical and Computer Engineering. So a couple of things that, as I was, this was a great workshop. I really enjoyed, and thank you to the organizers. I was thinking about these questions. They were kind of posed ahead of time, and I was using this to distill with my lens some of the responses here. So I guess, I could just read from this. I guess these will be distributed. But the first question was, a lot of applications are concerned with things like hallucinations, uncertainty, and safety considerations. Are there kind of cross-cutting ideas? Are there ideas that are universal that could be transferred across? A couple things. First of all, just to challenge the premise of the question a bit, it was brought up in an earlier session that not all hallucinations may be bad, right? If we allow a little bit more leeway in this, it may lead to new discoveries. I think we do this for ourselves as well. So I don't know if we call it hallucinations, but at least the creative thinking is not without its virtues. Some of the other ideas would be, for instance, there's a lot of models that we have access to now. If you're thinking of large language models, there's Claude and the Llama models and ChatGPT and Gemini and things like this. They're all trained slightly differently, so you could use outputs of one model to validate another model. So these might be ways of trying to reduce uncertainty. It's kind of like a mixture of experts type validation, but maybe slightly different. You could also use models to kind of scrutinize each other, not just validate, but also police. One would produce a response and you'd say, is this legitimate, or does it adhere to whatever principle I'm thinking of? whether it's a physical principle or an ethical principle. One of the concepts that came up as well was this idea of sensitivity analysis. And I think that this is an interesting insight because in a lot of ways, if you think of classic machine learning type problems, maybe a supervised learning kind of problem, you're training on discrete data, right? You have instances. And what you're hoping is that you're behaving kind of sensibly off of those instances, right? The generalization is kind of the value add. And I think sensitivity analysis could be a good way to kind of try to quantify this, to look at what's happening locally in the vicinity of maybe the training data points or farther away. But this idea of like trying to understand what was sort of learned from the data, which was discrete, to something that we're going to generalize off that grid. And then another idea that came up was this idea of negative examples, that maybe we don't really have those kind of pervasive in our society, tabulated in the same way that other kind of collections of information are, but they could be useful here. I think that's worth exploring to see. If I go to the next slide, the second question, what are possibilities for cross-domain complementarities for addressing data scarcity? So one that came up earlier today, I'll just start from the bottom here, was this idea that your data set might be structurally similar to something else. So the example that my colleague Sachin and ECE discussed was they were looking at this EDA task, but they didn't have access to a wealth of training data because of IP restrictions, so they trained on street data maps, which is a really kind of clever idea. Some of the other things that I was thinking about is, again, just to reiterate some of the concepts I talked about yesterday, is this idea of problem decomposition. If the problems themselves might not be holistically related, but if you can decompose each problem into subtasks, there might be similarities in subtasks. So it's almost like we're doing a physical latent embedding ourselves, right? We're saying, this is similar to that, so I'm going to try to share insights here. And then just more generally, this idea of finding potentially unifying latent space representations. Just one other thing that I wanted to say here, kind of as I was thinking about the panel and the structure that we were presented here, I wondered if it's also a microcosm. So this is a situation where, again, we were provided the questions ahead of time. It was kind of like view the workshop through the lens of these questions. And I don't know that many of us get that many opportunities to do that. I was thinking about trying to pose questions like that to the students in my class, but it sort of made me wonder, just kind of as a parting thought maybe, with some of these kind of applications, would it be useful to train with the questions in mind ahead of time, right? Instead of looking at, for instance, an autoregressive model or the autoregressive kind of characteristics of a large language model, just looking for latent connections in text, say, I'm interested ultimately in answering this question, right? It's sort of like you're baking in attention ahead of time. Just a thought, but it was something that kind of was a microcosm for this modality, and I thought I would share it. So, thank you.
Thank you, Jarvis. Lior?
Lior Choresh. I'm the head of the Mathematics and Theoretical Computer Science department at IBM Research. I was tasked with 2 questions, and I added 1 bonus. But beforehand, I would like to thank all of you because I learned a lot during this 2 days of workshop from you and from my peers, so I'm grateful being here. So the first question was around interpretability as a common theme across many GenAI applications in different domains. Are there any recurring approaches or methods that can address that, and are there any ideas that can be carried out across different domains? And few ideas and propositions that at least I could conceive. One is that when we look into the specific primitives that are transferable between one domain and another, whether we use attention mechanism, we use structured state space models, gradient-based methods, or causal discovery, what we can carry from one model to another is typically the knowledge rather than the specific instances of data, right? So as long as we ground our models with some fundamental principles and we are conscious, we know how to articulate those, these can be carried out from one domain to another, from one problem to another. Another concept or idea is compositional generalizability. So if we are capable of identifying some modular combinations of interpretability primitives, so if we are capable of learning representations, and those representations are common as a concept rather than specific to one instance or another, we can then systematically recombine them across different scales and across different domains. Another possible way to go about the domain disparity is if we look into systematic learning, right? Rather than asking an LLM or a GenAI create a model for me. Great, you have a model. We can ask, generate a program, generate a code that describe a certain model. Now, the advantage in doing the latter is that I can now take that description that includes some of my background theory and maybe some other preferences, and ask another model to create such a model, right? So I'm taking maybe a step back. I'm doing systematic learning rather than generating models, but that is much more transferable. This is something that we can now have other experts scrutinizing what we have done and trying to figure out whether the assumptions we put inside are sensible, and it is much more transferable in that fashion. Another concept which was mentioned here in different versions is to incorporate feedback, right? So if we are capable of doing cross-domain validation, we can now bring a feedback loop and check whether some of the concept indeed transferred from one domain into another domain. So that was the first question. The second question was around universal explainability. So explainability relies on vocabulary. Different domains have different vocabularies. Can we come up with a generic explainability framework that transcends the separate syntax and semantics of vocabularies? So that goes a little bit into the linguistic side. One distinction that I wanted to make, and I hope that it makes sense to others, is we talk about explainability, we sometimes talk about interpretability, and sometimes some of us talk about derivability. And these are three different concepts. If we try to frame them, at least in my mind, explainability means that you have a decision and you make it maybe a post hoc explanation of that decision, right? Your system came up with an output. You want to explain what was that output to a human, right? Interpretability, on the other hand, is a model that you can explain to another person, this is the model and this is why it makes sense. Where derivability means that the model itself was formed in a way that is formally verifiable without any human, right? This is something that does not require any human approval for its consistency. So with that stated, one thing that we can try to do is to come up with a unified language. We heard a little bit about formal methods. So these are excellent means for us to, as a community, to come up with some consensus as for we will all going to use from tomorrow one system or another, and we will articulate all the theorems that we derive in that system. And once we do that, the beauty is that we can build up a collective corpus, right? So my theorem doesn't dust in a paper somewhere, but it can be employed by someone else, and your theorem can be employed by someone else, and that makes it more scalable as a community to build something. Of course, we can incorporate information theoretic machinery. We can bring algebraic geometry in order to embed theory and data in one unified space. And the other thing is we can bring some other notions from ontologies in order to bring the abstraction of, okay, we use a language when we define a model. We have operators, we have variables, we have programs. There is a Corey Howard definition of a program that also extends to algorithms and proofs, and it's not only models. If we try to come up with such a unification, it may help us to understand what we are doing in a way that is transferable. And once we do that, we can also build translators or mappings between one domain space and another. So that was my attempt to address that question. I have one more bonus slide. I hope that's not too much today. So I also noticed that we may talk about two different types of discovery as a community. One is GenAI empowered simulation. So the physics or the knowledge is given, and it's really about exploration in some configuration space and trying to figure out what properties may be satisfied after we run such a simulation. Pins was mentioned, neural operators, physics-inspired, Hamiltonian neural network, Lagrangian neural network, equivariant, and so forth. The other types of discovery is one where I think there was a question about Nobel Prize here and maybe some other question about getting an understanding of what those models are doing, is discovery when we have an unknown relations. And in that context, we can see how the scientific method has different ways of evolving, right? So we can start with hypothesis generation from the theory, verify empirically with data. We can go in the other direction. We can induce those hypotheses from the data. And we can try to do the reverse even. We can try to start from the knowledge, from the data, and try to combine them together. So I just want to leave this as something that we may want to consider as another paradigm for trying to bring more insight and understanding to the discovery mission. Thank you.
Thank you, Lior. Jag? Thank you. So my name begins with the 10th letter in the alphabet. And in this panel, I'm going last in alphabetical order. Which is just pretty amazing. So I want to begin by thanking Bobby. Glad that you're here in this session, Vipin, and the other organizers for a really fantastic 2 days. I had two specific questions to address. The first, to talk about uncertainty, safety, hallucinations. These were topics that came up repeatedly in the presentations. And what I thought I would do is, rather than me trying to build a theory of all of this, just quote some of the things that other people said that I thought were really insightful. And so these are things that I think came up, are all comments that came up at least once in the words that I have here and in spirit in other presentations. So first, worry about out-of-distribution data. Okay, this is something that I think we all have. Rare cases came up repeatedly. There is a need for uncertainty quantification. A more general way of thinking about this is that we need validation methods. So there is a lot of worry about if your model works, you know that it works on some example and you have no idea about anything else. And if you have statistics, there's at least some theory of what the error bars are and what the significance is and things of this nature. Explainability and interpretability, we just heard a lot of a careful analysis of from Lior. My one bullet point on that is a shortcoming of GenAI that a lot of people are thinking very hard about is the inability to engage in symbolic reasoning, in decision making, and a particularly telling comment from this morning was that these models provide even less insight than computational models, which already are disappointing in their ability to provide insight, even though they've been used for years. Okay. I want to move on to the next question, which is also about other challenges. So this is now compliance, fairness, etc. So the first comment is, it doesn't matter how good the science is if the people responsible for using it or deploying it don't trust it, it isn't going to get used. And this was particularly emphasized in the agriculture panel yesterday, but I think that it came up in a lighter way in many other contexts as well. There was discussion, sometimes directly and sometimes indirectly, about the training data. And in particular, that the quality and the diversity matters. There was things like we should be able to consider diverse data types, new data types, multiple modalities. The way that people talk about this varied. What diversity means can vary a lot. It can be in types, it can be in demographics, it can be, in many different ways. There was issues of multi-resolution, multi-scale came up repeatedly. These are important things. These are tunable parameters in computational models that people use to trade off performance for accuracy. It isn't clear how you would use these as parameters in GenAI models. And then there was some discussion about being able to address outliers, being able to address small minorities, things of this nature, which overall aggregate error metrics tend to cause models to ignore. It was already mentioned by one of the other speakers, I think Jarvis, that training data in science tends to have only positive examples. We should figure out how to have negative examples. And this is certainly true if the science that is being used to train your model comes from publications. And we think of scientific publications as a really good source of training data. And then there were complaints about limited controllability of models in scientific contexts. Right, okay, so these were the two things that were assigned to me, and then as I was going through, it appeared to me that there was a question not on Vuk's original list that I thought I'd also do, which are, what are the cross-cutting challenges across domains? Basically, my observation over these 2 days were there were people experts in many domains, and they would talk about why their domain was challenging. And then one would hear very related challenges in a different domain. It's not that the challenges are the same, they're not, but there are similarities, and I thought it'd be interesting just to talk about them. We talked about trust and explainability as something that leads to trust. We talked about heterogeneity, and this is heterogeneity in the data and data types, but we also talked about heterogeneity in models and methods. There was perhaps the one point that got said the most was that data are often skewed, and data of interest, some data of interest may be very limited, very sparse. We've got to deal with it. A thing that was said actually more yesterday than today was that labels are expensive and are often not available, and so reinforcement learning is important. I think the issues of outliers and singularities of various types came up repeatedly. And again, just to remind people, since we talked about that quite a bit today, yesterday when we were talking about, for instance, hydrology, there was a question of, some small land feature can make a huge difference to how things flow and collect. In almost every domain, real-life testing is expensive and slow. And this obviously constrains what one does. So two things. One, this seemed to be the case for many domains, but this is not always the case. Where it's not always the case, we have high throughput setups that are possible, right? So in biological sciences, this started a couple of decades ago, in terms of high throughput experiments changing the bench. Today, in certain areas in chemistry, that is beginning to happen. But for most of the other domains that we were talking about, real-life testing is just not something that's easy to do. And what that means is that you've got to have good models. The models really matter. Digital twins are important. You've got to prove things out in silico as far as one can. Finally, there was some discussion of human-AI interface and how to split responsibility, how to divide the larger problem into things that the GenAI systems can do well and that humans can do well and in a complementary way. That was mentioned today, and I felt that this was actually an important point that applied to everybody, even though in some of the discussion, particularly yesterday, it didn't come up. And with that, I'm going to hand it back to Vuk.
Thank you very much, Zach. So given the theme of this workshop, I thought it would be very fitting to ask GenAI what it thinks about itself. So I fed an earlier draft of these slides to one of the large language models and asked it to produce 4 bullets. And this is what it came up with. I'll let you read those. I think I wouldn't necessarily prioritize them in the same way, but I think they're reasonably fitting. We are rather overdue, so let me ask if there are any pressing questions or comments or other thoughts on the synthesis of what you've heard today. If not, I think I'll just say thank you very much to all of our panelists. I know it was not easy to do this over the last couple of days, and we really appreciate your hard work. And I'll pass it back to
Yeah,
Vipin.
and again, reiterating, Vuk, this was an amazing 2-day meeting and made possible only because of your participation. And the synthesis panel idea sort of was added towards the end. And I'm so glad we did it because we got to learn the wisdom from all of you. So much more information than we would have done otherwise. We have this session recorded, as you all know. People have been watching them on YouTube and Zoom already. But like previous workshops, we have made these recordings available to people later on, and a lot of people come and watch. Those of you who have slides, we can post them on the website along with the videos, only if you give us permission. So we will be in touch with you, and if you give us permission, we'll post it. If you want to modify something, that's perfectly fine. But videos would still be available. It will be an excellent resource for everyone, including anybody who could not attend the workshop. So again, thank you so much. It is just such a remarkable pleasure for us to bring all of you and learn from each other, learn across disciplines. And I also like to thank Bobby, who literally ran the whole show. It's absolutely amazing, how she manages to pull year after year. Even the workshop at NSF headquarters that we held in 2023, she was running the show from here. So yeah, again, thank you, everybody. We have a reception outside, so people can hang around, talk to each other, unwind. And I know some of you have flights to catch, but enjoy, have a more conversation, and let this be the beginning of conversations across the discipline.
If you don't want